Hey there, everyone! Welcome to our Generative AI course. We're going to dive into some amazing techniques using Python and PyTorch to create stunning content. Now, get ready because we'll be rolling up our sleeves and getting hands-on with practical coding exercises. We'll explore various architectures like GANs and VAEs, which is super exciting. And just a quick reminder, make sure to check out the GitHub repository linked in the description for all the code you'll need. It's all laid out for you there. And stick around until the end of our session because you'll be taking on a final project to showcase all the skills you've learned. So let's jump right in and get started. Generative models are a fascinating area of artificial intelligence and machine learning, enabling us to create and generate new data samples that closely resemble our training data. Imagine being able to synthesize realistic images, text, or even music that feels truly authentic. Isn't that incredible? In this lesson, we're going to dive into the world of generative models, exploring what they are, how they work, and coding a few examples in Python using PyTorch. So, get ready to embark on this exciting journey of creativity and data. Now, let's implement a simple generative adversarial network, or GAN, using PyTorch. We're going to start by importing the necessary libraries, including PyTorch and TorchVision, which are, really handy for building neural networks and managing datasets. So the GAN itself has two main parts, the generator and the discriminator. Both of these are defined as classes that inherit from nn.module. The generator's job is to create new data samples from random noise. It takes a 100-dimensional input and passes it through several layers with ReLU activation functions. And guess what? It outputs images reshaped to 28 by 28 pixels using the TON activation function to make sure the values stay in the range of -1, 1. Pretty neat, right? Now, on the flip side, we've got the discriminator. Its task is to differentiate between real and fake images. It takes a 784-dimensional input, processes that through a series of layers with Lie-ReLU activation, and then spits out a single probability score, indicating whether the input is real or fake. Next up, let's define our hyperparameters, including batch size, learning rate, and the number of training epochs. Then we'll prepare the MNIST dataset, applying normalization and loading it into a data loader for mini-batching. After that, we initialize our generator and discriminator networks, set the binary cross-entropy loss function, and get optimizers ready for both networks. Finally, we set up a training loop. For each epoch, we train the discriminator on real and fake samples, and then we train the generator to create better fakes. This adversarial process goes on iteratively, allowing both networks to improve through competition. As each epoch wraps up, we print out the discriminator and generator loss. This gives us some insight into how things are progressing through the training process. The figure titled Applications of Generative Models features a vertical bar chart that illustrates how much focus is given to various application areas. On the y-axis, we measure as percentage of discussion, while the x-axis categorizes 5 main areas: image generation, text synthesis, data augmentation, style transfer, and deepfakes. Each bar is topped with a numeric label indicating its exact percentage. Image generation sits at 25%. Text synthesis leads with 30%. Data augmentation at 20%. Style transfer at 15%. And deepfakes trails at 10%. If we look closely at these figures, a clear hierarchy emerges. The largest slice of discussion, 30%, goes to text synthesis, followed by image generation at 25%. Then we have data augmentation at 20%, with style transfer at 15%, and finally, deepfakes down at 10%. A key takeaway from this chart is that more than half of our conversation, specifically 55%, is centered around text synthesis and image generation, highlighting a focus on these two areas. So, as you approach this material, prioritize diving deep into methods and examples relevant to text and image generation first. But don't forget, data augmentation, style transfer, and deepfakes are also important, just covered with a bit less intensity. Now, let's implement the Variational Autoencoder, or VAE model. We begin by defining the encoder class, which transforms an input of 784 dimensions into two distributions that represent the mean and the log variance. This design is super important for our variational sampling process. Using a fully connected layer, it reduces the dimensionality and applies the ReLU activation function, which helps ensure non-linearity. Such a key aspect, right? Next, we have the decoder class, and this one takes our latent representation and attempts to reconstruct the original input by reversing the encoding process. This involves another set of fully connected layers, and it applies the sigmoid activation function to output values between 0 and 1. Now, let's look at the main VAE class that integrates both the encoder and decoder. It performs this nifty reparameterization trick, which allows for gradient-based optimization of the latent space during training. This basically involves sampling from a distribution defined by the mean and log variance. Finally, we need a loss function that, well, combines binary cross-entropy with Kullback-Leibler divergence to quantify the difference between the learned distribution and the true distribution. This gives us a measure of how well the VAE reconstructs its inputs while also maintaining a structured latent space. And that structured space, it's not just for show. It enables us to effectively generate new samples while retaining those important characteristics of our training data. In practice, training a VAE would be quite similar to what we did with the GAN. You'd load your dataset and implement a training loop that optimizes the VAE's loss function. Throughout the iterations, the VAE learns to create new data points resembling our training data while allowing for smooth transitions across the latent space. Now, let's take a break for a moment. How cool is it that we can create entirely new images from scratch? Generative models have opened an exciting avenue for creativity and automation in various fields, such as art, music, and even game design. Imagine using AI to generate unique character designs, bustling cityscapes, or intricate patterns based on simple inputs. Generative models also pave the way for advancements in data augmentation, allowing us to artificially expand our datasets by creating realistic variations of existing data. This can be particularly useful in scenarios where collecting real data is time-consuming or expensive. Through techniques like augmentation, we can reduce overfitting and improve the predictive performance of our models. That's an essential aspect of building robust AI systems. Now, let's implement the following code to generate text using the pre-trained GP2 model. First, we begin by importing the necessary classes from the Transformers library, specifically GP2LM head model and GP2 tokenizer. After that, we'll load the pre-trained model and tokenizer by specifying the model name, which is set as GP2. The tokenizer will take care of converting our textual prompt into a format that the model can understand, transforming it into tensors suitable for input. All right? Next, we define a prompt that serves as the starting point for our text generation, something like, "Once upon a time in a land far away." We then pass this prompt through the tokenizer, encoding it into the required tensor format. The critical point here is utilizing the generate function, where we specify the maximum length for the output and how many sequences we want to return. After invoking this function, we get our generated outputs, but hang on, these are still in tensor format. To make the generated text readable, we need to decode the first output tensor back into a human-readable format using the tokenizer. Finally, we print the resulting text, which showcases the coherent continuation of the narrative initiated by our prompt. This way, we can observe how GP2 constructs sentences that align beautifully with the context provided. In satisfaction. Generative models hold transformative potential in various industries, and the more we explore them, the more fascinating applications we uncover. They can revolutionize the way we think about data, decision-making, and creativity. It's pretty incredible, right? As you've seen from the code examples, implementing these models is accessible, and honestly, they can yield some really impressive results. So let's wrap this up. In conclusion, generative models are not just about creating new samples. They encapsulate a broader vision of understanding and recreating the world around us, driven by data and patterns. Whether it's visual art, music, or even natural language, these models empower both creators and scientists alike. As technology keeps evolving, I can tell you, those who harness the power of generative modeling will surely be at the forefront of innovations that reshape our daily lives. So let's keep exploring this exciting field, unraveling new possibilities with every line of code we write. Deep learning has significantly transformed the landscape of generative modeling, opening up new horizons for innovation across various fields. Today, we will delve into the applications of deep learning in generative modeling, specifically focusing on powerful techniques like variational autoencoders, or VAEs for short, and how they utilize random numbers to generate complex and realistic data samples. So far, we've learned about generative models, which are fascinating tools in artificial intelligence and machine learning that enable the creation of new data that resembles existing datasets. We've explored how these models function, particularly highlighting generative adversarial networks, yes, those GANs that you've probably heard about, and variational autoencoders. They each generate images and data through their unique processes. We also touched on their applications in natural language processing, such as utilizing the GPT-2 model to generate coherent text based on prompts. Overall, generative models open up exciting avenues for creativity, data augmentation, and automation across various fields. Now, we will cover several applications of deep learning within generative modeling, spotlighting how VAEs can efficiently create realistic images and complex data structures. Along the way, we'll even look at some coding examples to see these concepts in action. So let's jump right in and discover how deep learning continues to push the boundaries of what's possible in generative modeling. The included figure, titled Applications of Deep Learning in Generative Modeling, presents a pie chart breaking down 5 application areas with their respective shares. So we see variational autoencoders, or VAEs, taking the largest slice at 30%, followed closely by generative adversarial networks, or GANs, at 25%. Then we have text generation, like GPT, contributing 20%, while image generation, such as Midjourney, accounts for 15%, and data augmentation rounds out the chart with 10%. Now, some key patterns really pop out here. VAEs represent the largest share, which shows us a notable emphasis on those latent variable methods in the applications surveyed. GANs coming in second highlights their ongoing importance for high-fidelity generation tasks. When we combine the shares of text and image generation, it accounts for a solid 35% of the whole distribution. This tells us that generative modeling is making serious strides across both text and images. I mean, text generation alone is a substantial portion, reflecting just how rapidly those transformer-based language models are being adopted. Now, data augmentation, although it's the smallest slice at just 10%, is still an essential application that supports downstream supervised learning. So when we look at these proportions, we can conclude that the field relies on a combination of complementary techniques. The latent variable models like VAEs and adversarial approaches, such as GANs, are dominating. Plus, sequence and multimodal generation are playing major roles, while practical uses like augmentation remain critical for bolstering real-world datasets. What this distribution suggests is that practitioners should really consider both the task requirements and the unique strengths of each approach when choosing a generative method. Generative modeling primarily serves the purpose of creating samples from learned distributions, which can be both intriguing and useful. Let's focus on variational autoencoders, or VAEs, which have really caught on thanks to their ability to generate diverse and high-quality data. So, what exactly are VAEs? Well, they take a fresh approach by mixing neural networks with variational inference, a powerful statistical technique that helps us approximate complex distributions. Now, the architecture of a VAE consists of two main parts, the encoder and the decoder. The encoder compresses the input data into what we call a latent space, capturing the essential features of that data while throwing away the unnecessary noise. Then the decoder comes into play. It takes samples from this latent space and reconstructs the original input. Pretty cool, right? By doing this, the model learns to generate new data points that resemble the training data. All right, let's illustrate this with some code. Now, let's implement the encoder and decoder for our variational autoencoder, or VAE. First, we'll start with the encoder class, which is really quite fascinating, as it takes a flattened image. Typically, that's a vector of size 784, representing a 28 by 28 image, and it maps that through a fully connected layer to create two outputs, the mean and log variance of the latent space. This step is crucial because these two parameters, mean and log variance, actually define the distribution from which we're going to sample during the generation process. To add a bit of complexity here, we use the ReLU activation function in the forward method, which helps introduce nonlinearity, allowing our model to learn more intricate representations. Now, moving on to the decoder class, this part's designed to reconstruct the original image from the latent representation that we sampled from the encoder. It's similar to the encoder, but it works in reverse, expanding the latent representation back to its original shape using fully connected layers. And we come to the last layer, which employs a sigmoid activation function. This is really important because it ensures that our output pixel values are nicely constrained between 0 and 1, making it perfect for handling our binary data like the MNIST images we often work with. With this setup, we're establishing a robust framework for learning effective encodings and performing data reconstructions, both of which are essential for generative modeling. Now let's implement the core variational autoencoder, or VAE model, which effectively combines our previously defined encoder and decoder. In this implementation, we inherit from nn.module, allowing us to utilize all those awesome functionalities provided by PyTorch. The __init_ method is where we initialize the VAE class. And here, we instantiate both the encoder and decoder as its components. Next, we need to introduce the reparameterization trick through the reparameterize method. This technique is really crucial, as it enables us to generate samples from the learned latent space while still preserving the ability to compute gradients for backpropagation. So, this method takes the mean, or mu, and the log variance, or log var, that our encoder produces, calculates the standard deviation, and samples from it using a random tensor. What we get out of this is a latent representation of our input. Now, let's go ahead and see how we can implement the forward method, which processes an input tensor, x. The method starts by calling our encoder to obtain the mean and log variance. Using these, we then apply the reparameterization trick to get our latent variable, z, which is then passed off to the decoder. This allows us to generate the reconstructed output alongside the latent variables we use for loss computation. This structured flow we've built enables effective learning and the generation of data samples. Next, we will define the loss function that is crucial for training our variational autoencoder, or VAE. This function brings together two essential components, the reconstruction loss and the Kullback Leibler, or KL divergence. So, let's break it down. The reconstruction loss is computed using binary cross-entropy, which essentially compares the output generated by our decoder to the original input. This loss helps us gauge how well our decoder is doing in terms of, accurately reproducing those input images. Now, alongside this, we also calculate the KL divergence, which is really important. This component regularizes our model by making sure that the distribution we learn within the latent space closely matches a standard normal distribution. We achieve this by applying a penalty that considers how much the learned mean and variance deviate from the expected values. Finally, we combine both losses, which gives us a comprehensive measure that encourages our model to not only reconstruct effectively, but also to learn a meaningful latent representation. By optimizing this loss function during training, we steer the VAE toward generating coherent, realistic data samples. Now, let's implement the training loop for our VAE model. First, we set up the training parameters, which include batch size, learning rate, and the number of epochs. After that, we define a transformation for our MNIST dataset to ensure the images are converted to tensors and normalized properly. We load the training dataset using PyTorch's dataset utilities, and then we create a data loader to help with batch-wise processing during training. Next, we initialize an instance of our VAE model and set up the Atom Optimizer with the model parameters. In the training loop, we iterate through each epoch and make sure to set the model to training mode. For every batch of training data, we first reset the gradients of the optimizer to prevent any unwanted accumulation. We then pass the batch through the model, and it returns the reconstructed images along with the means and log variances of the latent variables. The loss function, which includes both reconstruction loss and KL divergence, is computed, guiding us in how well the model can generate outputs that resemble the original inputs. We backpropagate this calculated loss, updating the model's weights based on the gradients. After each epoch, we print the loss value to monitor the model's performance over time. This allows us to observe its learning curve and effectiveness in minimizing the loss. Now, let's implement a function that will allow us to generate new images from our trained variational autoencoder, or VAE. This function, generateImages, takes in two inputs, the model and the number of samples you want to create. First off, we need to set the model to evaluation mode, which we can do with model.eval, ensuring that any dropout or batch normalization layers behave properly during this inference step. Next, we're going to use torch.noGrad to turn off gradient calculations. This speeds things up since we don't need those gradients when generating new images. Now, within this block, we'll sample random points from a standard normal distribution. We do this using torch.rand, and we create a tensor called z that represents our latent space. The dimensions of this tensor will match the number of images we want to generate, with each point having a dimensionality of 20, which aligns with our VAE's latent space. After that, we'll pass these random samples through the decoder to create new images. Finally, we reshape the output so that it matches the original image dimensions of 1 channel by 28 by 28 pixels, which is perfect for the MNIST dataset. So, by calling this function and providing the model along with the number of desired samples, we can get a fresh set of images that showcase the model's ability to create new variations inspired by the training data. The applications of VAEs extend far beyond mere image generation, and it's fascinating to see how versatile they can be. They can be utilized in various domains, including medical imaging, where they can generate synthetic medical images, which is so cool, to augment datasets for training purposes. VAEs are also instrumental in anomaly detection. They enable us to identify those abnormal data points that deviate from normal patterns, which is really crucial in many applications. Moreover, they facilitate smooth transitions in latent space. This allows features like interpolation between different data samples, helping us gain insights into the relationships within the data. It's a really powerful concept. Now, consider leveraging VAEs to generate new samples for training machine learning models, especially when real-world data is scarce or, let's face it, pretty expensive to collect. By synthesizing these realistic data points, we can create robust datasets that bolster our model's performance, ensuring they maintain accuracy even when they're in deployment or production. This capability can really make a difference in how our models perform in real-world scenarios, don't you think? As we wrap up our exploration into the applications of deep learning and generative modeling, specifically with VAEs, it's clear that these innovations have opened exciting possibilities across numerous fields. The ability to generate new and realistic samples holds promise for advancing research, creativity, and efficiency. We've demonstrated how VAEs work alongside some hands-on coding examples, illustrating how to implement them from scratch and generate unique outputs based on learned data distributions. Now, deep learning techniques like VAEs aren't just theoretical exercises. They offer practical, impactful solutions to real-world challenges. So, whether you're a programmer, a data scientist, or an artist looking to enhance your creative process with AI, generative models are definitely poised to play an essential role in shaping the future. The journey doesn't stop here. As you continue to explore the captivating intersection of deep learning and generative modeling, there are endless possibilities just waiting to be uncovered. So keep that curiosity alive. Generative models have revolutionized artificial intelligence, enabling machines to create new data that's sometimes indistinguishable from real-world examples. Today, we're going to dive into the implementation of deep learning generative models, focusing on how deep neural networks effectively capture complex variations in data, like images and language. So far, we've explored the transformative impact of deep learning on generative modeling, particularly through techniques like variational autoencoders, or VAEs, and generative adversarial networks, known as GANs. We've seen how VAEs generate realistic data by encoding and decoding inputs, illustrated with practical coding examples that hopefully made things clearer for you. Plus, we've discussed the diverse applications of VAEs in fields like medical imaging and anomaly detection, showcasing their versatility. Overall, these generative models present exciting opportunities for creativity and innovation across various domains. Now, let's roll up our sleeves and cover how to implement these models in a practical setting, specifically using Python and PyTorch. So, let's get started. Now, let's implement the generator and discriminator models for our GAN. First, we'll create the generator class, which is responsible for generating synthetic images from a random noise vector. The generator uses a sequential model made up of multiple linear layers with ReLU activation functions, helping it to learn those complex patterns in the data. At the final layer, we apply the tan activation function to ensure that the output pixel values of the generated images fall within the range of -1 to 1, which is really important for proper image scaling. Next up, we define the discriminator class, which evaluates images and classifies them as either real or fake. This model has a similar structure, with several linear layers mixed in with Lie-ReLU activations, allowing for better gradient flow during training. The final sigmoid layer gives us a probability indicating whether the image is authentic. With both the generator and discriminator models in place, we can now effectively train these networks in an adversarial way. This back and forth helps them enhance each other's performance iteratively, leading to the creation of those high-quality synthetic images. Isn't that pretty cool? The figure displays two grouped sets of bars that summarize model-level performance and task-specific effectiveness. On the left axis, we've got model performance scores. GAN sits at 90%, while VAE holds 85%. This shows that GAN enjoys a modest advantage of about 5 percentage points in our chosen performance metric. Now, both these models are performing at a high level, indicating strong overall capability. On the right axis, we see application effectiveness scores, which show image generation at 75% and anomaly detection at 65%. Here, that 10-point gap emphasizes that these models are relatively more effective for image generation tasks compared to anomaly detection in this context. So it makes two clear points. First, while GANs have that slight edge in raw model performance, especially relevant for producing realistic images, VAEs remain competitive. And second, we see that application-level effectiveness is lower than model performance percentages, meaning that just because a model scores high doesn't mean it'll perform equally well across all downstream tasks. From these patterns, we can conclude that for tasks prioritizing visual realism, like image generation, the GAN is the stronger candidate. Thoughtful pause. However, for tasks that require structured latent representations or probabilistic reasoning, like anomaly detection, the VAE still shows utility, even with lower application effectiveness. This really suggests that when choosing a generative model for a specific application, practitioners should carefully weigh both the reported model performance and the task-specific effectiveness. Next, we will implement the training loop for our GAN, which will involve several key steps to maximize the performance of both the generator and discriminator networks. First, let's load the MNIST dataset and apply some necessary transformations, like normalizing the pixel values. This step is important to improve training stability. Now, after loading the dataset, we'll initialize both our generator and discriminator instances. It's crucial to set up the loss function. In this case, we'll use binary cross-entropy. This helps measure how well the generator is at fooling the discriminator, and vice versa. We also need to configure optimizers for both networks using the Atom algorithm, along with setting learning rates and momentum values to facilitate effective training. Now, here's where it gets exciting. Inside our core training loop, we iterate through the dataset for a specified number of epochs. In each epoch, we'll process batches of real images and create labels for both real and fake images to aid in the training process. First, we start by training the discriminator with a mixed batch of real and generated images. This helps continuously enhance its ability to tell the difference. Then, we train the generator, aiming to optimize its output so that the discriminator mistakenly identifies the generated images as real. After each epoch, we'll print the loss values for both models, providing us with insights into their learning progress throughout the training process. This feedback loop is essential. It lets us know how well our networks are learning. Now that we've trained our GAN, it's time to visualize the generator's progress. Next, we'll write a function to generate and save images during training. In this function, we start by creating a random input noise vector, z, using a normal distribution. This vector serves as the input to our generator, which means it produces synthetic images. After generating these images, we reshape them for proper display and then use the makeGrid function to arrange them in a nice grid format. Normalizing the images ensures they're in a suitable range for visual representation. We'll even add a title indicating the current epoch number, and to keep things tidy, we'll disable the axis for a cleaner view. Finally, the generated grid of images is saved to a file with a unique name for each epoch, allowing us to track the evolution of image quality over time. To utilize this function effectively, we will invoke it at specific intervals in our training loop, specifically after every 10 epochs. This ensures that we capture the progression of the generator in producing realistic images as training advances. This monitoring is crucial for assessing the effectiveness of our GAN. Now, let's implement a simple variational autoencoder, or VAE, in PyTorch for image data using the MNIST dataset. First, we need to define the VAE class. This will inherit from PyTorch's nn.module. In the constructor, we'll set up our encoder and decoder architectures. The encoder has a linear layer that brings down the input size from 784, which is what we get from 28 by 28 images, all the way down to 400. Next, we apply a ReLU activation function. After that, we have two separate linear layers, one to compute the mean and another for the log variance of our latent distribution. Both of these layers compress our data down to a size of 20. That defines our latent space. Now, we move on to implementing some key methods: encode, reparameterize, decode, and forward. The encode method takes the input and produces the mean and log variance from the encoder. Then comes the reparameterize method, which samples from the latent space using the mean and log variance. This is crucial as it allows gradients to flow during training. So, we get our decoded samples in the decode method, which works to reconstruct the original input from those sampled latent values. And finally, the forward method ties it all together, orchestrating the encoding and decoding process. It produces both the reconstructed data and the latent variables, which are essential for loss calculation during training. There you have it. That's our foundation for a variational autoencoder. Now, let's implement the training loop for our variational autoencoder, or VAE. First, we'll load the MNIST dataset using a data loader. This allows for efficient batch processing by shuffling the data and setting a batch size of 64. Next, we initialize our VAE model and set up the Atom Optimizer, which will help us adjust the model parameters as we train. In the training loop, we define the number of epochs we want to iterate through and begin processing each batch of real images. For every batch, we reshape the images into a vector format that's suitable for our network. Now, to prevent the optimizer from carrying over gradients from the previous iteration, we first zero the gradients. Then, we execute the forward pass, generating reconstructed images along with the mean and log variance of the latent variables. We compute the reconstruction loss using binary cross-entropy, ensuring our model learns to recreate the original images accurately. Additionally, we calculate the KL divergence to regularize the latent space, nudging it towards a standard Gaussian distribution. Now, the total loss is simply the sum of these two components. This total loss is what we use to perform backpropagation, updating the network's weights. After each epoch, we print out the loss to monitor our training progress, allowing us to see just how well the VAE is learning to generate data that's consistent with the original dataset. It's quite exciting to watch this all unfold. Now, let's implement the function that will visualize the reconstructed images generated by our trained variational autoencoder, or VAE for short. This function is called Visualize Reconstructed Images. It begins by disabling gradient calculations. Why? Well, this helps us generate samples efficiently without impacting our model parameters. Next, we create a random latent vector, which we'll call z. This serves as the input to our decoder. With this setup, we're going to generate a specified number of images. Why do we do this? It allows us to see how well our VAE has learned to replicate the input distribution. Once we have those generated images, they need to be reshaped to match the original input dimensions. We then arrange them into a grid using the makeGrid function. This arrangement makes visual comparison much easier. After that, we utilize plt.imshow to display this grid. We also configure the titles and axes for clarity, of course. This entire visualization process makes it much easier to evaluate how effective our model is in capturing the various features of the data. So, by calling this function after training, you can see firsthand the results of your VAE's ability to generate new data samples. This will really help you understand how well your model is performing, as well as the quality of the output images. In conclusion, the implementation of deep learning generative models like GANs and VAEs really invites us to explore creative data generation. Whether we're synthesizing new images or uncovering complex data distributions, these models open up a world of possibilities. From art to medicine, you name it. Today, we've walked through how deep neural networks serve as the backbone for these generative models. We took a closer look at GANs, these remarkable adversarial networks that push their components to improve simultaneously, which is just fascinating. Then we pivoted to VAEs, where we emphasized probabilistic encoding and sampling within their architecture. And don't forget, by implementing practical examples in Python using PyTorch, we're really setting ourselves up to carry these techniques into real-world applications. As we continue our journey in this domain, there's still so much more to explore. We can dive into advanced techniques and tackle areas like conditional generation and monitoring model performance. So stay curious, keep experimenting with these tools, and remember, the only limit is your creativity. In this lesson, we're diving into the fascinating applications of generative models in natural language processing. Generative models have reshaped how we understand and generate text data, paving the way for tasks once thought to be uniquely human, like writing essays, producing poetry, and even engaging in conversations. So far, we've explored deep learning generative models, particularly generative adversarial networks, or GANs, and variational autoencoders, known as VAEs. We examined their architecture and training processes, implementing them in Python using PyTorch, and discussed their effectiveness in generating realistic data. We even visualized generated images and explored the unique capabilities of each model for different applications. This journey into generative modeling has really set the stage for our further exploration of advanced techniques and their applications. Now, let's talk about how these powerful tools are applied to natural language processing, especially highlighting the impact of models like transformers and BERT. Generative models in NLP have significantly changed the landscape of how machines understand and produce human language. And at the heart of this transformation are advanced architectures like the transformer model. Introduced in the paper "Attention is All You Need," the transformer brought forth the attention mechanism, which allows for better context retention and understanding across long texts. With the transformer, sequential data can indeed be processed in parallel, enabling faster training and more efficient handling of extensive datasets, a real game changer compared to earlier architectures like RNNs, those recurrent neural networks. The displayed pie chart, titled Performance of Generative Models in Natural Language Processing Applications, presents 4 application categories with hypothetical performance scores. text generation at 95%, dialogue systems at 90%, sentiment analysis at 85%, and summarization at 80%. So, what can we conclude from these proportions? Well, first off, text generation takes the largest slice of the pie. This indicates that generative models excel in producing fluent, coherent text and creative content. Right behind it, we have dialogue systems, which suggests that these models are also highly capable of maintaining context and delivering interactive conversational responses. This high score, you might notice, implies their suitability for applications like chatbots and conversational AI, after some fine-tuning, of course. Now, let's talk about sentiment analysis. While it's typically seen as a discriminative task, it still shows strong performance, reflecting that generative architectures can be effectively adapted for classification-style outputs or even as feature-rich encoders that feed downstream classifiers. And summarization? Well, it takes the smallest share at 80%, hinting that condensing and abstracting content is comparatively more challenging for generative models. Often, this requires specialized training objectives or hybrid extractive-abstractive approaches. Overall, this pattern paints a clear picture. Effectiveness runs from open-ended text production toward tasks demanding precise compression or classification. So, when you're making practical choices, prioritize generative approaches for creative and interactive tasks. And for those areas where performance lags, like summarization, don't forget to plan some additional task-specific strategies, okay? Think data curation, objective engineering, and evaluation metrics, like Rouge and Blue, along with human evaluations, to really fine-tune your approach. Now, let's dive into implementing a self-attention mechanism in our transformer model using Python and PyTorch. We'll kick things off by defining a class called self-attention, which, by the way, inherits from nn.module. In the constructor method, we'll initialize some essential parameters, like the embedding size and the number of attention heads. It's important to check that the embedding size is divisible by the number of heads. Why? Well, this ensures the proper functionality of multi-head attention. Now, moving on to the forward method, we'll process the input tensor, pulling out the batch size and sequence length as we create the necessary representations for values, keys, and queries through linear transformations. After that, we reshape these representations for multi-head processing and permute them to fit the required dimensions. The attention mechanism then computes energy scores by taking the dot product of the queries and keys. We normalize these scores using a softmax function to derive our attention weights. Then, we multiply these attention weights by the values to generate our output for this layer. This enriched output captures the essential information from the input, preparing it for use in subsequent layers of the transformer architecture. And that's how we facilitate the model's ability to efficiently process complex relationships in language. Now, let's see how we can implement a simple transformer model for text generation. The code begins by defining the transformer class, which inherits from nn.module. This is a standard practice in PyTorch for creating neural network models. Inside the constructor, or the _init method, we first create an embedding layer that transforms the input vocabulary into dense vector representations. This layer is super important as it helps the model understand the meanings of words in a continuous space. Next, we instantiate a list of self-attention blocks which we create through a loop that runs for the specified number of layers. This is crucial because each block allows the model to attend to different parts of the input sequence, effectively capturing relationships and dependencies. Finally, after processing through the self-attention layers, the output is fed into a fully connected layer that translates the learned representations into vocabulary probabilities for each word. Now, let's take a look at the forward method, which defines how data flows through the model. When the input passes through the embedding layer, it is then forwarded through each self-attention block sequentially. At the end, the model outputs the predictions, which can be used to generate coherent text when trained on appropriate datasets. Now, let's implement a training loop for our conversational AI model, which will allow the model to learn from the dataset over several epochs. This function, train model, kicks off by setting the model to training mode, preparing it for those important updates. It then iterates through the specified number of epochs, and each epoch represents a complete pass through the dataset. During each epoch, we traverse through the data loader, which feeds input-output pairs to the model. For every batch processed, the optimizer's gradients, listen closely here, are reset to 0 using optimizer.0grad. This step is crucial because we want to ensure that previous gradients do not affect the current updates. Then, the model generates predictions based on the input data. We compute the loss by comparing these predictions with the actual targets, reshaping them appropriately for the criterion we're using. After that, we backpropagate the loss through the model with loss.backward, updating the weights based on how well the model performed. And finally, the optimizer applies those calculated gradients, effectively tuning the model's parameters. Throughout this process, we keep an eye on things by printing the current epoch along with the loss, which lets us monitor the model's learning progress. Once we've defined all the necessary components, we just call this function with our transformer model and other parameters, and voila! The training process is initiated. Now, let's see how we can implement a text summarization algorithm using a pre-trained BART model, which, believe me, is known for its effectiveness in generating concise summaries from longer texts. First, we're going to start by importing the necessary components from the Hugging Face Transformers library. We'll specifically need the BART for conditional generation model and the BART tokenizer. The tokenizer, it's essential for converting input text into a format that the model understands, whereas the BART model is equipped to generate those summaries we want. Now, let's initialize the tokenizer and model with the pre-trained weights from Facebook/BART large CNN, which is, you guessed it, designed for summarization tasks. All right, we're going to define a function called summarizeText right now, where we encode our input text prefixed with summarize. This step is crucial as it guides the model on what task we want it to perform. The function specifies settings like max length and truncation. This ensures our input fits perfectly within the model's capacity. Then, with these encoded inputs, we invoke the model's generate method, which produces summary IDs that reflect the condensed version of the input. Finally, we decode these generated IDs back into readable text, stripping away any special tokens as we go, and return that summary. This succinct approach, I promise, drastically simplifies complex NLP tasks, allowing developers like us to focus on building applications rather than getting lost in the intricacies of model training. As we continue exploring the vast capabilities of generative models in natural language processing, we should also consider their applications in creative writing, automated storytelling, and content creation. Tools like AI Dungeon utilize these generative models to craft narratives based on user inputs, dynamically generating plot lines and providing tailored storytelling experiences. This creativity is fueled by the underlying transformers, which enable the AI to maintain consistent story arcs grounded in context. However, ethical considerations are paramount as we leverage these powerful models. While promoting the use of generative models to create compelling narratives, we must remain vigilant about how this technology shapes discourse and the potential for misinformation or biased representations in the content produced. Proper monitoring and responsible deployment of these tools are vital to ensure that they serve a constructive purpose. In summary, generative models have opened the door to innovative applications in natural language processing, impacting everything from chatbots to creative writing. With the power of transformer architectures and the functionality of pre-trained models like BERT and BART, we can harness the ability to generate meaningful text autonomously. The journey through generative models has truly transformed our interactions with machines, making language a domain ripe for exploration and limitless potential. So I encourage you to continue experimenting with these models. Dive into the realms of NLP and see where your creativity takes you. With every step you take in your learning journey, you're contributing to the interplay between human thought and machine-generated insights, paving the way for future advancements in language and beyond.
Generating diverse images is a fascinating topic in the realm of generative models and machine learning. Today, we'll explore how we can map random numbers, those seemingly chaotic entities, into a structured set of artificial images using a latent vector. So far, we learned about how generative models have transformed natural language processing, leveraging architectures like transformers to produce coherent text. Now we will cover the creation of diverse images through manipulations of data in a latent space. Now let's explore how to set up our Python environment and generate a latent vector. First, we need to ensure that we have PyTorch and TorchVision installed in our system. This can be done through a simple pip command, which will download and set up these essential libraries. Once our environment is ready, we import the Torch library, and to maintain consistency in our results, we set a fixed random seed using Torch manual seed 42. This step is crucial for reproducibility, as it ensures that the random numbers generated will be the same each time we run the code. Next, we generate a latent vector using torch random1 100. This function creates a tensor filled with random numbers sampled from a standard normal distribution, yielding a unique representation for our image generation task. The size of the vector in this case is set to 100, which means it will serve as the input to our image generation model. Finally, we print the latent vector to the console, providing us with the initial foundation upon which we can build our image generation process. Each execution of this code will provide a different latent vector, highlighting the role of randomness in the creation of diverse images. The figure titled Diverse Image Generation from Latent Vectors presents a scatter plot that maps sampled latent vector values on the x-axis against image quality scores on the y-axis for 100 points. Visually, the points are broadly dispersed across the full range of both axes, and there is no clear linear or monotonic trend connecting latent value magnitude to image quality. High-quality scores and low-quality scores appear at many different positions along the latent value axis. This widespread dispersion implies that, for these raw samples, the latent coordinate alone does not reliably predict output quality. The plot also shows small local concentrations of points reflecting sampling variability, but these do not form a consistent pattern that would allow simple rules, e.g., increase latent value to improve quality. From this visualization, we can conclude that turning random latent vectors into consistently high-quality images requires learning or structuring the latent space, for example, via training, conditioning, or supervised mapping, rather than relying on unstructured random sampling. The grid and labeled axes help identify where points concentrate and where interventions might be targeted to steer generation toward desirable quality regions. Now let's implement a simple feed-forward neural network that will allow us to generate images from our latent vector. We begin by defining a class called SimpleImageGenerator, which inherits from NN module, a base class for all neural network modules in PyTorch. Within the constructor, we initialize 4 fully connected layers. The first layer takes the latent vector of size 100 and expands it to 256 dimensions. Each subsequent layer progressively increases the dimensionality, from 256 to 512, then 512 to 1024, and finally, the last layer outputs a tensor that corresponds to the size of an RGB image, 3 color channels of 64x64 pixels. Next, we implement the forward method, which defines the forward pass of the network. In this method, we apply the RayLU activation function to the outputs of the first 3 layers to introduce nonlinearity. The output of the final layer is passed through the tan activation function, ensuring the pixel values are scaled between -1 and 1, which is essential for image generation. Finally, the output tensor is reshaped to the format required for the image, specifically into a shape of 1, 3, 64, 64, representing a single image with 3 color channels. With this setup, we can now create an instance of the generator and generate an image from our latent vector. Now let's see how we can visualize the generated images using Matplotlib. First, we import the necessary libraries, Matplotlib for plotting the images and NumPy for handling numerical operations. We define a function called showImage that takes a tensor representing the generated image. Inside this function, we first convert the tensor to a NumPy array using detach, numpy, which allows us to manipulate the data outside the PyTorch framework. Next, we rescale the pixel values from the range of -1, 1 to 0, 1 to fit the standard visualization requirements. This is achieved by the formula image plus 1/2. Following the rescaling, we rearrange the array dimensions from CX-HXW, where C is channels, H is height, and W is width, to HXWXC, which is the order expected by Matplotlib for displaying images. Finally, we use PLT, imShow, to render the first image in the batch, disable the axis for a cleaner look, and then call PLT show to display the image. This process allows us to see what the model has generated from the random latent vectors effectively, showcasing the diversity of outputs as we iterate through different latent inputs. Next, we will write the following code to prepare our CIFAR10 dataset for training. We begin by importing necessary libraries like transforms from TorchVision to handle the image transformations, and CIFAR10 for accessing the dataset itself, along with data loader for batching the data. Now let's implement image transformations that include converting images to tensors and normalizing them. The normalization scales the pixel values to a range suitable for neural network training, specifically shifting them to have a mean of 0 and a standard deviation of 1, which helps with convergence during training. After setting up the transformation pipeline, we load the CIFAR10 dataset from the specified root directory, enabling the option to download it if not already present. This dataset contains 60,000 images in 10 different classes, providing a rich variety of visual data for our model to learn from. We then create a data loader instance with a batch size of 64 and enable shuffling, which randomly orders the images in each epoch, ensuring diverse samples are presented to the model during training. This step is crucial for improving the generalization capability of our generator. Next, we will implement the training loop that enables our generator to learn from the CIFAR10 dataset over multiple epochs. First, we define the loss function using binary cross-entropy loss, which is suitable for our task of differentiating between real and fake images. We also set up an atom optimizer tailored for the generator's parameters, which will facilitate the learning process. Now let's see how we can structure the training function. Within the loop, we iterate over the dataset for the specified number of epochs. For each batch of real images, we create random latent vectors, which the generator will transform into fake images. We then compute the loss for both the real images and the generated images. The real images are expected to produce labels of 1s, while the generated images should yield 0s, indicating they are not real. Next, we perform backpropagation by resetting the optimizer, calculating the total loss from both the real and fake images, and calling backward on the loss to compute the gradients. The optimizer then updates the generator's parameters. During each iteration, we output the total loss, allowing us to track the generator's learning progress. This loop embodies the essence of adversarial training, where the generator continuously improves its skills based on the feedback from the discriminator. Now let's implement the code to visualize the unique images generated by our trained generator. We start by defining a loop that will run 5 times, corresponding to the 5 images we want to create. Within each iteration, we generate a random latent vector using tortrandom, which produces a one-dimensional tensor filled with random values. This vector serves as the input to our generator, which has been trained to transform such latent vectors into realistic images. After generating the image, we need to visualize it, which brings us to the showImage function. This function converts the output tensor into a numpy array, rescaling the pixel values from the range of -1, 1 to 0, 1 to ensure it fits the standard format expected by visualization libraries. By changing the tensor dimensions, we prepare it for display and then use Matplotlib to plot the image, turning our latent vector's randomness into a visual masterpiece. Each execution of this code snippet will yield a different image, showcasing the model's learned representation of the CIFAR10 dataset, illustrating the creativity inherent in generative models. To wrap up our exploration of generating diverse images, it's crucial to appreciate the interplay between random latent vectors, neural network architectures, and the training processes that steer model creativity. Through these techniques, we unlocked potential visual outputs from numerical chaos, vividly demonstrating the strength of generative models in image creation. In our journey, we covered the essence of latent vectors, the construction of a basic generator, the importance of datasets, and how to train our model to yield diverse images that reflect learned patterns. The beauty of this work lies not only in the images produced, but in the myriad applications it opens up, from creative art and advertising to scientific visualization and beyond. Don't forget, as we stride into the world of AI, there's always a balance to maintain between innovation and ethical considerations, ensuring that our creations impact society positively. Thank you for joining me today. Keep experimenting, stay curious, and see what unique images you can generate from your latent space. In this lesson, we will explore the powerful concept of data augmentation using generative models. By leveraging these models, we can enhance the capabilities of small datasets by creating additional examples, which can, in turn, improve the performance of discriminative models. So far, we learned about generating diverse images using generative models, particularly through the manipulation of latent vectors in a structured latent space. We explored how random numbers transform into images by utilizing a simple feed-forward neural network and the importance of training the model with a dataset like CIFAR10. The training process involves a generator learning to create realistic images by receiving feedback from a discriminator. Ultimately, we've grasped the interplay between random vectors and neural networks in producing unique visual outputs. Now, we will dive into the fascinating world of data augmentation, which helps overcome the problem of having small datasets and how generative models can significantly assist in this regard. Data augmentation is an effective technique used in machine learning to artificially expand the size and diversity of a training dataset by providing modified versions of the existing data. This approach is especially crucial in domains where gathering more data is expensive or time-consuming. Instead of simply replicating the existing data, data augmentation introduces variations that can lead to better generalization in machine learning models. In this tutorial, we will show how generative models, such as variational autoencoders, VAEs, and generative adversarial networks, GANs, can create new examples and augment our datasets. Now let's implement the variational autoencoder, VAE, in PyTorch, starting with the class definition. The VAE class inherits from NN module, encapsulating the architecture needed for our model. In the init method, we define both the encoder and decoder components. The encoder consists of a sequential stack of layers that compress the input dimensions into a lower dimensional latent space, producing outputs for the mean and logarithm of the variance. This compression is critical for our model to learn meaningful representations of the data. Next, we implement the encode method, which extracts the encoded mean and log variance from the input data. The reparameterization trick is used in the reparameterize method, allowing us to sample from the latent distribution and introduce the necessary stochasticity for backpropagation. After encoding, the decode method reconstructs the output from the latent vector, ensuring that the reconstructed values stay within the appropriate range by applying a sigmoid function at the output layer. Finally, the forward method integrates these components into the flow of the model. It reshapes input data to match the expected dimensions, encodes it, samples from the distribution, and then decodes it back into image space, making it ready for training. Next, we will implement the loss function for our variational autoencoder, VAE, which combines two essential components, the reconstruction loss and the callback labeler divergence. The reconstruction loss, computed using binary cross-entropy, measures how well the reconstructed output matches the original input, which is crucial for ensuring that the VAE accurately captures the characteristics of the training data. To achieve this, we reshape the input tensor to ensure it aligns with the expected dimensions for binary cross-entropy calculation. Simultaneously, the callback labeler divergence serves as a regularization term, enforcing the learned latent space distribution to approximate a standard normal distribution. This step not only guides the model towards a more structured latent space, but also prevents overfitting by encouraging generalization. By summing the two losses, we obtain the total loss that will be minimized during the training process. This composite loss will play a pivotal role in steering the VAE's learning, ultimately enabling it to generate variations of the data effectively while maintaining a coherent structure in the latent space. Now let's implement the training loop for our variational autoencoder, VAE, using the MNIST dataset. First, we load the dataset and set up a data loader, which allows us to easily access batches of images during training. The batch size is set to 128, with random shuffling to enhance the model's generalization. Next, we initialize the VAE with specified dimensions for the input and latent space, along with an atom optimizer to update the model weights effectively. We then enter the training loop, which will execute for 10 epochs. For each epoch, we iterate through the data loader, processing each batch of images. Before performing any updates to the model, we zero out the gradients to prevent accumulation from previous iterations. As we pass our data through the VAE, we obtain the reconstructed images along with two parameters, the mean and logarithm of variance from the encoder. Subsequently, we compute the loss using the defined loss function, which consists of reconstruction loss and the Kullback labeler divergence. After calculating the loss, we perform backpropagation to update the weights of the model. At the end of each epoch, we print the current loss value, allowing us to monitor the training progress and adjust parameters if necessary for improved performance. Now let's implement the code to generate new samples from the trained variational autoencoder, VAE. In this section, we begin by ensuring that gradients are not calculated, allowing us to generate samples efficiently without updating any model parameters. We create latent space samples using random normal values with a shape of 64 by 20, matching the latent space dimensionality of our VAE. After generating these latent samples, we use the decoder to reconstruct them back into the original data space, formatting them into a shape suitable for visualization as images. Next, we prepare to visualize the generated samples using Matplotlib. We set up a grid of subplots, arranging the output in an 8x8 format to display 64 images neatly. For each generated sample, we visualize the output while ensuring that unnecessary axes are removed for clarity. Finally, we invoke the plt show function to display the grid of generated images. This demonstration enables us to appreciate the varying outputs produced by the VAE, illustrating the model's ability to create different yet realistic variations that augment our dataset effectively. The displayed figure is a bar chart titled Data Augmentation through Generative Models that compares the number of generated samples produced by three classes of generative models: variational autoencoders, generative adversarial networks, and transformers. Each bar is labeled with its exact value on top: variational autoencoders at 150, generative adversarial networks at 200, and transformers at 300. Visually, the transformer bar is the tallest, about twice the height of the VAE bar and 1.5 times the height of the GAN bar, indicating the largest number of generated samples in this simulation. The bars are color-coded, a blue for VAEs, an orange for GANs, and a pink for transformers. The x-axis lists the model types, and the y-axis indicates the number of generated samples with a dashed horizontal grid for reference. From these values and relative heights, we can conclude that in this scenario, transformers are shown producing the most synthetic examples, 300, GANs an intermediate amount, 200, and VAEs the fewest, 150. Interpreting this for data augmentation practice suggests that the quantity of generated samples varies considerably across model families, and that choices about augmentation should consider both the number of synthetic examples available and the downstream requirements for dataset size. Next, we will write the following classes to define the generator and discriminator for our generative adversarial network, GAN. The generator class takes random noise as input and transforms it into synthetic images using a sequential neural network. Within its init method, we first specify the dimensions for the input and output, initializing a series of linear layers interspersed with ray-LU activations, concluding with a tan activation function to ensure the output falls within the desired pixel value range. Now let's take a look at the discriminator class, which is responsible for distinguishing between real and generated images. Similar to the generator, it employs a sequential model consisting of linear layers paired with leaky ReLU activations. This choice is pivotal for combating the issue of dead neurons during training, enhancing gradient flow. The last layer employs a sigmoid activation function to output probabilities that indicate whether an image is real or fake. With the architectures defined, we can facilitate the generator's learning by initializing the optimizer and defining the loss function. The generator aims to maximize the discriminator's errors, while the discriminator works to minimize them, effectively training both models in an adversarial manner. Now let's define the loss functions and optimizers for the GAN. In this section, we will use binary cross-entropy as our loss function, which is appropriate for the binary classification task the discriminator faces, distinguishing real images from generated ones. Next, we will initialize our optimizers using the Atom algorithm for both the generator and the discriminator, ensuring they each have the same learning rate of 0.0002 to facilitate effective training. Now let's implement the training loop for our GAN. We will train for 30 epochs, iterating over batches of real images retrieved from the data loader. During each iteration, we first optimize the discriminator. This involves calculating the loss based on real images, where we assign labels of 1 for real images, and then computing the loss when feeding the discriminator fake images generated by the generator, which receive labels of 0. We accumulate the losses and perform backpropagation to update the discriminator's weights. Subsequently, we will optimize the generator by capturing its performance based on the discriminator's assessment of generated images, seeking to maximize its ability to create convincing data. The process concludes by printing out the losses for both networks at the end of each epoch, allowing us to monitor the performance and improvements of both the generator and discriminator throughout training. Now let's implement the code to generate new images using the trained GAN. We begin by using TorchNoGrad to deactivate gradient tracking, which is unnecessary during inference and helps save memory. We generate random latent noise, which serves as input to the generator. In this case, we create 64 samples of 100-dimensional noise. The generator processes this noise to produce generated images, reshaping them to match the desired output shape, which is typically a 28x28 pixel image. Next, we visualize the output images using Matplotlib. We set up a grid of subplots with 8 rows and 8 columns, creating a figure that is 8 inches by 8 inches in size. For each of the generated images, we display it in the appropriate subplot using the imshow function, ensuring the pixel values are shown in grayscale for clarity. The axes are turned off to provide a cleaner visual presentation. Finally, we call PLT show to render the complete figure, allowing us to see how effectively the GAN has generated diverse samples. This exercise demonstrates GAN's capability for augmenting datasets by creating new and varied data instances that can enhance the performance of discriminative models. In summary, data augmentation is a pivotal technique in machine learning, allowing us to enhance the capabilities of small datasets through the creation of new examples. Variational autoencoders and generative adversarial networks are two powerful types of generative models that help facilitate this augmentation process. By employing these models, we can train more robust discriminative models that generalize better to unseen data. As you explore data augmentation further, try implementing different generative models and experimenting with various datasets. It's an exciting field that combines creativity, technical skill, and a deep understanding of machine learning principles. Remember, the ability to create more data can be a game changer in the quality and accuracy of your models. Thank you for joining me in this exploration of data augmentation using generative models. Keep practicing, stay curious, and happy coding. Generative models are a groundbreaking aspect of artificial intelligence, powering applications from creative content generation to realistic image synthesis. However, implementing these complex models comes with its own set of challenges that developers, data scientists, and researchers must navigate. In this session, we'll dive deep into the hurdles faced when integrating generative models into real-world applications. So far, we learned about the concept of data augmentation using generative models, focusing on variational autoencoders, VAEs, and generative adversarial networks, GANs. We explored how VAEs encode and decode data while learning to create realistic representations, and how GANs produce convincing synthetic examples through an adversarial training process. Additionally, we implemented training loops for both models, resulting in the generation of new data that can enhance small datasets. This foundational understanding positions us for further experimentation with generative models and their applications in improving machine learning performance. Now we will talk about the challenges that arise when implementing these generative models effectively. Now let's see how we can implement a basic generative adversarial network, GAN, using PyTorch. We start by defining two key components of the GAN, the generator and the discriminator. The generator is designed to create synthetic data from random noise. In its architecture, we utilize a sequential model consisting of linear layers followed by activation functions. It transforms input noise into a space of increasing dimensionality, ultimately producing the output in the range of -1 to 1 using the tan activation function. Next, we turn our attention to the discriminator, which serves as the adversary to the generator. It aims to distinguish between real and generated data. Similar to the generator, the discriminator is also constructed using a sequential model with linear layers and Latent activations, which help in maintaining gradient flow during training. The output of the discriminator is a probability score, indicating whether the input data is real or fake. Finally, we instantiate both models. The generator receives a parameter defining the noise dimension, and the discriminator is created without requiring specific initialization parameters. This setup lays the groundwork for training our GAN, where both networks will learn through a competitive process. Now let's implement a simple variational autoencoder, VAE, which is a generative model that can be particularly useful for augmenting our datasets. The VAE consists of two primary components, an encoder and a decoder. The encoder maps input data, such as images, into a latent space representation, while the decoder reconstructs the original data from this representation. In our implementation, the encoder begins by reshaping the input images from a 28 by 28 pixel format into a flat vector. It then processes this vector through a series of linear layers, each followed by a ReLU activation function, before finally compressing the information into a 20-dimensional latent space. This latent space acts as a compact representation of the input data, from which we can sample new data points. The decoder works in the opposite manner. It takes the latent representation and expands it back into the original image size through another sequence of linear layers, culminating in a sigmoid activation that produces pixel values ranging between 0 and 1. With this VAE structure, we can generate new samples by sampling from the latent space and decoding them, thereby enhancing the diversity and quality of our training dataset as we discussed. Now let's implement GPU support to enhance our model training efficiency. First, we check if a CUDA-enabled GPU is available by using the torch CUDA is available function. Depending on this check, we set the device to either CUDA for running on the GPU or CPU if a GPU is not available. Next, we need to make sure our models are utilizing the available hardware. This is crucial as both the generator and discriminator in our GAN, as well as the VAE, need to be moved to the GPU for improved performance. We achieve this by calling the toDevice method on each model. This operation essentially transfers the model's parameters to the specified device, allowing for faster computations during training. Finally, we also prepare a sample input data for testing our models on the GPU. We create random noise with a specific shape, which is typical for GANs, and move this tensor to the GPU as well. This step is vital as it sets the groundwork for our training loop to efficiently utilize the computational power of the GPU, enabling us to train our models faster and more effectively. The displayed bar chart titled Challenges in Implementing Generative Models quantifies 5 key challenges on a severity scale from 1 to 10 and shows their numeric values above each bar. Training complexity 8, dataset quality 7, computational cost 9, debugging 6, and ethical concerns 8. A clear pattern emerges where computational cost is the most severe challenge at 9, indicating that resource requirements and associated expenses outweigh the other issues in magnitude. Training complexity and ethical concerns both register at 8, signaling they are closely pressing issues that demand substantial methodological effort and governance respectively. Dataset quality at 7 is a notable but slightly less acute constraint, implying that while data diversity and volume are important, they are perceived as somewhat more manageable than cost or core training difficulties. debugging is the least severe of the 5 at 6, which suggests that isolating and fixing model issues, though non-trivial, may be more tractable with existing tooling and practices. From these values, we can conclude that prioritizing optimizations to reduce computational burden, investing in robust training strategies to handle model complexity, and establishing ethical safeguards should be primary focuses when planning generative model projects, while continued attention to dataset curation and improved debugging workflows will also contribute to overall success. Now let's see how we can implement logging for tracking the performance of our GAN during training using TensorBoard. We start by importing the Summary Writer class from PyTorch's Torch Utils TensorBoard module, which provides an easy way to log data for visualization. After initializing the Summary Writer with a specified directory called run/gan experiment, we ensure that all our training metrics will be stored in this location. In the training loop, which runs for a number of epochs defined by num epochs, we insert logging commands right after calculating the generator and discriminator losses. By utilizing the addScaler method of the writer, we log the generator loss with a unique tag and associate it with the current epoch. The same is done for the discriminator loss. This structured logging allows us to track how each network's performance evolves over time. At the end of the training, we can use TensorBoard to visualize the logged metrics. This visualization helps us analyze the training dynamics and identify potential issues, such as whether one network is outpacing the other, which can be crucial for debugging our GAN model. One cannot overlook the ethical considerations when implementing generative models. The ability to generate highly realistic data comes with the responsibility of mitigating potential misuse. Deepfakes, for instance, have emerged as a major concern, with implications for privacy, misinformation, and identity theft. As creators and researchers in AI, it's vital we remain conscientious about how we apply our technologies. It's essential to incorporate guidelines and ethical frameworks within our work with generative models. Clear policies on how data is used and transparency about the capabilities and limitations of the models can help in addressing ethical concerns and building public trust in AI technologies. To summarize the challenges we've explored today, implementing generative models necessitates navigating complex training dynamics, ensuring high-quality, diverse datasets, managing computational costs, debugging intricate systems effectively, and addressing ethical implications. Each challenge requires unique solutions and considerations. As you progress in your journey with generative models, keep these factors in mind. In the next session, we will move on to techniques for optimizing the performance of generative models and explore advanced methods that can help us overcome these challenges. So stay tuned, and let's make your journey through AI not just educational but also enjoyable. Welcome to our exciting session on generating images with variational autoencoders, or VAEs for short. In today's lesson, we'll explore how VAEs can transform random numbers into artificial images, unearthing the underlying patterns that make this magic possible. So far, we learned about generative models in artificial intelligence, focusing on their application in creative content generation and the challenges faced during implementation. We discussed complexities in training these models, particularly with GANs and VAEs, emphasizing data quality, computational costs, and ethical considerations. Additionally, we highlighted the importance of effective debugging strategies and utilizing tools like TensorBoard for performance monitoring. These insights set the stage for exploring optimization techniques in future sessions. Today, we will cover the fascinating capabilities of VAEs in image generation, focusing on the mapping of latent vectors into meaningful visual outputs. Let's dive into the core concept of variational autoencoders. At their heart, VAEs are designed to learn efficient encodings of the training data in such a way that enables new data generation. Unlike traditional autoencoders that focus solely on reconstructing their input, VAEs introduce a probabilistic twist. They aim to learn the distribution of the data, allowing us to sample from this distribution and create entirely new data points. This is particularly valuable when we want to generate images from a latent space defined by random numbers. Imagine you stumble upon a magical vault filled with numbers. Each combination opens the door to a different image. To illustrate how this works, let's take a look at the structure of a VAE. Typically, a VAE consists of two main parts, the encoder and the decoder. The The encoder compresses the input image into a smaller latent space representation, while the decoder reconstructs the original image from this representation. So instead of mapping a single point in latent space to a specific image, VAEs learn to represent images as distributions over the latent variables. Now let's implement the encoder and decoder for our variational autoencoder using PyTorch. The encoder class is defined to transform input images into a smaller latent space representation, which involves two key outputs, the mean mu and the logarithm of the variance logvar of the latent variables. In this process, the input is first passed through a fully connected layer, after which a RayLU activation function is applied. The resulting output is then fed into two additional linear layers to generate mu and logvar, which are crucial for sampling in the latent space. Next, we will implement the decoder class, which takes this latent representation and reconstructs the original images. The decoder likewise consists of fully connected layers, commencing with a layer designed to expand the latent space representation, followed by a final layer that generates the output, passed through a sigmoid function to ensure the output values are between 0 and 1. This design is essential for maintaining high-quality reconstructions that resemble the original inputs, even when generated from random latent points. Together, these components create the foundational architecture of our VAE, allowing us to encode and subsequently decode images efficiently. Now let's take a look at the reparameterization trick, which is essential for allowing gradients to flow through our sampling operation during training. We implement this through a function called reparameterize, which takes the mean mu and log variance logvar obtained from the encoder. Inside the function, we first calculate the standard deviation by exponentiating half of logvar. This is crucial as it relates to how we sample from the normal distribution defined by our encoder's output. Next, we generate random noise with the same shape as the standard deviation. Finally, we return a sample in the latent space by adding mu to the product of generated noise and standard deviation. This method enables us to sample in a way that is fully differentiable, allowing for effective backpropagation during training. Next, we will write the loss function, which combines two critical components, the reconstruction loss and the callback labeler divergence. The loss function receives the reconstructed output from the decoder, the original input, and the mu and logvar from the encoder. We compute the binary cross-entropy between the reconstructed image and the original input, representing how well the decoder reconstructs the image. Simultaneously, the KL divergence penalizes the encoded distribution for diverging from a standard normal distribution. By summing these losses, we create a comprehensive measure to guide our model's training, ensuring it learns both to generate accurate reconstructions and to maintain a well-structured latent space. Now that we have defined the architecture and essential loss function for our variational autoencoder, VAE, let's implement the training loop to bring everything together. First, we load the MNIST dataset, which contains grayscale images of handwritten digits. The data loader is set up to shuffle and batch the images, ensuring that our model sees varied data during training. We also flatten the images into a one-dimensional array to match the input requirements of our neural network. Next, we initialize our encoder and decoder, specifying the dimensions for inputs, hidden layers, and the latent space. Both components are transferred to the specified device to enable efficient computation. The optimizer we choose, Atom, is a popular choice for training neural networks due to its adaptive learning rate capabilities, which helps stabilize and speed up training. As we enter the training phase, we iterate through the specified number of epochs, processing batches of data. For each batch, we clear the gradients, compute the encoder outputs, sample from the latent space using the reparameterization trick, and pass those samples through the decoder. This allows us to reconstruct the original images and calculate the loss, combining both the reconstruction error and KL divergence. Finally, we perform backpropagation to update the network parameters and monitor loss performance at each epoch. This iterative process is crucial for refining our model to generate high-quality images from the latent space. Now let's implement the following code to visualize the creative output of our trained VAE. We begin by disabling gradient tracking with TorchNograd to improve computational efficiency, since we will not be updating the model weights during the sampling process. Next, we sample random points in the latent space by generating 64 vectors from a standard normal distribution, which will then be decoded into images. Each of these latent samples corresponds to a unique combination of features learned by our VAE. Once we have our samples, we use the decoder to transform these latent vectors back into the image space, resulting in generated images that are representative of the learned data distribution. To effectively visualize the results, we utilize torch vision, utils, make grid to create a grid layout of the generated images, reshaping them appropriately for display. Finally, we render the grid image using matplotlib, ensuring that the axes are turned off for a cleaner presentation. This allows us to observe the diversity and creativity of the digit images produced by the VAA, showcasing the model's ability to generate new content from random latent representations. Generative adversarial networks, commonly known as GANs, have taken the world of artificial intelligence by storm. They represent a fascinating leap forward in the capabilities of neural networks for generating new content. Today, we will dive into how GANs work, their architecture, and their applications, while also illustrating concepts with code examples to solidify your understanding. So far, we learned about variational autoencoders, VAEs, and their role in generating artificial images from random numbers via learning data distributions. We've explored the architecture comprising the encoder and decoder, introduced the reparameterization trick, and implemented the loss function for effective training with the MNIST dataset. Our exploration highlighted VAE's creative potential and laid the groundwork for understanding optimization techniques. Now we will cover generative adversarial networks in detail, focusing on their competitive architecture and functionalities. Now let's implement the generator and discriminator classes for our GAN model. The generator class is designed to create synthetic images from random noise. It utilizes a structured sequential model that begins with dense layers, each followed by ReLU activation functions to introduce nonlinearity. Notably, the final layer applies a tan activation function, crucial for scaling the pixel values to a range suitable for image generation. Next, we'll establish the discriminator class, which focuses on evaluating the authenticity of images. Similar to the generator, its architecture features sequential layers, starting with a flattening layer to convert 2D image data into a 1D vector. Dense layers process this data, employing leaky ReLU activations to mitigate issues of vanishing gradients. The final output layer uses a sigmoid activation, generating a probability score indicating whether an image is real or generated. These components function collaboratively, with the generator learning to improve its outputs based on feedback from the discriminator, while the discriminator sharpens its distinguishing abilities by analyzing both real and fake images. This iterating process is integral to the effectiveness of GANs, promoting a dynamic learning environment. The figure presents a stacked bar chart comparing the generator and discriminator across two stacked categories labeled real data, blue, and fake data, orange, with the y-axis showing effectiveness %. For the generator bar, the chart displays 80% attributed to real data and 20% to fake data, whereas for the discriminator bar the proportions are inverted, 20% real data and 80% fake data. This pattern highlights a complementary distribution where each component's effectiveness sums to 100%, emphasizing their opposing roles in the adversarial setup. Interpreting these values in the context of training dynamics, the generator's large real data portion, 80%, indicates it is producing outputs that are largely being perceived as real, an indicator of successful generation, while the discriminator's large fake data portion, 80%, shows its ability to identify fake samples when evaluating inputs. Together, these proportions suggest a state where the generator has become proficient at producing realistic examples, yet the discriminator still retains strong discriminatory power, implying a balanced adversarial interaction rather than a collapsed or dominated state. This visual therefore underscores the core GAN objective, iterative improvement through competition, where shifts in these percentages across training would signal progress toward equilibrium or reveal instability that needs adjustment. Next, we will set up the data processing necessary for training our GAN. We begin by defining a transformation pipeline using PyTorch's transforms module. This involves converting images into tensors and normalizing them to ensure optimal data distribution for training. We utilize the MNIST dataset, a classic dataset of handwritten digits, specifying that we want to download it into the data directory if it's not already present. The data loader class is invoked to create manageable batches of data, shuffling them to ensure the model learns from different sets in each epoch. which is crucial for effective training. Now let's implement the generator and discriminator networks that make up our GAN architecture. We define both using PyTorch's NN module. The generator takes a random noise vector as input and outputs a generated image, consisting of several layers with ReLU activations to introduce nonlinearity. Conversely, the discriminator processes images to classify them as real or fake, using a layout that includes leaky ReLU activations for better gradient flow during training. Next, we'll focus on the training loop, where the generator and discriminator will compete against each other. For each epoch, we will generate fake images and compute the discriminator's loss based on both real and fake images, adjusting its weights accordingly. After optimizing the discriminator, we will switch to training the generator by minimizing its loss, thereby refining its ability to create realistic images that can fool the discriminator. Please note that we also include print statements to monitor the losses throughout the training process. Finally, to visualize the results of our training, we create a simple function that generates and displays images produced by the generator after each epoch. This function reshapes the generated images for better representation and arranges them in a grid format, providing a clear view of the progress made during training. It's important to understand the loss functions used in GANs. The loss of the discriminator measures how well it can distinguish real images from fake ones, while the generator aims to minimize the probability of the discriminator correctly identifying its outputs as fake. This adversarial process can sometimes lead to stability issues during training. Thus, variations of GANs like Wasserstein GANs, WGANs, and least squares GANs, LSGANs have been proposed. Each of these alterations aims to improve training stability, convergence speed, and overall output quality. Now that we've gone through a standard GAN setup, let's look at some real-world applications. GANs have been employed in numerous fields, from creating realistic images, like portraits or landscapes, to generating fashion designs and even enhancing image resolutions. One of the most impressive capabilities of GANs is in the realm of image-to-image translation. For instance, Cycle GAN is a type of GAN that transforms pictures from one domain to another, such as converting horse images to zebra images and vice versa, without needing paired examples of the two domains. We've taken a comprehensive journey through understanding GANs, from the foundational concepts of the generator and discriminator roles to building and training a simple GAN for image generation. There's a vast potential and excitement surrounding GANs, with ongoing research unearthing new applications and models. So far, we've covered GANs, their architecture, and how to implement them using PyTorch. We also discussed the importance of loss functions and introduced real-world applications. Looking ahead, we can explore advances in GAN variants, address challenges in training them effectively, and consider ethical implications surrounding their power in generating hyperrealistic content. As we wrap up this section, it's vital to remember that the world of GANs is continually evolving. From creative industries leveraging them for designing products to researchers pushing the boundaries of what's possible with machine learning, the scope of generative models is expanding rapidly. If you're intrigued by the world of AI and its potential, GANs will certainly continue to be an exciting area worth your exploration. Now let's see how we can implement the training loop for our GAN in PyTorch, focusing on logging the losses for both the generator and the discriminator. First, we initialize two lists, dlosses and glosses, which will store the loss values for the discriminator and generator respectively throughout the training process. In the training loop, we iterate over a specified number of epochs. For each epoch, we then loop through the batches of images provided by the data loader. We create tensor labels for real and fake images, where real labels are represented as ones and fake labels as zeros. Next, we proceed to update the discriminator by first calculating the loss on real images and then on fake images generated by the generator. After computing the total discriminator loss, we perform backpropagation and update the discriminator's parameters accordingly. Following that, we update the generator, calculating its loss based on the discriminator's feedback for the fake images it produced. Again, we backpropagate this loss and update the generator. As the last step of each iteration, we append both the discriminator and generator losses to their respective lists. This logging allows us to track loss dynamics over time, offering insights into the training stability of our GAN. The displayed horizontal bar chart titled Challenges of Implementing Generative Models quantifies the relative impact percent of 5 common implementation issues: training instability 25%, mode collapse 20%, data quality 30%, scalability 15%, and ethical considerations 10%. Key patterns evident from the chart are: 1. Data quality is the single largest reported impact at 30%, signaling that problems in the dataset, bias, noise, or poor representation, are the most influential factor undermining successful deployment. 2. The two technical training-related issues, training instability, 25%, and mode collapse, 20%, together account for 45%, which combined with data quality yields 75% of the overall impact, indicating that technical model behavior and data jointly dominate implementation risk. 3. Scalability, 15%, and ethical considerations, 10%, are quantified as lower impact categories by percentage, but remain meaningful in practice. From these proportions, we can draw practical conclusions. Prioritize robust data collection, curation, and augmentation to address the largest single source of impact. Invest in stabilization techniques, regularized training schedules, discriminator-generator balance, monitoring of loss dynamics to reduce the combined technical burden. Plan for scalable infrastructure early to avoid bottlenecks as model complexity grows. And allocate explicit processes for ethical review and mitigation despite its lower percentage, since ethical failures can have outsized consequences beyond the numeric score. The chart therefore serves as a direct guide for prioritizing efforts. Begin with data quality and training stability, while integrating scalability and ethics into the development lifecycle. Now let's take a look at a crucial aspect of our generator model, its architecture. In this code snippet, we define a generator class that inherits from NN module, which is a base class for all neural network modules in PyTorch. The constructor initializes a sequential model composed of several layers. We begin with a fully connected layer, NN. Linear, that takes a 100-dimensional input, transforms it to a 256-dimensional output, and is followed by a RayLU activation function. Next, we integrate dropout regularization by including NN dropout 0, 3 layers after the first two linear transformations. This dropout layer, with a dropout probability of 0.3, randomly sets 30% of the input units to 0 during training, which helps prevent overfitting and mode collapse by encouraging the network to learn multiple independent representations. We then continue with more linear layers, each followed by RayLU activations, until we reach the output layer that generates a 784-dimensional output, corresponding to a 28x28 image. Finally, the forward method reshapes the generated output, organizing it into the appropriate dimensions for further processing in our GAN framework. This structure enhances our generator's ability to produce varied outputs, addressing the mode collapse challenge. Now let's implement a simple data augmentation strategy using PyTorch's transforms library. We start by importing the necessary transforms from TorchVision, which provides a suite of common image transformations. The first step is to create a composite transformation using transforms compose. This allows us to chain multiple transformations together. Here we include transforms random horizontal flip, which randomly flips the image horizontally with a probability of 0.5, introducing variability in left-right orientations. Next, we add transforms random rotation 10, allowing the images to be rotated by a maximum of 10 degrees, making our model more robust to slight variations in angles. After applying these augmentations, we convert the images to tensors using transforms to tensor, which also normalizes the pixel values to a range of 0, 1. Finally, we normalize the dataset with transforms normalize, specifying mean and standard deviation values. To illustrate these transformations in action, we load the MNIST dataset by passing our transform to the datasets MNIST function. The data loader wraps our dataset, allowing us to shuffle and batch our training data effectively, ensuring a well-rounded training process. Now let's implement a simple model that utilizes gradient checkpointing to optimize memory usage during training. The model is defined by creating a class called myModel, which inherits from NN module, the base class for all neural network modules in PyTorch. Within the init method, we initialize two linear layers, layer 1 and layer 2, which define the structure of our neural network. The first layer takes an input of size 100 and transforms it to a size of 256, while the second layer reduces it to 128. In the forward method, we define how data flows through the network. Initially, the input data X is passed through layer 1, followed by applying the RayLU activation function to introduce nonlinearity. To enhance resource efficiency, we invoke the checkpoint function on layer 2, which allows us to save memory by not storing intermediate activations. This technique trades some computation during the backward pass for increased memory efficiency, making it particularly useful for training larger models. By implementing this gradient checkpointing, we aim to scale our deep learning tasks without the need for extensive hardware upgrades. The last challenge we will discuss revolves around ethical considerations. As generative models become more powerful, they also become more susceptible to misuse. For instance, deepfakes created via generative techniques can spread disinformation or produce harmful content. With this capability, the responsibility of practitioners and developers in understanding the implications of their work becomes paramount. Establishing guidelines and ethical frameworks for the use of generative models should include a clear understanding of how the generated data will be used. Developers must take care not to create models that propagate harmful stereotypes or invade privacy. Transparency in building these models and responsible reporting practices are important aspects of ethical AI deployment. As a practical step toward mitigating misuse, practitioners may employ model audit checks for bias detection, ensuring the robustness of the ethical guidelines established during model deployment. In summary, while generative models offer compelling opportunities, they present various challenges that practitioners must navigate carefully. From training instability to mode collapse and data quality issues, the path to effective implementation can be intricate. Emphasizing the importance of scalability, ethical considerations, and various strategies, like dropout regularization, data augmentation, and gradient checkpointing, will considerably bolster your approach to these challenges. As we conclude this discussion, it's evident that addressing these challenges requires awareness, diligence, and a proactive mindset. The world of generative models is continuously evolving, but by remaining informed and responsible, you can tap into their vast potential while contributing positively to the field of AI. In our next lesson, we will explore advanced GAN variants that have emerged to address some of the challenges we've discussed and the exciting possibilities they introduce. So stay tuned for more enlightening insights into the generative model world. In this lesson, we will dive into the advanced applications of generative models, particularly focusing on how these models can learn to map one type of image to another. Generative models have shown incredible promise in various fields, and understanding their advanced applications will allow us to tap into their full potential. So far, we covered the challenges of implementing generative models, such as training instability, mode collapse, and the importance of a robust dataset for successful implementations. Now, we will explore the innovative ways generative models can be utilized, especially in tasks involving image transformation and augmentation. Now let's see how we can implement the generator class, which forms the backbone of our style transfer model. In this implementation, we define a class called Generator that inherits from NN module, a base class for all neural network modules in PyTorch. Inside the init method, we initialize our neural network layers, beginning with a convolutional layer that takes in images with 3 color channels, typically RGB, and outputs feature maps with 64 channels. This convolutional layer uses a kernel size of 7, a stride of 1, and a padding of 3, which allows it to effectively capture details from the input image without losing spatial dimensions. Moving on to the forward method, we apply the RayLU activation function after passing the input through the convolutional layer. This activation introduces nonlinearity to the model, helping it learn complex image features. As we proceed with the style transfer process, this generator will eventually be expanded to include additional layers and functionalities that gradually transform the input images into stylized outputs. By focusing on extracting and then modifying the inherent features, we pave the way for compelling style transfer applications powered by generative adversarial networks. Next, we will write the discriminator class, which plays a crucial role in our GAN architecture by distinguishing between real images from the training dataset and the fake images generated by the generator. This class inherits from NN module, a base class for all neural network modules in PyTorch, allowing us to utilize its capabilities for building our model. Within the init method, we initialize a convolutional layer that accepts a 3-channel input representing RGB images. This layer has 64 output channels, utilizing a kernel size of 4, and applies a stride of 2 with padding of 1, effectively reducing the spatial dimensions of the input while capturing essential features. Now let's implement the forward method, where the input images are passed through the convolutional layer, followed by a LU activation function with a negative slope of 0.2. This activation function is crucial as it mitigates the vanishing gradient problem, allowing gradients to flow more effectively during training. Ultimately, the output of this forward pass will provide a representation that the following networks can use to classify images as real or fake, guiding the generator based on this feedback. Now let's implement the training loop for our GAN architecture, which is crucial for optimizing the generator and discriminator. We start by initializing 2 atom optimizers for the generator and the discriminator with specific learning rates and beta values that help maintain the stability of training. This setup is essential, as it allows both models to learn effectively from each other's performance during training. Next, we enter a loop for a number of epochs, iterating through the available data batches. Within this loop, we first focus on training the discriminator. We clear the previous gradients and generate fake images using random noise as input to the generator. The discriminator evaluates both real images from the dataset and these generated images, computing losses based on how well it can distinguish between the two. The real images should be classified as 1s, and the generated images should be 0s. By summing these losses, we backpropagate the gradients and update the discriminator's weights to improve its performance. Following the optimization of the discriminator, we switch our focus to training the generator. We again clear the gradients, generating fake images and calculating the generator's loss based on its success in fooling the discriminator. The goal for the generator is to produce images that the discriminator classifies as real. This cyclical training process allows both models to improve iteratively, showcasing the adversarial nature of GANs. Now let's see how we can implement the cycle GAN model, which facilitates the translation of images across 2 different domains. The cycle GAN class is structured around 2 generators and 2 discriminators to facilitate effective learning. When initializing the class, we call upon the generator class twice, once for converting images from domain A to domain B, and once for the reverse. Similarly, we instantiate 2 discriminators, one for each domain, to evaluate the authenticity of the generated images. Next, we define the forward pass method, where we execute the cycle of image transformation. The input images from domain A pass through the generator that transforms them into the B domain, producing fake B. We then generate a cyclical image, cycle A, by passing fake B back through the generator specifically meant to convert images from B to A. We repeat this process for images in domain B, creating fake A and obtaining cycle B. Ultimately, this bidirectional translation and the preservation of style between domains are crucial for tasks such as artistic stylization, making the cycle GAN a powerful architecture for cross-domain image transformations. The accompanying bar chart presents a direct comparison of 5 generative models, LLMA, Mixtral, DALL-E, Falcon, and Grok, across 2 measured dimensions shown in the legend. Application success, sky blue bars, and challenges, salmon bars, both on a percentage scale. Key patterns are visible. LLMA reaches the highest application success at -90%, while showing a moderate level of challenges, -30%, indicating strong practical performance with some remaining friction. Mixtral also performs well with -80% success and the lowest challenges, -20%, positioning it as both effective and relatively smooth to apply. Falcon shows percent success paired with the lowest challenges, -10%, suggesting a particularly stable model for deployment despite not being the top performer in success rate. Grok sits in the middle with -75% success and relatively high challenges, -40%, implying potential usefulness that is currently impeded by implementation or training issues. DALL-E is a clear outlier with the lowest success, -60%, and the highest challenges, -50%, signaling significant barriers to reliable application. Overall, the chart reveals a general inverse relationship between application success and reported challenges. Models with higher success rates tend to have fewer challenges, but with notable exceptions, e.g., Falcon's low challenges relative to its success. From this representation, we can conclude that for cross-domain tasks like the cycle GAN examples discussed above, prioritizing models in the upper left region of this trade-off, high success, low challenges, will likely yield more immediate practical gains, while models in the lower right require targeted work on stability, data quality, or architecture adjustments to close the gap. Now let's take a look at how we can implement the cycle consistency loss in our cycle GAN training process. The function cycle loss is vital for maintaining the integrity of images as they are translated between domains. It takes in the real image and the cyclical translated image as inputs, along with a weighting parameter called lambda cycle, which defaults to 10. Inside this function, we utilize the L1 loss, which effectively measures the absolute differences between the pixel values of the two images. This form of loss is particularly useful as it penalizes deviations, ensuring that generated images closely resemble their original counterparts. By multiplying the L1 loss by lambda cycle, we can control how much influence this particular loss has in our overall training objective. This provides flexibility to adjust the balance between maintaining image fidelity and driving the generator to create more realistic outputs. Such careful calibration is essential for optimizing the learning process during the training of the cycle GAN, ultimately leading to better image translations with minimal distortion. As we wrap up our discussion on advanced applications of generative models, it's important to address ethical considerations. With powerful tools like these, we have a responsibility to ensure they are used for good. For instance, while the ability to create photorealistic images from sketches opens up artistic possibilities, it also raises concerns around deepfakes and misinformation. Always remember, in the quest for innovation, we should aim to foster responsible use. The technology we develop should be wielded to enrich creativity, not deceive or mislead. Keep these factors in mind when applying generative models. So what have we covered today? We explored the advanced applications of generative models, focusing on architecture and strategies for image transformation. We looked at implementations with various code snippets such as generators and discriminators, and discussed how to optimize GANs, particularly cycle GANs, for cross-domain image translation. In conclusion, the world of generative models is rich with potential applications, from artistic transformations to innovative new solutions in industries ranging from entertainment to healthcare. As you continue your journey into the realm of deep learning, embrace these advanced methodologies and consider pursuing projects that reflect your creativity and commitment to ethical practices. Imagine the future with generative models at your fingertips. The only limit is your imagination. Happy coding. Now let's take a look at the implementation of the mini-batch discrimination class, a crucial component for enhancing the stability of GANs during training. This class is designed to calculate mini-batch discriminative features by capturing the similarities between samples in the generated batch. The init method initializes two parameters, numKernels and kernelDim, which determine the number of features and their dimensionality. A trainable weight matrix, W, is created using PyTorch's NN parameter, allowing the model to learn the optimal feature representation. In the forward method, we begin by processing the input tensor x, which represents the batch of generated features. We expand the dimensions of x to compare each sample within the batch against every other sample. By computing the squared differences between these pairs and summing them, we obtain a distance matrix that indicates how similar or different the features are across the batch samples. Finally, the method computes the mean of the exponential of the negative distances, creating a compact representation that helps the GAN to recognize patterns more effectively. This approach not only improves training stability, but also enhances the generator's output quality by ensuring it learns from the collective characteristics of generated samples. Now let's take a look at the implementation of a noisy generator class, which is designed to introduce Gaussian noise into the training of a generative model. This technique helps alleviate the issue of mode collapse by encouraging the generator to produce a wider variety of outputs. The noisy generator class inherits from NN, module, which is a base class for all neural network modules in PyTorch. Within the initializer method, we define a fully connected layer with an input size of 100 and an output size of 256. This layer will help transform the noisy input into a higher dimensional feature space suitable for generating outputs. In the forward method, we define how the generator processes input latent vectors. We begin by adding Gaussian noise to the input vector z. The noise has a specific scaling factor applied to it, in this case 0.1, which controls the amount of randomness introduced. This noisy vector is then passed through the fully connected layer, and we apply the RayLU activation function to introduce nonlinearity. By doing so, we not only increase variability in the generated samples, but also help the model navigate the latent space more effectively, thereby addressing the diverse output requirements of generative tasks like image creation. Now let's see how we can implement data augmentation techniques using PyTorch's TorchVision transforms. This code begins by importing the necessary transforms module, which provides a suite of transformations to enhance our dataset's variability. We define a composition of transformations using transforms compose, which allows us to combine multiple transformation steps into a single pipeline. In this case, we first include transforms random horizontal flip, which randomly flips images horizontally with a 50% chance, introducing variability that can help the model learn more robust features. Next, we apply transforms random resized crop 224 scale equals 0.81, enabling the model to interpret different cropped versions of images at varying scales. This is crucial for ensuring that the model learns to recognize objects regardless of their positioning within the frame. Lastly, we introduce color variations through transforms color jitter, which modifies the brightness, contrast, saturation, and hue of the images slightly. This adjustment further ensures our dataset remains diverse. Now let's apply this transformation sequence to an image by loading it using the image class from the PIL library and passing it through the defined transformations. The result is an augmented image that enhances our dataset's robustness, improving the model's generalization capabilities and helping to mitigate overfitting during training. The displayed horizontal bar chart titled Future Challenges in Generative Modeling quantifies 6 categories on a 0-100 difficulty scale and ranks them. Ethical considerations 90, instability in training 85, data scarcity 80, computational resources 75, mode collapse 70, and model interpretability 65. Key patterns are clear. Ethical concerns are rated the highest, indicating that governance, misuse prevention, and societal impact are perceived as the toughest problems to solve. Technical challenges cluster closely behind, with instability and data scarcity showing nearly the same high difficulty, underscoring the need for better training protocols and richer data pipelines. Computational resource demands sit in the mid to high range, signaling significant infrastructure and cost barriers, while mode collapse and interpretability, though slightly lower, remain substantial obstacles. From this distribution, we can draw practical priorities: immediate investment in ethical safeguards, detection, provenance, watermarking policy, parallel efforts to stabilize training techniques like mini-batch discrimination and feature matching, and expand or augment datasets, and targeted work on compute efficiency, distillation, model compression. The chart synthesizes the lesson's themes and suggests where to allocate research and operational effort to most effectively reduce overall implementation difficulty. Now let's implement the GradCam technique, which allows us to visualize the important regions of input images that influence model predictions. In this function, we first set the model to evaluation mode, which is crucial as it disables any training-specific layers like dropout. We then pass the input image through the model to obtain the output predictions. To compute the gradients necessary for generating the heat map, we create a one-hot encoded tensor representing the target class and perform backpropagation to calculate the gradients with respect to that class. Next, we retrieve the gradients of the activations, as well as the activations themselves. By averaging the gradients across the spatial dimensions, we obtain weights that indicate the significance of each activation map. Subsequently, we initialize a heat map with zeros, where we will accumulate the contributions of each activation, weighted by the calculated importance scores. By adding these weighted activation maps together, we create a comprehensive heat map representing the areas of the image that were most influential in the model's decision-making. This method can significantly enhance our understanding of how the model interprets input data and aids in debugging and improving model performance. Now let's implement the knowledge distillation process, where a smaller student model learns from a larger teacher model. We begin by defining the teacher model class, which consists of a fully connected layer with an input dimension of 100 and an output dimension of 256. In the forward method, the model applies a linear transformation followed by a sigmoid activation function, producing outputs that represent the teacher's learned knowledge. Next, we create the student model, which has a similar structure but with a smaller output dimension of 128. This smaller network is intended to efficiently capture the teacher's essential features while reducing computational complexity. Now we will implement the distill function to facilitate the transfer of knowledge from the teacher to the student model. This function iterates over a data loader containing input data and computes the outputs of both models. To encourage learning, we scale the logits from both models by a temperature parameter, which smooths the distribution of the predictions. The core of the training process involves calculating the Kullback-Leibler divergence loss between the softmax outputs of the student and the teacher. This loss guides the adjustment of the student model's parameters, ensuring it inherits the performance capabilities of the teacher while remaining more resource efficient. Lastly, ethical considerations will continue to be a challenge as generative models become more advanced. The ability to create photorealistic images and realistic audio or video presents powerful tools that can also be easily misused for malicious purposes, such as the creation of deepfakes, misinformation, and fraudulent content. To mitigate these risks, it's essential to implement best practices around model usage and development. This includes creating guidelines for responsible use, ensuring transparency in AI development, and training models on ethically sourced datasets. Promoting system accountability through regulatory frameworks is also important. A robust example of enforcement could involve developing common standards that prevent the chaos of deepfakes by embedding digital watermarks in generated content. Such watermarks can indicate when content has been altered or generated. As we wrap up our discussion on the future challenges in generative modeling, it's evident that while the technological advancements are exciting, they are accompanied by substantial hurdles that require concerted efforts from the AI community. From improving stability and diversity in outputs to addressing ethical concerns, the path forward necessitates innovation, creativity, and responsibility. Hopefully, this discussion has illuminated some of the complexities of implementing generative models. By understanding and tackling these challenges, we can continue to push the boundaries while ensuring the responsible use of these technologies. Despite the hurdles, the potential applications of generative models are vast and varied, from art and entertainment to healthcare and more. Embrace these challenges as they will shape the next steps in the evolution of generative AI. Thank you for tuning in and happy coding. Advanced generative models are transforming industries by creating art, music, text, and even complex simulations. Today, we're diving deep into an intriguing application of these models, the rediscovery of a lost Picasso masterpiece through generative modeling. Now let's take a look at a simple implementation of a generative adversarial network, GAN, designed for image generation. This code defines two key components, the generator and the discriminator. The generator takes random noise as input and transforms it through a series of layers into a 64x 64 pixel image with 3 color channels. Each layer employs activation functions like RayLU to introduce nonlinearity, enabling the model to capture complex patterns. The final output uses the tan function, which scales the pixel values to the range of -1 to 1, making it suitable for image representation. On the other hand, the discriminator seeks to effectively differentiate between real images and the fake images produced by the generator. It processes the input image through a sequential model with decreasing dimensions, utilizing leaky RayLU activation to allow a small gradient when the unit is not active, enhancing training stability. The output layer, equipped with a sigmoid function, provides a probability score between 0 and 1, indicating the likelihood of the input image being real. By iteratively training these two networks together, we create a dynamic system that progressively improves the quality of the generated images, showcasing the fundamental mechanism of GANs. The figure titled Impact of Advanced Applications of Generative Models displays 5 vertical bars, each corresponding to an application area and annotated with its impact score on a 0-100 scale. Text generation 90, art 85, research 80, music 75, and simulations 70. The bars are ordered categorically by application name, and each bar carries a numeric label above it, making exact comparisons immediate. Key patterns emerge. Text generation leads with the highest impact score, 90, indicating that advances such as large language models and transformer architectures have produced the most pronounced effects in this domain. Art follows closely at 85, reflecting strong influence of image-based generative techniques, GANs, diffusion models, in creative restoration and synthesis. This supports the lesson's example of uncovering a hidden Picasso. Research 80 and music 75 occupy the mid-range, suggesting that generative methods are driving substantive but somewhat less dramatic change there, while simulations 70 register the lowest score among these categories, implying either more specialized applications or higher barriers to broad impact. The relatively narrow spread 70-90 signals that all 5 domains benefit meaningfully from generative modeling, but priorities and resource allocation should reflect the observed differences. Emphasize text and image model development and evaluation when targeting maximum immediate impact, while recognizing the value of continued investment in simulation and music-specific architectures for longer-term gains. Next, we'll implement the training process for our GAN, which is vital for the generator and discriminator to learn from each other. In the train GAN function, we start by iterating through a specified number of epochs, wherein the model will refine its capabilities over time. For each epoch, we generate batches of random noise that serve as input for the generator to create fake images. These fake images are then evaluated alongside real images, with corresponding labels established for both categories, real images labeled with 1s and fake images with 0s. The discriminator is trained first. We clear its previous gradients, pass the real images to it for evaluation, and compute the loss based on how well it identifies real versus fake. This loss drives the optimization process, as we apply gradients to improve the discriminator's accuracy. Once the discriminator is updated, we shift focus to the generator. It's trained by assessing how well the fake images perform against the discriminator's expectations, aiming to improve its ability to deceive. The overall process encourages competition between the two networks, leading to progressively realistic outputs. This interplay perfectly aligns with our goal of recreating lost artwork, making each iteration a step closer to uncovering hidden treasures. Now let's see how we can implement a music generation model using a recurrent neural network, RNN. We begin by defining a music generator class that inherits from NN module, which is essential for building any neural network in PyTorch. In the constructor, we establish 3 key components: the RNN layer itself, which processes sequences of musical notes, a linear layer that maps the RNN's hidden output to the output size, representing possible musical notes. As we move to the forward method, we initialize the hidden state to 0s, accommodating the input data's batch size. The RNN processes the input sequence, and we extract the final output for the last time step, which we feed into the fully connected layer. This setup enables the model to predict the subsequent note based on the preceding sequence. Finally, we create an instance of the music generator, specifying parameters like input size, hidden size, and output size, ensuring it is directed to the appropriate device for computation, whether that be a CPU or GPU. Through this framework, our model will learn the complexities of musical compositions, allowing it to generate new melodies by leveraging learned patterns from the training data. Now let's take a look at how we can implement an autoencoder to enhance image quality, which plays a crucial role in reconstructing lost details in artworks. The autoencoder class is defined by inheriting from NN module, a base class for all neural network modules in PyTorch. The constructor initializes both the encoder and decoder as sequential layers. In the encoder, we compress the input, which in this case is a color image represented as a flattened tensor of size 3 × 64 × 64 pixels. It first reduces the dimensions to 512 and then to 256 using linear layers with Ray-LU activation, effectively capturing the essential features of the image. Following this, the decoder sequentially reconstructs the image back to its original size, starting from 256 dimensions back to 512, and finally expanding to 3 × 64 × 64. The use of the tan activation function at the output layer ensures that pixel values are scaled properly. In the forward method, the image is reshaped for processing, then encoded, and finally decoded to reconstruct the image. By adequately training this model, we can reveal the underlying Picasso masterpiece, enhancing image clarity in the process. As we conclude this exploration of advanced applications of generative models, we realize that these technologies hold immense potential to bridge the past and present. From uncovering lost artistic treasures to creating fresh compositions in music and text, generative modeling offers a new lens through which to view creativity. In this lesson, we covered the rediscovery of lost art, delving into the technical aspects of implementing generative models through GANs, RNNs, and autoencoders. So far, we have discussed their application and how they interact with data to create something entirely new. Generative models truly are the gateways to unlimited creativity and innovation in artificial intelligence. It's an exhilarating time to be involved in AI, and as we advance, who knows what other masterpieces we will uncover or create. Stay curious and keep exploring the wonders of generative modeling. Now let's take a look at how we can implement the training loop for a generative adversarial network, GAN. The train-GAN function starts by accepting the generator and discriminator models, a data loader for fetching real images, and a specified number of epochs for training. For each epoch, we loop through the batches of real images from the data loader. Inside this loop, we generate random noise, which serves as input for the generator to create fake images. We then proceed to train the discriminator by zeroing its gradients and preparing real and fake labels, indicating the authenticity of images. The discriminator processes both real images and detached fake images to prevent gradient flow back to the generator, allowing us to calculate the loss for both sources. After combining both losses, we perform backpropagation and optimize the discriminator's weights. Following this, we train the generator by resetting its gradients, passing the generated fake images through the discriminator again. This time, the generator aims to fool the discriminator, so we calculate the generator's loss using the real labels. After backpropagation and updating the generator's weights, we complete the training step for one iteration. This structure supports iterative improvements for both models, helping stabilize the training process crucial for effective GANs. Now let's see how we can implement data augmentation using PyTorch's TorchVision library to enhance the diversity of our training dataset and help mitigate the issue of mode collapse. We start by importing the necessary transforms module from TorchVision. With this module, we can create various data transformation techniques as part of a composable pipeline. In our example, we use transforms compose to combine multiple transformations, allowing us to apply them sequentially to our input images. First, we apply a random horizontal flip, which randomly flips the images horizontally with a 50% chance, creating mirrored variations of the original data. This effectively doubles the amount of training data, as the model sees both inverted and standard versions of the images. Additionally, we employ random rotation, which randomly rotates images by up to 10 degrees. This small variation in orientation helps the model develop a more robust understanding of the image features by exposing it to different perspectives. Finally, we include transforms to tensor, which converts the images into PyTorch tensors suitable for model input. After defining these transformations, we apply them when creating an instance of a custom dataset which prepares it for use in a data loader. This data loader will efficiently batch and shuffle the augmented dataset, setting the stage for our training process with a rich variety of images. Now let's see how we can implement a grid search to optimize the learning rate for our GAN. In this code snippet, we begin by defining a list of learning rates that we want to experiment with, which includes values such as 0.0001, 0.0002, and 0.0005. This variety allows us to systematically evaluate how different rates impact the model's performance. Next, we create an empty dictionary called results that will store the outcomes of our experiments. For each learning rate in our list, we initialize the atom optimizers for both the discriminator and the generator using the current learning rate. This step ensures that each optimization process is distinct and tailored to the specific learning rate we're testing. Then we call our previously defined train-GAN function to train the GAN model over a fixed number of epochs, 10 in this case. This training will allow the model to adjust its parameters based on the current learning rate. After training, we evaluate the generator's performance with a function called evaluateModel, storing the results in our results dictionary. This systematic approach helps us identify the optimal learning rate by analyzing the performance outputs for each rate tested, ultimately contributing to the fine-tuning of our generative model. The bar chart titled Unique Challenges of Generative Models synthesizes the relative impact of 6 key challenges by displaying an impact score out of 100 for each category. Reading the bars from highest to lowest impact, interpretability scores highest at 90, followed by mode collapse at 85, data quality at 80, training instability at 75, hyperparameter tuning at 70, and ethical concerns at 65. This ordering highlights a clear pattern. Challenges tied to understanding and controlling model behavior, interpretability, and mode collapse are judged most impactful, indicating that practitioners prioritize both the ability to explain outputs and the need to maintain diverse, robust generation. Data quality and training instability occupy the middle range, reinforcing that dataset curation and stabilization techniques are essential complements to algorithmic fixes. Hyperparameter tuning, while important, appears slightly less critical relative to structural and data-driven issues, suggesting that automated tuning methods, e.g., Bayesian optimization, can be practical interventions. Ethical concerns, though scored lowest among the 6, still register a non-trivial impact and should remain part of overarching governance. The chart's numeric labels above each bar make these comparisons precise and actionable. For prioritization, invest first in interpretability work and mode collapse mitigation, then strengthen data pipelines and training practices, while continuing systematic hyperparameter search and ethical safeguards. Now let's see how we can filter out biased examples from our dataset using Python. The function we create, filterBias, takes 2 parameters, data, which represents our dataset, and bias indicator, a term that signifies the presence of bias in the dataset items. Inside the function, we use a list comprehension to iterate over each item in the data. For each item, we check if the bias indicator is not present. If the condition is satisfied, the item gets included in the resulting filtered list. This approach helps us remove any items that could skew our model's learning. After defining the function, we use it to filter our original dataset, original data, by passing in the term bias term as the bias indicator. The outcome is assigned to filtered data, which now contains only those items that are free from the specified bias. By employing this filtering technique, we ensure that the training data is cleaner and more representative. This step is essential in fostering a generative model that can produce outputs that are both fair and accurate, ultimately helping us tackle the data quality challenges inherent in generative modeling. Now let's implement a method for visualizing high-dimensional data using T-distributed stochastic neighbor embedding, or TSNE. This technique is particularly useful when we want to understand how our generative model represents data in a lower dimensional space. First, we start by importing the necessary TSNE class from the Sklearn library. Then we define a function called visualize, which takes in our high-dimensional data as an input. Inside the function, we create an instance of the TSNE class, specifying that we want to reduce our data to 2 dimensions by setting the parameter encomponents to 2. We then call the fitTransform method on our TSNE instance, passing in the data we want to visualize. This step computes the TSNE coordinates for our original data, effectively transforming it into a more manageable form that can be plotted. Finally, we utilize matplotlib_scatter function to create a scatter plot of the reduced data, where each point represents an observation in the 2-dimensional space. The show method is called to display the plot. This visualization aids in grasping how well the model clusters similar data points and contributes to our understanding of its generative process. Now let's see how we can implement an explanation mechanism using Lime, which will help us interpret the predictions made by our text classifier. We start by importing the necessary LimeTextExplainer class from the LimeText module, which is designed for text data. Once we have the explainer class, we create an instance of it, specifying the classification labels. Here, we have negative and positive. This step sets up the framework for generating explanations based on the model's predictions. We then select an arbitrary instance index from our dataset. In this case, we choose the second item, index 1. Next, we use the explainInstance method of our explainer object to generate an explanation for the selected instance. We pass the features of the instance and the model's probability prediction function to this method, along with an option to focus on the top label for clarity. Finally, the explanation is rendered in a notebook format where users can visually interpret how the input features influence the classifier's output, enhancing transparency and trust in the model's decision-making process. As we wrap up our exploration of the unique challenges associated with generative models, it's clear that while the potential applications are vast, there are significant hurdles to overcome. From training stability and mode collapse to data quality and ethical problems, each aspect requires attention and thoughtful solutions. Today, we discussed multiple challenges faced in implementing generative models and explored practical techniques to address them. As we navigate this intricate landscape, it is crucial to remain diligent in our approaches and conscientious in our applications. With these considerations in mind, we can harness the true power of generative modeling, ushering in a new era of creativity and technological advancement. Let's continue to challenge ourselves with these ideas, knowing that each step we take towards addressing these challenges brings us closer to unlocking the full potential of generative models. Thank you for joining me today, and let's keep the learning journey alive. Generative models have emerged as a powerful tool in the field of machine learning, specifically in data augmentation. They present an innovative solution to the challenge of working with small datasets by generating additional synthetic examples. In this segment, we'll delve into how generative models can be utilized for data augmentation, enhancing the usability of limited datasets and ultimately improving model performance. So far, we learned about the transformative impact of generative models in various fields and the unique challenges in their implementation. We explored issues such as training instability and hyperparameter tuning. We also discussed methods like data augmentation to address these challenges. Now, we will cover how generative models specifically help in augmenting datasets and the techniques you can implement with Python and PyTorch. Data augmentation using generative models involves creating new data points that mimic the underlying distribution of existing data. This process is crucial because it alleviates the fears surrounding overfitting, which often arises from training on small datasets. Synthetic data can introduce more variation, thereby helping models generalize better. One popular type of generative models is generative adversarial networks, or GANs, which consist of two neural networks, the generator and the discriminator, that work against each other to produce convincing synthetic data. Now let's implement the generator and discriminator networks for our GAN. The generator class is first defined, where it initializes a series of fully connected layers that transform a 100-dimensional random noise vector into a 28x28 image. The layers include RayLU activation functions, which help introduce nonlinearity, and the final layer uses tan activation since image pixel values are typically normalized between -1 and 1. In the forward method, this random noise is passed through the layers, and the output is reshaped to match the 28x28 image format. Next, we define the discriminator class, which serves to evaluate the authenticity of images. Similarly, it consists of fully connected layers that analyze 28x28 input images and output a single probability indicating whether the image is real or fake. The use of leaky RayLU activations helps prevent dying RayLU issues by allowing a small gradient when the unit is not active. The final output layer employs the sigmoid function to map the discriminator's predictions to a probability between 0 and 1. By establishing these foundational networks, we set the stage for the adversarial training process in the GAN framework. Next, we will implement the training loop for our GAN, which orchestrates how the generator and discriminator learn from each other. First, we define the batch size, number of epochs, and learning rate, which are critical hyperparameters for controlling the training process. We instantiate both the generator and discriminator networks, ensuring they will be trained on the same dataset. Now let's set up the loss function. We employ binary cross-entropy loss, a standard choice for classification tasks like this where the goal is to distinguish between real and fake images. Following that, we create optimizers for both networks using the Atom optimizer, which helps in fine-tuning the learning process based on the gradients we compute. In each training epoch, we first train the discriminator using real images, and then update it with fake images generated by the generator. This process involves feeding real images into the discriminator, calculating the loss, and backpropagating that loss to update the discriminator's weights. Afterward, we train the generator by attempting to fool the discriminator into thinking the fake images are real. This dynamic process encourages both networks to improve continually. Finally, we print the loss values to monitor how effectively each network is learning throughout the training epochs. At this point, let's elaborate on where the strengths of data augmentation through generative models really shine. As mentioned, generative models offer an effective way to augment datasets, especially when the size is limited. For instance, if we are dealing with a dataset of images containing cats and dogs, we can generate new synthetic images of cats and dogs that are not present in the original dataset, enriching it without needing to collect additional real images. Now think of practical applications. Imagine in the medical field where acquiring data can be costly and sometimes rare. In such cases, generative models provide a way to create more training data, which can lead to better diagnostic models. The figure titled Effectiveness of Data Augmentation Techniques Using Generative Models displays 5 techniques on the x-axis and their measured effectiveness in % on the y-axis with numeric annotations above each bar. The standing order from highest to lowest effectiveness is CGANs at 90%, GANs at 85%, data synthesis at 80%, variational autoencoders, VAEs at 75%, and neural style transfer at 70%. From these values, we can draw several conclusions. Conditional GANs, CGANs show the highest effectiveness, indicating that conditioning generation on class or label information improves the usefulness of synthetic samples for downstream tasks. Standard GANs are a close second, confirming their strong ability to produce diverse, task-relevant examples. Data synthesis methods, rule-based or simulator-driven, perform well and can be a competitive alternative when domain knowledge is available. VAEs provide moderate gains, likely reflecting their tendency to produce smoother or blurrier samples that still enrich training distributions. And neural style transfer is comparatively less effective for augmentation when the goal is to improve task-specific metrics, which suggests it primarily alters appearance rather than creating new, label-preserving variation. The relatively small gaps between these bars, all above 70%, also imply that multiple generative approaches can meaningfully improve datasets, and that selecting or combining techniques should be guided by the task, availability of labels for conditioning, and the type of diversity required. Now let's implement a function to visualize the synthetic images generated by our GAN. This is important for assessing the quality and diversity of the produced data. The function begins by generating a batch of random noise, which serves as the input for the generator model. In this case, we use 25 random noise vectors. Once we obtain the generated images, we convert them to a NumPy array for easier manipulation and visualization with Matplotlib. The PLT figure method sets up a figure with a specified size, allowing us to organize our images neatly in a grid. In this case, we arrange them in a 5x5 grid. Within a loop, each generated image is displayed in a subplot. The PLT imshow function renders the images using a grayscale color map since the generated outputs are likely single-channel images. We also remove the axis for a cleaner look. Finally, the PLT show function displays the grid of images, enabling us to visually assess how well our generator is performing. This step is crucial to ensure that the synthetic data we're generating is representative and useful for our applications. Now let's take a look at the implementation of the conditional generator class, which is designed to extend the capabilities of a standard generator in a GAN by incorporating class labels as additional input. This class begins with an initialization method where we create an embedding layer to convert the class labels into dense vectors. This helps the model understand the different categories available during the image generation process. Next, we define the network architecture, which uses a sequential model to build a neural network that combines the random noise vector /z/ with the label embeddings. The architecture consists of several linear layers interspersed with RayLU activation functions, culminating in an output layer that generates a 28x28 image. The key here is that we add the label embedding to the noise vector before feeding it through the network, allowing us to condition the generated images based on the specified label. Finally, the forward method is implemented to enable the generator to accept both noise and labels as inputs, ultimately producing images that reflect the desired class. By training this conditional generator, we can effectively generate specific classes of images on demand, enhancing the diversity and relevance of our synthetic data. Lastly, we should address the ethical and practical implications of using generative models for data augmentation. It's essential to be transparent about the use of synthetic data, particularly in sensitive areas like healthcare, where accuracy is paramount. Additionally, understanding biases in the original training data must remain a priority, since the model might propagate those biases in the synthetic data it generates. As we conclude, generative models present a versatile approach to data augmentation. By creating additional synthetic examples, they empower us to train more robust models, especially when real-world data is scarce or expensive to acquire. However, with this power comes the responsibility to ensure these methods are used ethically and effectively. So there you have it. Using generative models for data augmentation is not only feasible but immensely beneficial. Whether through GANs or conditional GANs, the techniques we've covered today lay the groundwork for augmenting datasets with synthetic examples. Start experimenting with your projects and witness firsthand how generative models can enhance your machine learning workflows. In this lesson, we're diving into the fascinating world of style transfer and image transformation applications. We'll explore how generative models facilitate the mapping between different kinds of images, allowing us to create stunning visual effects and transform images in innovative ways. So far, we learned about the significance of generative models in machine learning, particularly for data augmentation with limited datasets. We discussed how these models, especially GANs, can produce realistic synthetic data to improve model performance and mitigate overfitting. We also explored practical applications and the ethical considerations of using synthetic data in sensitive areas like healthcare. Finally, we highlighted the importance of visualizing generated data to assess its quality and representativeness. Now we will talk about how we can leverage generative models for style transfer and image transformation applications. Let's start with the concept of style transfer, which is a technique that allows us to apply the artistic style of one image to the content of another image. Think of it as taking a beloved painting, like Van Gogh's Starry Night, and using its brushstrokes and colors to imbue a photograph of your backyard with that unique artistic flair. The magic behind this transformation lies in neural networks, specifically convolutional neural networks, CNNs. Now let's see how we can implement the function to load and pre-process images for style transfer. We begin by defining a loadImage function that accepts the image path and a maximum size parameter. The function utilizes the PIL library to open the image, checks if its size exceeds the specified maximum, and rescales it if necessary. This ensures efficiency while retaining quality. We then transform the image into a tensor that is compatible with PyTorch's processing requirements using the transforms module. This involves converting the image into a tensor and adding an additional dimension so it can be processed in batches. Following this, we create a class named VGG, which initializes the pre-trained VGG19 model. We pass in a list of layers that we want to extract for content and style representation. The class's forward method iterates through the layers of the model, collecting outputs from specific convolutional and ReLU layers to form two separate lists, one for style representations and another for content. This careful selection allows us to effectively capture the necessary features from our images, facilitating the style transfer process. The horizontal bar chart titled Effectiveness of Style Transfer Applications in Image Transformation displays 5 application domains along the vertical axis and their effectiveness percentages along the horizontal axis. The values shown are fashion visualization at 92%, artistic style transfer at 90%, real-time AR effects at 89%, image restoration at 85%, and medical imaging at 78%. Key patterns are immediately visible. Creative and consumer-facing applications, fashion visualization and artistic style transfer, occupy the top of the ranking, indicating the highest reported effectiveness, with fashion visualization leading by a small margin. Real-time AR effects is nearly as effective as artistic style transfer, positioned just below them, which highlights the method's suitability for interactive and live applications. Image restoration is moderately effective, while medical imaging shows the lowest effectiveness among the 5 domains at 78%. The spread across applications is relatively narrow, 78%, 92%, suggesting that style transfer techniques are broadly useful across diverse tasks but perform best in visual perceptual tasks tied to aesthetics and user-facing experiences. From these values, we can conclude that style transfer is particularly strong for generating or modifying visual content where stylistic appearance is paramount, while applications demanding strict fidelity or domain-specific accuracy, such as medical imaging, may require additional tailored approaches or validation despite being promising. Now let's implement the functions needed to compute the gram matrices, which are essential for measuring style in our images. The gram matrix function takes a tensor representing the feature maps extracted from an image and computes the gram matrix, capturing the correlations between different features. It reshapes the input tensor to facilitate matrix multiplication and normalizes the result by dividing it by the product of the number of channels and the height and width. This normalization helps maintain the scale of the computed gram matrix. Next, we define the getStyleContentLoss function to collaboratively assess the content and style losses between our target image and the original content and style images. It calculates the mean squared error, MSE, for content loss based on specific layers in the feature maps, and aggregates MSE scores for style loss from the gram matrices of both the target image and the style image. The combination of these two losses dictates how well our generated image preserves content while adopting the desired style, enabling an effective optimization process that we will set up afterward. Now let's implement a function to visualize the generated artwork after the style transfer process. We will define a helper function called imShow, which takes a tensor as input. This function first detaches the tensor from the computation graph and moves it to the CPU. By squeezing the tensor, we remove any unnecessary dimensions, ensuring it matches the expected input format for visualization. Next, we clamp the values of the tensor to the range of 0 to 1 for proper image representation. To convert the tensor into an image that can be plotted, we transform it into a NumPy array and rearrange the dimensions to match the format required by Matplotlib, which expects images in the shape, height, width channels. By disabling the axis for a cleaner presentation, we focus solely on the artwork. Finally, we invoke the imShow function on target image, inputting our optimized image that seamlessly blends content and style, allowing us to admire the results of our efforts in style transfer. This visualization step is crucial as it provides tangible feedback on how effectively the style has been integrated into the content image. In the world of augmented reality, AR, image transformation enhances user experiences by allowing users to superimpose artistic filters on live camera feeds or to transform real-world images in real time. Picture attending a concert and using your phone to apply various filters or styles to the scene before sharing it on social media. It's interactive and engaging. Another fascinating use case is in the realm of game design, where developers can generate unique textures and environments based on predefined styles. This can drastically reduce the workload while enhancing creativity. Instead of designing every texture from scratch, they can combine styles drawn from various influences, speeding up the development process and delivering visually stunning results. As we explore further, we can't overlook the ethical considerations involved in using generative models for image transformation. Since deepfake technology has become a significant talking point, it's crucial to enforce guidelines and practices that ensure the responsible use of style transfer. Misuse can lead to dishonest representations or manipulated content and propagate misinformation, particularly in sensitive cases. One potential solution is to maintain transparency in the applications of these technologies. When using style transfer or generative models, clearly indicating that a piece of content has undergone transformation serves to uphold integrity in representation and prevents misunderstandings. So there you have it, a comprehensive overview of style transfer and the many applications of image transformation using generative models. By creating stunning visualizations and merging diverse styles, we're not just becoming digital artists, we're also pioneering new frontiers in technology. As we continue coding, experimenting, and pushing boundaries, let's embrace the creativity within technology and share it with the world. Now it's your turn to replicate these techniques. Go ahead and tweak parameters or experiment with different styles and content images. With endless possibilities, the only limit is your imagination. Generating images using latent vectors is a fascinating aspect of generative models in machine learning. By leveraging techniques such as deep learning, we can create realistic images from random latent vectors, enabling us to explore a vast space of artificial images without the need for labeled data. So far, we learned about generative models and their role in enhancing machine learning, particularly in data augmentation and creating realistic synthetic data. We explored the technique of style transfer, which applies the artistic style of one image to the content of another using pre-trained models like VGG19. Additionally, we discussed how style transfer has practical applications in various industries, including fashion visualization, augmented reality, and game design, while considering the ethical implications of these technologies. Now, we'll dive deeper into image generation utilizing latent vectors, a concept fundamental to understanding how we can map random numbers to create stunning visuals. Now let's see how we can implement a variational autoencoder, VAE, which consists of two main components, the encoder and the decoder. The encoder converts input images into latent vectors by passing them through a series of fully connected layers, producing two output vectors, one for the mean and another for the log variance. These vectors characterize the latent distribution from which we can sample to generate new images. Next, we define the decoder, which takes these latent vectors and reconstructs the original image through similar fully connected layers, ultimately outputting an image of the same size as the input. Now let's take a look at the VAE class where both the encoder and decoder interact. The forward method first reshapes the input image for processing, then uses the encoder to obtain the mean and log variance. In the reparameterization step, we sample from the latent space using the mean and log variance, ensuring that the generated samples retain meaningful features. Finally, this sampled latent vector is passed through the decoder to reproduce the image. This framework allows us to effectively train our model, enabling us to learn robust latent representations that can generate diverse images from sampled latent vectors. Now that we have our variational autoencoder structured, let's implement the training process using the MNIST dataset. First, we define a series of transformations to preprocess the images, converting them to tensors and normalizing their pixel values to a range of -1 to 1. Next, we create our training dataset in Data Loader, which allows us to efficiently manage and shuffle the data in batches during training. Now let's set up the optimizer, which is crucial for updating our model's weights. We opt for the Atom optimizer, known for its adaptive learning rates, and we pass in our model parameters along with a learning rate of 0.001. Following this, we define our loss function, which combines two essential components: binary cross-entropy, that measures how well the reconstructed image matches the original, and callback labeler divergence, which regularizes the latent space to ensure meaningful sampling. Next, we move into the training loop, running it for 10 epochs. For each batch of images, we clear the gradients, perform a forward pass through the model, calculate the loss, and update the model's parameters. Finally, we print the loss for each epoch, allowing us to monitor the training progress and performance. Now let's implement the function to generate images from our trained model. This function, generateImages, takes in the VAE model and the number of images we want to generate as parameters. First, we set the model to evaluation mode, which is important for ensuring layers such as dropout and batch normalization behave appropriately during inference. Then we use the torch no_grad context to disable gradient tracking, making the operation more efficient since we don't need to calculate gradients for generating new samples. Next, we sample random latent vectors, z, from a standard normal distribution, which serves as our input to the decoder. This randomness allows us to explore the latent space and generate diverse outputs. The decoder processes these vectors and reshapes the output to match the dimensions of MNIST images. Finally, we visualize the generated images using Matplotlib. The loop iterates over the generated images, displaying them in a grid format for easy comparison. This will allow us to see the handwritten digits created by our model, demonstrating how the latent space can produce novel images that still resemble those in our training dataset. The displayed bar chart compares four models labeled Model A through Model D by showing two quantities per model, the number of model parameters annotated as parameters billions, and the size of the training dataset annotated as dataset size trillions. Reading the bars, Model A has roughly 70 billion parameters and a dataset of about 0.2 trillion tokens, 200 billion. Model B shows tilde 280 billion parameters with a dataset near 1.3 trillion tokens. Model C has billion parameters paired with a very large dataset of tilde 15 trillion tokens. And Model D shows the largest parameter count at tilde 1, 6 trillion, but the same dataset size as Model C, tilde 15 trillion tokens. Key patterns visible from the chart. 1. Dataset size generally grows as models get larger, but not strictly proportionally. 2. Models C and D share the same, very large dataset size despite a substantial jump in parameters from C to D, indicating a point where parameter scaling outpaced dataset scaling in this comparison. And 3. The dataset to parameter ratio varies considerably across models. Model B and C have datasets several times larger than their parameter counts, while Model D's parameter count approaches the same order of magnitude as its dataset. From these displayed values, one can conclude that while larger models are often trained with larger datasets, the relationship is not fixed. Designers must consider both parameter scale and available data when aiming to learn rich latent representations, and matching dataset scale to model size is an important practical consideration suggested by the comparisons shown. Now let's see how we can implement the components of a generative adversarial network, GAN, specifically the generator and discriminator models. The generator class initializes with several linear layers, progressively increasing the dimensionality of the input latent vector. It uses ReLU activations for the intermediate layers to introduce nonlinearities and culminates with a TAN activation to ensure the output images are within the desired range. The output is reshaped to match the dimensions of the target image format. Next, we will write the discriminator class, which serves to differentiate between real and generated images. Similar to the generator, it has a series of linear layers but in reverse order, reducing the dimensionality from the image size down to a single output value that indicates authenticity. Here, we employ leaky ReLU activations to allow a small gradient to flow when the unit is inactive, which helps during training. In summary, these two classes form the core architecture of the GAN, where the generator crafts new images from random noise and the discriminator evaluates them. This dynamic interplay between the models during training enables GANs to produce highly realistic images over time. Now let's implement the following code that brings our GAN training process into action. We start by initializing our discriminator and generator models, followed by defining optimizers for both using Atom with a learning rate of 0.0002. This ensures that we efficiently update the parameters of each model during training. Next, we enter the main training loop, which runs for 10 epochs. Within this loop, we iterate through each batch of training data. For the discriminator's training, we first set its gradients to 0. We then prepare both real and fake images. Real images come directly from the dataset, while fake images are generated by passing random noise drawn from a normal distribution to the generator. For the loss computations, we create labels for real images set to 1s and for fake images set to 0s. We calculate the loss for both real and fake images using binary cross-entropy, summing these losses to determine the total loss for the discriminator. After backpropagation, we optimize the discriminator's parameters. Subsequently, we switch to training the generator by again resetting gradients, calculating its loss based on the discriminator's evaluation of the fake images, and performing another optimization step. This alternating training process helps improve both models over time, resulting in increasingly convincing image generation. In conclusion, generating images using latent vectors provides a profound way to create artificial data and explore creative possibilities without labels. With models like VAEs and GANs, we can effectively map random vectors to tangible images. The key takeaway here is understanding how the latent space operates and how manipulation of latent vectors can lead to the generation of diverse and sometimes completely novel data. Beyond simply generating images, these concepts can be applied to various fields like art, design, and even game development, offering fertile ground for innovation. As we continue our journey into machine learning, remember that the latent vectors not only serve as a bridge between the noise of random numbers and the clarity of generated images, but also symbolize a vast universe of creative opportunities waiting to be explored. Let your imagination run wild. Natural language processing, or NLP, has emerged as a cornerstone of artificial intelligence, revolutionizing how we interact with machines. By understanding and generating human language, we unlock new possibilities in technology, from chatbots to large language models. So far, we learned about generative models in machine learning, particularly the role of latent vectors in creating realistic images. We explored the architecture and implementation of variational autoencoders, VAEs, for encoding and decoding data, along with the training process involved in generating images. Additionally, we discussed the functionality of generative adversarial networks, GANs, and how they can produce even more realistic outputs by pitting a generator against a discriminator. Ultimately, these concepts enable us to harness the potential of latent vectors for innovative applications across various fields. Now we will talk about the innovations in natural language processing, particularly focusing on the transformer network and its evolution through models like BERT. To begin with, let's discuss the foundation of NLP innovations, the transformer model. Released in 2017, the transformer architecture was a game changer. It replaced recurrent neural networks with a mechanism that allowed models to handle sequential data more efficiently. The core principle behind transformers lies in self-attention, a process where the model weighs the significance of different words concerning each other in a sentence, providing a rich contextual understanding. Now let's implement the attention mechanism in a simple Python function. We begin by importing necessary libraries, specifically PyTorch and its functional module, which provides various operations we will need. The function attention takes three inputs: query q, key k, and value v. Inside the function, we calculate the attention scores by performing a dot product between the query and the transpose of the key. This step captures how much focus each query should place on each key, allowing the model to weigh the relevance of different words in the input. To ensure the scores are suitable for comparison, we scale them by the square root of the dimension of the query vectors, which helps stabilize gradients during training. Following this, we apply the softmax function to the scores, converting them into a probability distribution. This focuses our attention weights, ensuring that they sum to 1, thus enhancing interpretability and utility. Finally, we compute the output by performing another dot product, this time between the weights and the value vectors. This results in a contextualized representation of the input, demonstrating how significant each word is in relation to others in the sequence. Now let's see how we can implement a simple version of masked language modeling using BERT in Python. We begin by importing the necessary components from the Hugging Face Transformers library, which includes the BERT tokenizer and model designed for masked language modeling tasks. Next, we load the pre-trained BERT tokenizer and model. This step is crucial because it enables us to utilize the extensive training BERT has undergone, effectively allowing us to tap into its linguistic understanding. After setting up our model, we will define an input sentence containing a mask token, represented as mask. This is the word we want the model to predict based on its context. Now let's tokenize and encode the input sentence. This step converts the sentence into a format suitable for BERT, specifically into tensor format, which is necessary for the model to process the input. Following this, we will perform masked language prediction by feeding the encoded input through the BERT model. Finally, we extract the logits from the model's output to identify the most likely word for the masked position. By decoding this predicted token, we gain insights into how well BERT understands language context and can predict missing words based on surrounding information. The displayed figure, titled Comparison of Parameters and Training Time of NLP Models, presents two linked measures for four models: GPT-3.5, BERT, GPT-2, and Chinchilla. The bar series parameters in billions shows that GPT-3.5 has by far the largest parameter count at 175 billion, followed by BERT at 110 billion, Chinchilla at 70 billion, and GPT-2 at 1.5 billion. Overlaid on the same x-axis is a line series, training time, in days with markers that reports training durations of 750 days for GPT-3.5, 16 days for BERT, 14 days for GPT-2, and 12 days for Chinchilla. From these plotted values, we can draw several observations and practical conclusions. First, GPT-3.5 is a clear outlier. It combines the highest parameter count with an extraordinarily long training time, 750 days, indicating a much larger compute training commitment than the other models. Second, the remaining 3 models cluster at much lower training times despite substantial variation in parameter counts. For example, GPT-2 has very few parameters, 1.5b, but a training time 14 days comparable to BERT 16 days, while Chinchilla sits between BERT and GPT-2 in parameter count 70b, but shows the shortest training time among the 3, 12 days. This pattern indicates that parameter count alone does not fully determine training time. The plotted data imply additional factors, architecture, training regimen, dataset size, or compute allocation, affect how long training takes. Finally, the juxtaposition of parameter bars in the training timeline highlights the trade-offs practitioners face. Very large parameter budgets can be associated with much larger training durations, and therefore resource cost, whereas models of differing sizes can achieve similar training times depending on design and training choices. These visual relationships help inform decisions about model selection when balancing capacity, training time, and available compute. Now let's see how we can implement text generation using the GPT-2 model with the Hugging Face library. First, we begin by importing the necessary classes, GPT-LM head model and GPT tokenizer, from the Transformers library, which allows us to access pre-trained models and their tokenizers easily. We then load the GPT-2 tokenizer and model using their respective from pre-trained methods, which fetch the model and tokenizer configurations. Next, we define an initial prompt, once upon a time in a magical forest, serving as the starting point for our text generation. After defining this prompt, we encode it into the format required by the model, converting the text into input IDs using the tokenizer, and setting the return type to a PyTorch tensor for processing. Following that, we call the generate method on the model, specifying the encoded prompt along with parameters such as max length, which controls how long our generated text will be, and numReturn sequences, determining how many variations of the generated text we want to retrieve. Once the model produces the output, we decode the generated tensor back into human-readable text using the tokenizer, ensuring we skip any special tokens and print the result. This showcases the model's remarkable ability to create coherent narratives based on the initial input prompt. A crucial consideration in training these models is the need for a large dataset. While pre-trained models alleviate this concern, they still require substantial computational resources to fine-tune effectively. This highlights an important balance, the relationship between model size, dataset size, and computational capacity. In practice, developers may choose to focus on the trade-offs that best match their available resources and application needs. As we explore this innovative landscape, it's essential to understand the considerations involving ethical implications of these models. The ability to generate text raises questions about authenticity and accuracy. Misinformation can spread easily, and the lines between human and machine-generated content may blur. In summary, the innovations stemming from the transformer architecture and its derivatives are transforming how we process and generate natural language. Through self-attention mechanisms, models like BERT and GPT have demonstrated the potential for powerful language understanding and generation, enabling advancements across various applications from chatbots to creative content creation. In today's lesson, you've learned about the groundbreaking developments of NLP innovations, from foundational transformer models to cutting-edge implementations like BERT and GPT. We've explored key functionalities through practical code examples that illustrate how these powerful models work. As we move forward, keep these principles in mind and consider the exciting possibilities that lie ahead in the realm of natural language processing. Generative modeling has revolutionized the way we approach data synthesis, with significant innovations transforming various fields, particularly in natural language processing. Today, we will explore how generative models create realistic textual content using complex interrelationships between words, highlighting key techniques like transformer networks and the BERT model. So far, we learned about the foundational concepts of natural language processing innovations, focusing on the transformer architecture and its role in enhancing language understanding. We discussed the self-attention mechanism that allows models like BERT and GPT to process context effectively, enabling powerful capabilities such as text generation and masked language modeling. Key implementations were illustrated through Python code examples showcasing how these models operate in practice. Additionally, we highlighted the importance of ethical considerations and the balance of resources in developing and deploying these advanced NLP systems. Now, we will cover innovations in generative modeling, specifically how representations of language data allow for effective textual generation, including practical implementations in Python. Now let's implement a simple transformer encoder using PyTorch to understand its structure and functionality. We begin by importing the necessary PyTorch libraries and defining a class, transformer encoder, which inherits from the NN module. Within the init method, we initialize several key components: an embedding layer that converts input tokens into dense vector representations, and a self-attention layer that allows the model to identify relationships between these tokens based on their context. Next, we create a feed-forward network consisting of linear transformations with array LU activation in between to introduce nonlinearity. This network further processes the data after self-attention has been applied. To stabilize learning and facilitate convergence, we incorporate layer normalization both after the self-attention layer and the feed-forward network. In the forward method, we pass the input data through the embedding layer, followed by self-attention, which yields outputs. These outputs are then passed through layer normalization before entering the feed-forward network. Finally, we apply another normalization before returning the final output, allowing the model to generate meaningful representations of the input tokens. This implementation serves as the backbone for various natural language processing tasks using transformers. The accompanying figure, titled Innovations in Generative Modeling, presents a bar chart that allocates an impact score in arbitrary units summing to 100 across 6 innovation areas: text generation 30, reinforcement learning 25, model distillation 20, multimodal models 15, agentic models 5, and textual evaluation 5. Key patterns emerge. Text generation holds the largest single share at 30, indicating it is the dominant focus area, while reinforcement learning and model distillation follow closely with 25 and 20 respectively. Together, the top 3 areas account for 75% of the total impact, signifying that advancements in generating high-quality text, training strategies that incorporate decision-making signals, and techniques that compress or transfer knowledge are the primary drivers of progress in the field. Multimodal models at 15 show a substantial but smaller emphasis, reflecting growing interest in integrating vision, audio, and text. Agentic models and textual evaluation are both at 5, equal and comparatively low, which suggests these topics are either emerging niches or under-resourced relative to generation, training methods, and distillation. From these values, one can conclude that the current innovation landscape prioritizes improving generative capability and efficiency, with increasing but uneven attention to multimodality and evaluation control mechanisms. Now let's see how we can set up a masked language modeling task using BERT with the transformers library. We begin by importing the necessary components, the BERT tokenizer and the model specifically designed for masked language modeling. The tokenizer converts our input text into a format suitable for the model, which includes tokenizing the sentence and returning it as PyTorch tensors. Next, we create a masked sentence, where we replace a word with the masked token, indicating to the model that it should predict this masked word based on its context. After preparing our input, we run the model in evaluation mode, disabling gradient calculations to optimize performance. The model then processes the input and generates output logits, which represent the predicted probabilities for each token in BERT's vocabulary. To identify the most likely word for the masked position, we locate the index of the masked token in the input. Using this index, we access the logits and find the token with the highest probability. Finally, we decode the predicted index back into a word and print it. This implementation illustrates how BERT leverages bidirectionality to effectively predict masked words, enhancing our understanding of context in language. Now let's see how we can implement a sequence classification task using BERT, which involves fine-tuning a pre-trained model on a specific dataset. We begin by importing the necessary classes from the transformers library, including BERT for sequence classification, which is specifically designed for tasks like sentiment analysis or text classification, and trainer alongside training arguments to manage the training process. Next, we define the training arguments, which allow us to specify crucial parameters for our training session. Here, we set the output directory for saving results, number of training epochs, batch sizes for training and evaluation, warm-up steps, weight decay, and logging directory for monitoring progress. These settings play a vital role in optimizing the training process and ensuring we achieve a well-tuned model. Following that, we instantiate the BERT model for sequence classification. By specifying num labels equals 2, we prepare the model for a binary classification task, whether it's positive or negative sentiment. After setting up the model, we create a trainer object with our model, training arguments, and datasets for training and evaluation. This trainer automates the training loop and evaluation process, allowing us to focus on analyzing results and improving our model's performance. Finally, we call the train method to kick off the training routine, which will iteratively adjust the model's parameters based on our training data. Now let's implement a function to gather user feedback on generated text. This feedback mechanism plays a crucial role in enhancing the model's performance and ensuring the content aligns with user expectations. In the code, we define a function called collectFeedback, which takes two inputs: predicted text, the text generated by the model, and user input, which could be any contextual information we might want to consider. The function prompts the user to evaluate the appropriateness of the generated text by asking, "Is this text appropriate?" The user is presented with a simple choice, yes or no. If the user responds with no, indicating dissatisfaction with the output, we trigger an adjustment process. Here, we include a placeholder comment explaining that the model should adapt its training data or strategy based on this feedback. This consideration is vital for creating a robust feedback loop that enhances the model's reliability over time. Through this approach, we encourage continuous learning, allowing the model to improve its outputs and address potential biases or inaccuracies in generated text. To wrap up our discussion on innovations in generative modeling, we've explored how transformer architectures like BERT have fundamentally transformed our approach to text generation and understanding. Through effective self-attention mechanisms and bidirectional context, these models excel at various natural language tasks, shaping the future of human-computer interaction. We also delved into practical implementations in Python, showcasing the code for key NLP tasks. While we've touched on the technical elements, the onus lies on developers and researchers to ensure ethical use and continuous improvement. The rapidly evolving landscape of generative modeling will undoubtedly present new challenges and opportunities, paving the way for a future where machines and humans collaborate in understanding language like never before. In conclusion, innovations in generative modeling are not just about enhancing capabilities, but also about responsible and ethical applications in real-world scenarios. Let's continue our journey in this field, staying curious and critical as we unravel the complexities of language through technology. Now let's see how we can implement a preprocessing function to clean and tokenize our tweet data. The first step is to utilize regular expressions to remove URLs and mentions from each tweet. This is important because these elements can introduce noise and distract from the core content we want to analyze. We apply a regex that matches any URL patterns and another that identifies usernames prefixed with @ replacing them with empty strings. After cleaning the data, we move to the tokenization process, where each tweet is split into individual words, making it easier for further linguistic analysis. The function takes a list of tweets as input and outputs a list of tokenized tweets. As an example, we define a small dataset of tweets in a pandas data frame, showcasing how this function can be applied in practice. Finally, we call our preprocessing function on this data frame and print the cleaned and tokenized tweets. This process not only prepares our data for modeling, but also highlights the necessity of ensuring quality data free from distractions when working with generative models. The figure titled "Challenges in Language Generation Using Generative Models" presents a horizontal bar chart that ranks 6 key challenges by an impact level arbitrary units. The bars and their numeric labels, read from highest to lowest impact, are quality of training data 28, ambiguity in language 24, creativity versus coherence 18, scalability 15, ethical considerations 10, and handling hallucinations 5. The x-axis runs from 0 to 35, and grid lines aligned with the x-axis help quantify differences between values. From these values, we can observe clear patterns. Data quality is the single most impactful challenge, with a modest lead, 4 units, over ambiguity, which itself is substantially more impactful, 6 units, than creativity vs coherence. Scalability occupies a middle position, while ethical considerations and handling hallucinations are assigned lower impact values in this representation. The explicit numeric labels at the end of each bar make the relative magnitudes unambiguous, allowing us to conclude that prioritizing efforts on improving training data and reducing ambiguity should yield the largest reduction in overall impact according to this chart, followed by managing creativity coherence trade-offs and scalability, with ethics and hallucination handling appearing as additional, though smaller, areas of concern. Now let's implement the following code that utilizes a pre-trained sentence transformer model to enhance our understanding of context within sentences. First, we import the necessary libraries, specifically cosine similarity from Sklern, metrics, pairwise, and sentence transformer from sentence transformers. We then load the paraphrase mini LM-L6v2 model, which is designed to generate meaningful sentence embeddings. Next, we define a set of sentences. In this case, the bat flew out of the cave and I hit the ball with my bat. By encoding these sentences using our loaded model, we obtain their respective embeddings, which are mathematical representations that capture their semantic meaning. This sets the foundation for analyzing how closely related these sentences are in terms of context. We then compute the cosine similarity between the two sentence embeddings. This metric measures the cosine of the angle between the two vectors created by the embeddings, providing insight into their contextual similarity. A value closer to 1 indicates a high degree of similarity. Finally, we print the cosine similarity result, which aids in understanding how well the model contextualizes meanings based on the provided sentences. This approach demonstrates how context-aware mechanisms can improve generative models' performance. Now let's see how we can implement the temperature sampling technique in our text generation model. This code defines a function called sampleWithTemperature, which takes a prediction distribution and a temperature parameter to control the randomness of the sampling process. The first step in the function normalizes the prediction distribution to ensure that the sum of probabilities equals 1. Next, the function applies a temperature adjustment by transforming the log probabilities of the distribution based on the specified temperature, influencing how the probabilities are reshaped. A lower temperature results in loss of randomness, leading to more deterministic choices, while a higher temperature introduces greater variability, which can enhance creativity but risks producing nonsensical outputs. After adjusting the probability distribution, the function normalizes it again, preparing it for the final selection of a word. The NP random choice method is then used to sample a word based on the modified probabilities, effectively incorporating the temperature influence. To demonstrate this, a dummy prediction distribution array is created to simulate the output from our model. Finally, we can call the function with a temperature setting of 0.7, showcasing how the model selects the next word while balancing creativity and coherence. This approach allows us to refine text generation, making it more aligned with our desired output characteristics. Now let's see how we can implement a simple distillation process in PyTorch to train a lightweight student model based on a more complex teacher model. First, we define a basic neural network architecture using a class called SimpleModel, which consists of a fully connected layer. This will serve as both our teacher and student models, taking an input dimension of 100 and producing an output dimension of 10. Next, we create instances of teacher model and student model, which initially have the same architecture. However, to facilitate the distillation process, we need to set the teacher model to evaluation mode while allowing the student model to be trainable. The core of our distillation is defined in the distill function, which uses callback labeler divergence as the loss criterion to measure the difference between the teacher's output and the student's output. In each iteration, the teacher's outputs are calculated without gradients, ensuring they remain static during the student's training. The student's outputs are then used to compute the loss. By backpropagating this loss and updating the student's parameters with an atom optimizer, the student gradually learns to mimic the teacher. Finally, a message indicating the completion of the distillation process is printed, signaling that our student model is now ready for deployment. Now let's implement a simple human feedback loop to evaluate the generated text for appropriateness. This function, human feedback loop, accepts a piece of generated text and prints it for review. It prompts the reviewer to provide feedback by asking whether the text is appropriate or inappropriate. If the feedback indicates that the text is inappropriate, we document this for review and potential corrective action. This step is vital as it highlights our commitment to ethical considerations in model outputs by acknowledging and addressing problematic content. Conversely, if the feedback is positive, we simply acknowledge that the feedback has been noted, allowing us to continue refining our outputs based on user input. This feedback loop is essential in creating a human-in-the-loop system that gathers diverse perspectives to enhance the fairness and sensitivity of our generated content. To demonstrate this process in action, we provide an example of a generated text, which we can then assess through our feedback loop function. This setup allows continual refinement of the model and its training data, leading to more responsible and ethical AI outputs. We've traversed a landscape filled with challenges surrounding language generation using generative models. From the need for quality data to the complexities of ambiguity, creativity, and ethical considerations, understanding these hurdles is vital for realizing the full potential of these technologies. As we look forward, the continued evolution of generative models holds promise, but addressing these concerns must remain a priority. In conclusion, while generative models open exciting avenues in natural language processing, successfully navigating their challenges requires diligence, creativity, and a commitment to responsible development. By staying informed and proactive, we can build compelling, ethical generative systems that enrich our interactions and understanding of language in profound ways. Thank you for joining me in exploring these critical aspects of generative models. Generative models have opened new frontiers in technology, allowing us to bridge the gap between various forms of data. Today, we're diving deep into the advanced applications of these models, particularly focusing on how they can learn to transform one type of image into another. This will help us appreciate the versatility and power of generative models. So far, we covered the challenges of language generation with generative models, including the need for high-quality training data and the biases that might arise. We also discussed the ambiguity inherent in human language and the importance of context-aware mechanisms in generating meaningful text. Moving forward, we will explore the captivating world of generative models as they relate to image transformation, showcasing examples and techniques that illustrate their capabilities. Now let's take a look at how we implement the generator and discriminator models using PyTorch. We begin by defining the generator class, which inherits from NN module. The constructor initializes a sequential model comprising several transposed convolutional layers designed to upsample the input noise into a stylized image. Each layer uses the RayLU activation function, except for the final layer, which employs TAN to normalize the output to the range of -1, a common practice when generating images. Next, we define the discriminator class, also extending NN module. This model takes an image as input and passes it through a series of convolutional layers, using leaky RayLU activations to introduce nonlinearity. The final layer employs a sigmoid function, producing an output between 0 and 1, where values closer to 1 indicate that the input is likely real, while values closer to 0 suggest it was generated. Both classes encapsulate the architecture necessary for the CGAN framework, allowing us to create and evaluate the generator's ability to produce convincing images, while simultaneously training the discriminator to distinguish real from fake inputs. Next, we will explore how we compute the generator and discriminator losses in our CGAN. The function generatorLoss calculates the loss for the generator, where the objective is to maximize the likelihood of the generated images being classified as real by the discriminator. This is achieved using binary cross-entropy, comparing the input from the discriminator for fake images against a tensor of ones, which signifies that the generator wants its outputs to be perceived as real. Now let's take a look at the discriminator loss function. This function computes the losses for both real and fake images processed by the discriminator. It first assesses the real images, using binary cross-entropy to measure the loss between the discriminator's output for real images and a tensor of ones. Following this, it evaluates the fake images, checking how well the discriminator can identify them as fake against a tensor of zeros. The final loss for the discriminator is derived by averaging both losses, ensuring a balanced approach to improving its ability to differentiate between real and generated images. These loss functions are crucial in guiding the training process, allowing both the generator and discriminator to learn and improve over time. Now let's see how we can implement our data loading and preprocessing setup using PyTorch. First, we start by importing necessary modules from TorchVision, including datasets and transforms, which will help us manipulate our image data. We define a transformation pipeline using transforms, compose, which allows us to chain multiple transformation steps. In this pipeline, we begin with transforms. Resizing our images to 64x 64 pixels, ensuring uniformity in dimensions, which is crucial for training our model. Next, we apply transforms to tensor, converting the images into PyTorch tensors, making them suitable for model input. Finally, we normalize the pixel values to the range of -1, 1 using transforms normalize, which helps stabilize learning. After defining the transformations, we create a trained dataset using datasets, fake data. While this is a placeholder for demonstration, you should replace it with your actual dataset containing landscape images and their corresponding artistic representations. We then use Torch utils data loader to wrap our dataset into train loader, which facilitates batch processing and shuffling of data during training, enabling our model to learn effectively from diverse samples across epochs. The displayed pie chart summarizes the relative emphasis across 4 aspects of generative image transformation: landscape 30%, artistic rendition 50%, challenges 15%, and solutions 5%. The dominant slice is artistic rendition at half of the total, indicating that the primary application focus in this context is converting inputs into stylized outputs. Landscape, as the next largest segment at 30%, represents the substantial portion of input data types being transformed. Challenges occupy a noticeable but smaller share, 15%, showing that a non-trivial fraction of attention is on problems the models must overcome, while solutions are a very small slice, 5%, suggesting comparatively few dedicated outputs or mitigations are currently emphasized. From these proportions, we can conclude that practical efforts and resources are concentrated on producing stylized images from landscape inputs. However, the relatively small allocation to solutions compared with challenges signals a gap where more targeted methods, evaluation metrics, or engineering effort could improve robustness and address failure modes in model outputs. Now let's implement the training loop for our conditional generative adversarial network, CGAN. We start by initializing the generator and discriminator models, specifying their input and output dimensions. The Atom optimizer is selected with specific learning rates and beta coefficients for both networks, ensuring stable training dynamics. Next, we set the number of epochs for which we wish to train the model. Within each epoch, we iterate through the batches of real images from our training dataset. For each batch, we generate random noise to feed into the generator, which produces fake images. The discriminator then processes both the real and fake images to determine their authenticity. We calculate the discriminator's loss based on its performance in distinguishing between real and fake outputs. After backpropagating this loss, we update the discriminator's parameters. Then we turn our attention back to training the generator. By feeding the fake images into the discriminator again, we compute the generator's loss, aiming to fool the discriminator into classifying these images as real. This loss is backpropagated, and the generator is updated accordingly. This alternating training approach helps both the generator and discriminator improve collaboratively, enhancing the CGAN's ability to produce high-quality outputs over time. Now that we have trained our model, it's essential to visualize the generated images and evaluate the artistic transformations learned by our generator. Let's take a look at how we can implement a function that achieves this. First, we import the necessary library, mappletlib, which we use for displaying images. The function showGeneratedImages is defined to accept the generator model and the number of images we want to generate. Inside this function, we start by creating random noise vectors, which serve as input for the generator to produce images. With the use of TorchNoGrad, we ensure that no gradients are computed, allowing faster execution since we're only interested in the output at this stage. The generated images are then moved to the CPU for visualization, and we utilize TorchVision utils make grid to arrange our images in a grid format. The images are permuted to ensure the correct orientation for display. Finally, we use PLT imshow to showcase the grid of generated images, rescaling their values back to a visible range while hiding the axis for a cleaner presentation. This function thus provides a clear view of how well our model has learned to transform landscapes into artistic renditions. In conclusion, generative models have showcased their powerful capabilities, especially in the realm of image transformation. Through the use of conditional generative adversarial networks, we've learned to map one kind of image to a second, bridging different visual styles and generating artistic renditions from ordinary photos. So far, we discussed the structure and operation of CGANs, prepared our datasets, and implemented a training loop to optimize our models. We also explored a method to visualize our generated images. In the next segment, we can discuss further enhancements to our model or explore different applications of generative models across other data domains. As we conclude today's lesson, remember that with generative models, the possibilities are substantial, from creating artwork to enhancing game graphics, and they pave the way for a fascinating intersection of creativity and technology. Generative models are at the forefront of machine learning, enabling us to create, transform, and synthesize data in ways previously thought impossible. However, as with any powerful technology, they come with their own set of unique challenges. In this segment, we'll explore these challenges in detail, particularly focusing on implementations of generative models like GANs and their variants, while also providing practical coding examples. So far, we learned that generative models, particularly conditional generative adversarial networks, CGANs, enable the transformation of images from one form to another, such as converting landscape photos into artistic renditions. We discussed the importance of high-quality datasets and the structure of the generator and discriminator networks in the CGAN framework. Additionally, we covered the training process for these models, including loss calculations and the techniques to visualize generated outputs. Moving forward, we will cover the unique challenges faced when implementing these models. Now let's see how we can implement the necessary image loading and transformations for training our generative model. To start, we import the required libraries from PyTorch, specifically datasets and transforms from TorchVision, along with data loader from Torch utils data. The first step in our code is defining a transformation pipeline using transforms compose. This pipeline is crucial because it normalizes the input data, which enhances the model's training efficiency. We first resize the images to a uniform dimension of 64 x 64 pixels, ensuring consistency, and then convert them to tensor format suitable for PyTorch. Following this, we perform normalization, which adjusts the pixel values to a range that simplifies the learning task for the model. This involves scaling the data to have a mean of 0.5 and a standard deviation of 0.5. With the transformation defined, we proceed to load our dataset using the image folder class. This class allows us to easily load images organized in folders, where each folder represents a different class of images. We set the path to our flower images and apply our transformation pipeline. Finally, we utilize data loader to batch our dataset into manageable chunks of 32 images, shuffling them at every epoch to promote diverse learning experiences for the model. Now let's take a look at how we can implement a generator model using PyTorch, specifically designed to include dropout for regularization. In this code, we define a class called Generator, inheriting from the NN module class, which is the foundation for all neural network modules in PyTorch. Inside the init method, we build the generator architecture using a sequential container of layers. The model comprises 3 transposed convolutional layers, which are strategically arranged with activation functions. Each transposed convolution serves to upsample the input data, progressively transforming the lower dimensional tensor into a higher dimensional representation suitable for image generation. The RayLU activation function is applied after the first 2 convolutional layers to introduce nonlinearity, promoting feature learning. To combat overfitting, an issue especially common in GANs, a dropout layer is integrated just before the final output. The dropout layer is set with a rate of 30%, meaning that during training, 30% of the neurons will be randomly ignored, which helps the model to generalize better on unseen data. Finally, the forward method defines the flow of data through the model, indicating how the input tensor is transformed into the final output. This structure aids in developing a more robust generator that can produce diverse and high-quality images. The displayed horizontal bar chart is titled Challenges in Implementing Generative Models and quantifies 7 specific challenges as percentages on the x-axis, 0-30%. The values shown are data quality 25%, training instability 20%, overfitting 15%, computational expense 15%, bias in datasets 10%, scalability 10%, and robustness 5%. Key patterns visible in the figure. Data quality is the single largest concern at 25%, indicating dataset curation is the top priority. Training instability is the second largest at 20%, which directly supports our earlier emphasis on balancing adversarial training and stability techniques. Overfitting and computational expense are tied at 15%, marking them as notable but secondary issues that often require regularization and compute optimization respectively. Bias in datasets and scalability each sit at 10%, highlighting recurring concerns that should be addressed systematically: dataset diversification and distributed training. Robustness is lowest at 5%, suggesting it is less frequently cited relative to other challenges but still non-negligible. From these displayed values, one can conclude that mitigation efforts and resource allocation should focus first on improving data quality and stabilizing training dynamics, then on addressing overfitting and compute efficiency, while still incorporating bias mitigation, scalable architectures, and robustness checks into the development pipeline. Now let's see how we can implement a crucial aspect of training GANs by adjusting the learning rates for the generator and discriminator. In this configuration, we create instances of both the generator and discriminator models, specifying their respective input and output dimensions. To strike a balance during training, the learning rates for the two models are set differently. The generator is assigned a lower learning rate of 0.0001, while the discriminator has a higher rate of 0.0002. This differential learning rate strategy is key in preventing the discriminator from overpowering the generator, which can lead to training instability and mode collapse, where the generator produces a limited variety of outputs. By allowing the discriminator to learn more quickly, we enable the generator to catch up, fostering a more collaborative training dynamic. Both optimizers utilize the Atom optimization algorithm with specified beta parameters, which help in stabilizing learning and ensuring convergence. This setup not only promotes balanced competition between the two models, but also contributes to the effective training of GANs, which is essential for generating diverse and high-quality outputs. Now let's implement a method to evaluate the diversity of generated images. This function, named Evaluate Diversity, starts by randomly selecting a specified number of samples from the generated image set, ensuring that we analyze a representative subset without any replacement. By sampling without replacement, we can gain varied insights into the output diversity. Next, the code assumes there is an existing method, compute feature vectors, which extracts feature vectors from the sampled images. These feature vectors capture essential characteristics or attributes of the images, facilitating the diversity measurement. Once we have the feature vectors, we calculate the standard deviation of these vectors across the sample set. The standard deviation serves as our diversity metric. Higher values indicate a broader range of generated outputs, signifying richer variety, while lower values suggest a lack of diversity in the samples. Ultimately, this monitoring approach is crucial for ensuring that our generative model does not inadvertently reinforce biases or narrow its output range, thus promoting ethical AI development by fostering a more inclusive set of generated images. Now let's see how we can fine-tune a pre-trained RaiseNet model to leverage existing advancements in deep learning. We begin by importing the RaiseNet 18 architecture from the TorchVision library, which provides access to models that have been pre-trained on large datasets such as ImageNet. By setting the pre-trained parameter to true, we can load the model along with its learned weights, allowing us to build on what has already been established. Next, to customize this model for our specific task, we freeze the layers of the pre-trained network to prevent their weights from being updated during training. This step is crucial when we aim to retain the learned features from the original training. We do this by iterating through all parameters of the model and setting requires grad to false. Finally, we replace the last layer of the RaiseNet model, the classification layer, with a new linear layer specific to the number of classes in our dataset. This enables the model to output predictions suitable for our particular application. This approach significantly reduces training time and resource consumption while enhancing overall efficiency, particularly beneficial for projects with limited computational power. Now let's implement a simple setup for distributed training using PyTorch. The first function we define, setup_distributed environment, initializes the distributed training process by calling distinct_process_group with the backend set to nccl. This function is crucial as it enables multiple processes to communicate during training, leveraging the capabilities of GPUs effectively. Following this initialization, we set the specific CUDA device for each process based on its assigned rank. This ensures that each process operates on its designated GPU, optimizing resource utilization and speeding up the training process. Next, we create the trainDistributedModel function, which trains our model using a provided data loader. In this loop, for each batch of data, the model generates outputs based on the input data. Here, you would typically include steps for calculating the loss and performing backpropagation to update the model's parameters. Implementing distributed training in this manner helps manage larger datasets and more complex model architectures efficiently, paving the way for more scalable and high-performance training of generative models. Now let's implement a robust generator model that enhances its resilience by incorporating noise into its inputs. In this implementation, we define a new class called RobustGenerator, which inherits from NN module, a core component of PyTorch that allows us to build neural networks with various layers and functionalities. During the initialization of the class, we call the superclass constructor, which sets up the necessary infrastructure for our neural network. Although this piece of code includes a placeholder for defining the layers, it will eventually include the structure needed for generating outputs. In the forward method, we introduce inherent noise to the input data by generating random values with a specified standard deviation. This noise is added to the input tensor, thereby simulating variations that the model might encounter in real-world scenarios. By training the generator with these augmented inputs, we enable it to learn how to perform effectively, even when faced with data modifications or deviations. This approach not only improves the generalization of the model, but also enhances its performance under varied conditions, making it more robust against potential adversarial attacks or fluctuations in input data. In summary, while generative models like GANs present exciting capabilities for creating stunning images and novel applications, they do come with their set of significant challenges. From needing high-quality data to ensuring diversity and handling computational costs, the landscape is both demanding and rewarding. Throughout this lesson, we've explored common challenges, provided practical code examples, and discussed strategies to mitigate these issues. Generative models represent a marvel of modern machine learning, and with continued learning and adaptation, we can harness their full potential while overcoming the hurdles they present. Whether you're an aspiring AI researcher or a developer seeking to integrate generative approaches into your products, understanding these challenges will set you on a strong footing to navigate the landscape effectively. Thank you for joining me in this deep dive, and I look forward to our next exploration into the fascinating world of generative models. Generative models have become a cornerstone of modern machine learning, particularly in fields such as computer vision and natural language processing. This video will focus on the implementation of generative models in PyTorch, providing a step-by-step guide that combines theory with practical coding examples. So far, we learned that generative models, particularly GANs, offer powerful capabilities in data creation and transformation, but they face significant challenges, including the need for high-quality training data and overcoming issues like overfitting and data bias. We discussed strategies for ensuring good performance, such as utilizing proper transformations, regularization techniques like dropout, and monitoring output diversity. Additionally, we covered the importance of computational efficiency and scalability when training these models. As we move forward, we will delve deeper into addressing these challenges effectively. Next, we will start by setting up our environment to implement the GAN. We will first install essential libraries like PyTorch, TorchVision for handling datasets, and Matplotlib for visualization. This ensures that we have all the necessary tools to proceed with our implementation effectively. Now let's see how we can begin coding our GAN from scratch. We begin by importing the required libraries into our Python script. This includes importing Torch for tensor operations, the NN module for building our neural networks, and the Optim module for optimization functions. Additionally, we import transformations from TorchVision to pre-process our data and Matplotlib for plotting our results. Once the libraries are imported, we can proceed to define our generator and discriminator models. The generator will take a random noise vector and convert it into an image, while the discriminator will evaluate whether an image is real or fake. Using feed-forward neural networks allows both the generator and discriminator to learn complex features necessary for the GAN framework. Next, we set up the training process, where we define hyperparameters such as the size of the noise vector, learning rate, and number of epochs for training. We then load and prepare the MNIST dataset, normalize it, and initialize our models along with their respective optimizers and loss functions, paving the way for the training loop that follows. Now let's implement the generator and discriminator models, which are fundamental components of our GAN. The generator class begins by initializing a sequence of layers designed to transform a random noise vector /z/ into a 28x28 image, suitable for MNIST digit representation. The model uses linear layers, with Ray-LU activations to inject nonlinearity and culminates in a TAN activation, which maps output values to the range of -1 to 1, essential for effective GAN training. Next, we will take a look at the discriminator class, which is responsible for classifying images as real or fake. It flattens the images before passing them through a series of linear layers, employing leaky Ray-LU activations to maintain a small gradient even when units are inactive. The final layer uses the sigmoid activation function to provide a probability score indicating the authenticity of input images. These two classes serve as the backbone of our GAN, allowing one network to generate data while the other critiques it, creating a dynamic adversarial relationship that drives improvement in both models. Now let's implement the training setup for our GAN. First, we define our hyperparameters, which include the dimensionality of the random noise vector, the learning rate for the optimizers, the batch size for training, and the total number of epochs to run. Initializing these parameters is essential, as they directly influence the model's performance and training dynamics. Next, we create a set of transformations to normalize the MNIST dataset, ensuring that the input images have a mean and standard deviation of 0.5. This normalization helps stabilize training and improves the model's convergence. We then load the MNIST dataset using PyTorch's data loader, which also enables shuffling to promote better training through varied input sequences. Following this, we instantiate our generator and discriminator models, ensuring they are set to accept the defined input shapes. For each model, we use the Atom optimizer, known for its effectiveness in training GANs due to its adaptive learning rate features, to optimize their respective parameters. Finally, we establish the loss function as binary cross-entropy, which is standard for measuring the performance of GANs, facilitating clear feedback signals for both the generator and the discriminator during training. Now let's dive deeper into the training loop, where we iteratively enhance both the generator and the discriminator. We start by iterating through each epoch, and for each epoch, we loop through the batches of real images from our data loader. First, we define our labels. Real images are labeled with 1s, while the fake images generated by the generator are labeled with 0s. This labeling is crucial for training the discriminator to distinguish between real and fake data. Next, we train the discriminator by first setting its gradients to 0 to prevent accumulation from previous iterations. We then compute the outputs of the discriminator on the real images and calculate the discriminator loss for real images. Afterward, we generate fake images by sampling random noise and passing it through the generator. We again feed these fake images into the discriminator, computing the loss associated with these. By summing the losses from both real and fake images, we derive the total discriminator loss, which we backpropagate to update the model parameters. Following that, we shift our focus to training the generator. We clear the generator's gradients and pass the fake images through the discriminator to see how effectively the generator has fooled it. The generator's loss is calculated based on how many fake images the discriminator classified as real. Finally, we update the generator's parameters to improve its image generation capabilities. Throughout each epoch, we monitor and print the losses to track the training progress for both networks. The figure titled Training Dynamics of GANs displays two loss curves across epochs 1 to 200, the discriminator loss red and the generator loss blue. The x-axis represents training epochs and the y-axis represents loss magnitude. The red curve for the discriminator shows a generally downward trend from values near 0.5 toward lower values over the training run, indicating that the discriminator's classification confidence improves as epochs progress. In contrast, the blue curve for the generator exhibits an upward trend, moving from similar initial values toward higher loss values over time. Early on, the two curves may be close or intersect, suggesting brief periods of balance, but after those initial epochs they diverge and the gap between them widens. This sustained pattern, low discriminator loss paired with high generator loss, implies the discriminator is consistently outperforming the generator, meaning the generator is receiving larger loss signals and is less successful at fooling the discriminator. The plotted gridlines and legend make it straightforward to pinpoint epochs where divergence accelerates or plateaus. The curves here are relatively smooth with only small fluctuations, indicating steady but imbalanced training dynamics rather than high-frequency oscillations. From these observations, we can conclude that corrective measures, for example adjusting learning rates, changing update frequencies, or introducing regularization and diversity-promoting techniques discussed elsewhere in this lesson, are likely needed to rebalance training and allow the generator to learn more effectively. Now let's implement a function to visualize the images generated by our GAN after training. This function, showGenerated_images, begins by generating a set of random noise vectors which serve as inputs to the generator. Using torch_no_grad ensures that we do not track gradients during the image generation, leading to a more efficient operation and saving memory. The generated images are then moved to the CPU for easier manipulation. Next, we plot the results using matplotlib. The figure size is set to 10 by 10 inches, providing ample space to display the images clearly. A loop iterates over the number of images specified, creating a 5x5 grid. Each subplot displays one of the generated images, which is reshaped and squeezed to eliminate unnecessary dimensions, making it suitable for visualization in grayscale. Lastly, we turn off the axis labels for a cleaner presentation and call plt show to render the images. This process effectively showcases the capabilities of our GAN in generating realistic MNIST digit images, giving us immediate feedback on the model's performance. Now let's implement the following modified discriminator that incorporates mini-batch discrimination. In this class, Discriminator with mini-batch, we extend the functionality of the traditional discriminator. The initialization method accepts a batch size parameter, which allows us to retain information about the size of the mini-batch during training. We then define the core model architecture using a sequence of layers, similar to the traditional discriminator, but adapted to include the additional context from the mini-batch. In the forward method, we combine the input image and the context vector from the mini-batch using torchcat, which concatenates them along the desired dimension. By reshaping the incoming image with respect to the batch size, we ensure that the model effectively considers the distribution of features present in the mini-batch. This modification promotes diversity in the outcomes by allowing the discriminator to learn more robust representations from the batch, ultimately aiding in the generation of varied outputs by the generator during training. Overall, this approach helps alleviate issues like mode collapse, enhancing the performance and effectiveness of the GAN model. As we wrap up this tutorial, remember that while working with generative models in PyTorch can be both exciting and complex, the beauty lies in the iterative process of refinement and adjustment. Generative models harness the power of deep learning to create astounding results, whether it be generating realistic images or producing coherent text. To summarize everything we've covered so far, we dove into the world of generative models and the implementation of GANs in PyTorch. We constructed generator and discriminator networks, set up the training loop, and addressed how to deal with challenges like mode collapse. Along the way, we delved into coding examples that help demystify the theory behind these methods. In the next session, we will further explore more advanced types of generative models, enhancing our knowledge and skills in this fascinating area of machine learning. Happy coding! In this lesson, we will dive into advanced techniques in generative modeling. Understanding these techniques is crucial as they build upon the foundations we have established regarding generative adversarial networks, or GANs. As the generator becomes better at fooling the discriminator, its output increasingly resembles the historical examples it is designed to copy. So far, we learned that generative models, especially GANs, are essential in machine learning for data generation, but come with challenges like mode collapse and the need for quality data. We explored the structure and training of GANs using PyTorch, detailing the generator and discriminator functions and their loss calculations. Additionally, we addressed issues like maintaining diversity in generated outputs through techniques such as mini-batch discrimination. In this session, we will cover advanced generative modeling techniques and how they enhance the performance and applicability of GANs. Now let's see how we can implement the conditional GAN architecture in PyTorch. We begin by defining the conditional generator, which enhances the standard generator by accepting not just a noise vector, but also one-hot encoded class labels. This is achieved by concatenating the noise vector with the labels, allowing the generator to create specific outputs based on the class information provided. The model is built using several fully connected layers with activation functions such as ray-lu, concluding with a tan activation to produce image-like outputs in the range needed for visualization. Next, we implement the conditional discriminator, which follows a similar principle. It takes as input both the generated or real images and their corresponding labels. By flattening the image data and concatenating it with the one-hot labels, the discriminator can effectively evaluate the authenticity of the images in relation to their class membership. This dual input mechanism equips the discriminator to provide a robust feedback loop, enabling the generator to improve in its task of generating realistic images based on specific conditions. With these enhancements, we can guide our GAN to produce targeted outputs, making our models more versatile and capable. Next, we will implement the data loading process necessary for training our conditional GAN. First, we load the MNIST dataset, which contains handwritten digit images, into a dataset object. We use a data transformation to prepare the images and set up a data loader to manage batches during training. The batch size, which dictates how many samples we process at once, can be adjusted based on our computational resources. Now let's define a function, getLabels, which plays a crucial role in generating one-hot encoded class labels. Each label corresponds to a digit class from 0 to 9 and is essential for guiding the generator's output during training. By using PyTorch's torchI function, we create an identity matrix and fetch random class indexes to align with our batch size, ensuring the generator can effectively learn to produce specific digit classes. Moving on to the training loop, we iterate through multiple epochs and continuously retrieve real images along with their associated labels. This setup allows the discriminator to evaluate both real and fake images based on their class, facilitating its learning process. The generated images, crafted using random noise and the sampled labels, are compared against real images to enhance the generator's ability to create authentic digit representations. This interaction lays the foundation for the CGAN's training dynamics, enabling targeted generation of specific categories. Figure 1 displays the training dynamics of a GAN over 200 epochs by plotting discriminator and generator losses as filled areas. The red shaded area represents discriminator loss, and the blue shaded area represents generator loss, with epochs on the x-axis, 1-200, and loss on the y-axis. At the start of training, both losses are centered around ~0, 5, showing comparable initial performance. As epochs progress, the red area discriminator loss shows a clear downward trend, gradually decreasing from approximately 0.5 toward values near 0.1, while the blue area generator loss trends upward, increasing from roughly 0.5 toward about 0.9. Small, rapid fluctuations are visible in both series due to stochastic variation, but the dominant pattern is a steady divergence. The discriminator becomes consistently lower loss, more confident, and the generator accrues higher loss, less successful at fooling the discriminator. The widening separation between the two filled areas quantifies this imbalance over time, and the legend and labeled axes make it explicit which curve corresponds to which network, and that these changes occur across the full 200 epoch window. From these plotted losses, one can conclude that, during this run, the discriminator progressively dominates the game while the generator struggles to reduce its loss, indicating an imbalance in adversarial training that motivates application of the stabilizing and balancing techniques discussed elsewhere in the lesson, for example, normalization, adjusted training schedules, or architecture changes. Now let's implement the base models for our progressive growing of GANs, PGGAN. We start by defining a progressive generator class, which is responsible for generating images at a lower resolution initially. The generator uses a linear layer to project the random input noise to higher dimensional space, and then processes that information through a sequential model composed of ray-LU activations and linear layers. The output is reshaped to form a 4x4 image, allowing the model to initially focus on creating coarse structures. Next, we create the progressive discriminator. This class evaluates the generated images, beginning with a straightforward network that flattens the 4x4 images before passing them through a series of linear layers and leaky ray-LU activations, culminating in a sigmoid output that reflects the likelihood of the input being real or fake. This setup ensures that both the generator and the discriminator can efficiently learn from the smaller resolutions before gradually increasing complexity and image size as training progresses. This technique significantly aids the stability and quality of the generated outputs. Now let's implement the function to grow our generator and discriminator models to accommodate an increased image resolution of 8x8. This function, growModels, begins by defining new layers for both the generator and discriminator, which will enable them to learn and produce higher resolution outputs. For the generator, we create a sequential model consisting of a linear layer that expands the input size from 128 to 512, followed by a ray-LU activation. This is then succeeded by another linear layer that projects the output into the new resolution of 64, which is 8x8, and concludes with a tan activation to shape the output values between -1 and 1. In parallel, we build the discriminator's new layers that follow a similar structural approach. It takes the 8x8 input and transforms it through a series of linear layers, first to 512 units and then reducing it to a single output, which signifies the prediction of the image being real or fake, moderated by a leaky ray-LU and sigmoid function. Finally, we add these newly created layers into the existing generator and discriminator models through the add_module method, allowing our models to progressively improve their capabilities as they generate and evaluate more complex data distributions. This tiered approach enhances the stability of our training process and ultimately results in higher quality generated images. Now let's implement the spectrally normalized discriminator, which employs spectral normalization to stabilize the training of GANs. In this code, we define a class called spectrally normalized discriminator, inheriting from PyTorch's NN module. In the constructor, we initialize a sequential model containing a series of layers that progressively transform the input, starting from flattening the input images to fully connected layers, followed by leaky ray-LU activation functions. This architecture facilitates the learning process of the discriminator, which evaluates real versus generated images. A key function, applySpectralNorm, is invoked to wrap each layer of the model with the spectral normalization utility. This process ensures that the Lipschitz constant governing the discriminator's behavior remains controlled, preventing it from becoming too confident prematurely. As a result, this balance allows the generator to simultaneously enhance its capabilities without being overwhelmed by a dominating discriminator. The forward method defines how images flow through the model, reshaping the input to ensure it fits the expected dimensions. Overall, this implementation supports a more stable and effective adversarial training process. As we conclude our exploration of advanced techniques in generative modeling, keep in mind that the world of GANs is filled with an array of methodologies designed to push the boundaries of what generative models can achieve. From conditioning and progressive growing to stabilizing tricks like spectral normalization, each approach serves as another tool in your toolbox for creating more effective and nuanced generative models. Throughout this lesson, we covered essential advancements in GAN architecture, including conditional provisions for data generation and stabilization methods to ensure effective training. With these techniques at your disposal, you can tackle a wider range of problems in generative modeling, leading to exciting and transformative applications. Embrace these advanced methods as stepping stones toward mastering the art and science of generative modeling. Our next session will further delve into other groundbreaking technologies and refinements that help revolutionize the landscape of machine learning. Happy coding! Generative models have taken the artificial intelligence world by storm, providing powerful applications in image generation, text production, and beyond. However, implementing these models isn't without its hurdles. In this session, we'll delve into the significant challenges that arise during the implementation of generative models and how we can navigate these challenges to achieve effective results. So far, we learned that advanced techniques in generative modeling, particularly conditional GANs, CGANs, allow for more controlled data generation by incorporating class labels into the generator and discriminator architectures. We also explored progressive growing of GANs, PGGAN, which improves stability and quality by gradually increasing image resolution during training. Spectral normalization was introduced as a method to stabilize discriminator training and ensure balanced learning between the generator and discriminator. These advancements enhance the effectiveness and applicability of GANs in various machine learning tasks. Now we will cover the challenges in implementing generative models and how we can address them. Now let's take a look at how we can load a dataset for our generative model using PyTorch's TorchVision library. The code begins by importing the necessary libraries, specifically Torch and TorchVision datasets, along with TorchVision transforms. This sets us up to both load and preprocess image data efficiently. Next, we define a function called loadDataset, which takes a directory path data_dir as its input. Within this function, we first create a transformation pipeline using transforms compose. This pipeline resizes images to 64x64 pixels, which is a standard input size for many neural networks, and converts the images into tensors, a format suitable for PyTorch operations. We then load our dataset using datasets image folder, which expects the data directory to be structured in a way where images are organized into subdirectories representing their classes. The transformation we defined earlier is applied to each image as it is loaded. Finally, the dataset is returned to be used in model training. This approach ensures that we have a well-categorized and appropriately preprocessed dataset, which is pivotal for the performance of our generative model. Now let's take a look at how to implement the optimization setup for both the generator and discriminator in our GAN model. We begin by importing the Atom optimizer from the PyTorch library, which is a widely used optimizer due to its efficient performance in training deep learning models. Next, we define our generator and discriminator models, represented by placeholder comments. It is crucial to have these models properly defined before proceeding to set up the optimizers. Following this, we initialize two optimizer instances, OptimGen for the generator and OptimDisk for the discriminator. The generator's learning rate is set to 0.0002, which allows it to learn effectively while generating data. In contrast, the discriminator is assigned a slightly lower learning rate of 0.0001. This strategic difference in learning rates is essential. It helps to ensure that the discriminator remains more responsive than the generator during training. This balance is particularly important in the adversarial training process, as it prevents issues such as mode collapse. Additionally, both optimizers are instantiated with beta parameters of 0.5, 0.999, which are typical settings that help stabilize the training process. Now let's implement a transfer learning approach using a pre-trained model to aid in our generative modeling tasks. First, we import the necessary libraries, specifically leveraging the TorchVision library, which includes several pre-trained models beneficial for our purpose. Next, we initialize the RaiseNet18 model, specifying that we want the pre-trained weights. This means the model has already been trained on a large dataset, allowing us to utilize its learned features. By doing so, we can save both training time and computational resources, as we are building upon an established foundation rather than starting from scratch. To customize the model for our specific dataset, we freeze the parameters of the pre-trained model. This step ensures that the weights from the original training are retained and not updated during our training process. We do this by iterating over the model's parameters and setting requiresGrad to false. Finally, we modify the last fully connected layer of the model to align with the number of classes in our dataset. This crucial adjustment allows the model to output predictions relevant to our specific task, while still taking advantage of the extensive features learned from its previous training. This technique is a powerful way to enhance performance and efficiency in generative modeling scenarios. The displayed bar chart titled Challenges in Implementing Generative Models maps 5 challenge categories on the x-axis to an impact level 1.5 on the y-axis, with numeric labels shown above each bar. Dataset quality equals 5, training complexity equals 4, computational costs equals 3, output interpretability equals 4, and ethical concerns equals 2. The most prominent pattern is that dataset quality reaches the maximum impact level 5, indicating it is the top priority. This supports the earlier emphasis on diverse, well-preprocessed data as the foundation for successful generative modeling. Training complexity and output interpretability are tied at a high impact 4, highlighting that both the difficulty of adversarial training dynamics and the need to make outputs semantically meaningful are equally critical concerns that demand attention during model design and evaluation. Computational costs sit in the middle at 3, confirming that while resource demands are substantial, they are not ranked as the greatest single barrier when compared to data and algorithmic complexity. This aligns with mitigation strategies like transfer learning and cloud GPUs that can reduce this burden. Ethical concerns score lowest at 2 in this chart, which suggests that, within the scope of measured implementation impact, practical technical challenges tend to dominate decisions and resource allocation, though ethical issues remain present and should not be ignored. Taken together, the chart implies a prioritization strategy. Focus first on obtaining and curating high-quality datasets, concurrently invest in stabilizing training and improving interpretability, and then address computational scaling and ethical frameworks as integral but secondary steps. Now let's take a look at a function that calculates the Fréchet inception distance (FID) score, an essential metric for evaluating the quality of generative models. The function calculateFID takes as input 2 sets of samples, real samples from your dataset and generated samples from your model. Inside the function, we first compute the mean and covariance of both sets of samples. The mean is calculated using NP, mean, which gives us the average values for each dimension, while NP, cov, computes the covariance matrix, which describes how the dimensions vary together. These statistics are crucial as they help us understand the distribution of the samples in high-dimensional feature space. Next, we compute the FID score itself. This score combines the squared difference between the means of the real and generated samples with the trace of a matrix involving their covariances, using the sqrtm function from the SciPy linalg package to perform a matrix square root. A lower FID score indicates that the generated samples are more similar to the real samples, providing insight into the generative model's performance. Regularly evaluating the FID during training enables you to monitor improvements and guide optimization efforts effectively. Lastly, the issue of ethical concerns in the utilization of generative models cannot be overlooked. As generative models become increasingly sophisticated, they raise questions about the potential for misuse, such as creating deepfakes or other misleading visual content. It's crucial for developers to remain conscientious about how they use these models and to develop frameworks that promote ethical usage. Engaging with the community and fostering discussions about the ethical implications of generative models can help promote responsible usage. Implementing policies and guidelines during model development is essential for ensuring that your work adheres to ethical standards. As a budding machine learning practitioner, always ask yourself, what are the potential consequences of my work, and how can I ensure it benefits society? To wrap up, implementing generative models presents a myriad of challenges, from dataset complexity to ethical considerations. Throughout this discussion, we've explored strategies to tackle each of these hurdles, including balancing training dynamics, leveraging computational resources effectively, evaluating model quality quantitatively, and promoting responsible usage in a rapidly evolving landscape. Effective communication within the community and continuous learning will only foster further improvement as you embark on your journey into the world of generative models. Embrace these challenges as opportunities for growth, and you will not only enhance your skills but also contribute positively to the field. Keep experimenting, stay curious, and remember that every challenge is a stepping stone toward innovation. Generative models have revolutionized how we create and manipulate data across various industries, bridging gaps between different forms of information by learning complex mappings. Today, we'll delve into the advancements in generative models, particularly how they can learn to map one type of image to another. So far, we learned that generative models, particularly GANs, face numerous challenges, including the necessity for large and diverse datasets, complexities in training dynamics, computational costs, and the need for effective output interpretation. We discuss the importance of dataset quality in model performance and strategies like adjusting learning rates and using transfer learning to balance training. Quantitative metrics such as Frachet inception distance (FID) help evaluate the quality of generated outputs. Lastly, ethical considerations in the use of generative models are crucial for promoting responsible development and usage in AI applications. Now, we will cover the exciting advancements in generative models across various industries and how they are reshaping the landscape of content creation, healthcare, fashion, and more. The included horizontal bar chart, titled Advancements in Generative Models Across Industries, presents impact levels on a 1-5 scale for 5 industries: healthcare 4, art and design 5, fashion 4, video games 3, and finance 2. Each industry is represented by a horizontal bar with its numeric value annotated at the bar end, and the x-axis labeled Impact Level 1-5 quantifies the measured effect. Key patterns are clear. Art and design has the highest reported impact, 5. Healthcare and fashion share the next highest level, both 4. Video games shows a moderate impact, 3, and finance is lowest, 2. From these displayed values, we can conclude that generative models are currently perceived as most impactful in creative domains and strongly influential in healthcare applications, while financial applications are represented as having lower current impact. The ordering of industries on the vertical axis is not sorted by impact, so direct comparison should rely on bar lengths and their numeric labels. Now let's implement the function to load and pre-process images, which is essential for our neural style transfer application. The load image function begins by opening the specified image file, providing easy access to image data. It then uses a series of transformations to resize the image to a uniform 512 x 512 pixels, ensuring consistency across inputs. This resizing is crucial for feature extraction using the VGG network, which expects specific input dimensions. Once resized, the image is converted into a tensor format, which is the standard input for PyTorch models. Normalization follows, where we adjust the pixel values based on the pre-trained VGG model's expectations, with specific mean and standard deviation values derived from the ImageNet dataset. These normalization parameters help the model accurately interpret the input data by aligning it with the distributions of training images. Finally, we add a batch dimension to the tensor, preparing it for processing in the neural network. This entire process ensures that our images are suitably formatted and ready for the feature extraction phase, which we'll implement next. Next, we will implement a function to extract features from our input images using the VGG model, which is central to our style transfer process. This function, named getFeatures, takes an image and a pre-trained model as inputs. Inside the function, we define a dictionary mapping specific layers of the VGG network to more meaningful names, indicating which layers we will use for content and style extraction. The function then initializes an empty dictionary called features to store the extracted features. We start by passing the input image through the model layer by layer. For each layer, if its name matches one of our predefined layers, we save the output to our features dictionary. This way, we can later access the content and style features that are extracted from the designated layers. The choice of layers ensures we effectively capture both the high-level content and the intricate style details of the respective images. Finally, the function returns the features dictionary, ready to be used in the computation of loss during the optimization process, allowing us to assess how well our generated image retains content and style attributes. Now let's implement the content and style loss functions, crucial for training our style transfer model. First, we define the content loss function, which calculates the difference between the content features of the generated image and those of the original content image. This is achieved using the mean squared error method, focusing on a specific layer, conv42, of the VGG model that captures essential content information. Next, we need a way to quantify the style loss, which reflects how much the generated image differs from the style image. To do this, we implement the gram matrix function. The gram matrix captures correlations between features from different layers and helps characterize the style of an image. It processes the input tensor by reshaping and performing a batch matrix multiplication to compute the gram matrix effectively. Now let's see how we can combine these concepts in the style loss function. This function iterates through selected layers of the VGG model, calculating the gram matrix for both target and style features. By summing the squared differences of these matrices, we derive the overall style loss. Together, these loss functions will guide the optimization process, balancing content and style during image generation. Now let's implement the optimization loop, which is crucial for the style transfer process. In this section, we begin by loading both our content and style images using the previously defined loadImage function. We're initializing the generated image as a clone of the content image, enabling it to adjust while also requiring gradients for optimization. The optimizer chosen here is LBFGS, which is suitable for our task as it helps efficiently minimize the loss through its iterative steps. Next, we set up the model by loading the pre-trained VGG19 network, focusing on its feature extraction capabilities. We proceed to extract features for both the content and style images using our defined getFeatures function, which collects relevant layers for comparison during loss calculation. Now let's delve into the optimization loop, which runs for 300 iterations. The closure function within this loop computes the content and style losses after resetting the gradients for our generated image. By applying a weighted sum to these losses, we define our total loss that guides how the image should evolve. Every 50 iterations, we print the total loss, giving us visibility into the optimization process. At the end of this iteration, a new image emerges, beautifully blending the content from one image with the style from another, showcasing the essence of neural style transfer. Now let's implement the foundational components of a generative adversarial network, GAN, using PyTorch. We begin by defining the generator model, which is responsible for producing synthetic data. This model consists of a series of dense layers with RayLU activation functions to introduce nonlinearity, allowing it to learn complex mappings. It takes a random noise vector as input and aims to generate samples that resemble real data. The output layer utilizes the TAN activation function to ensure the generated images are scaled correctly, assuming we're working with 1D images for simplicity. Next, we define the discriminator, which evaluates the authenticity of the images. Similar to the generator, it comprises dense layers coupled with leaky RayLU activations, designed to effectively classify inputs as either real or fake. The discriminator's output layer employs a sigmoid activation function, allowing it to output a probability score that determines whether the input image is genuine or generated. Together, these components illustrate the competitive nature of GANs, where the generator's goal is to deceive the discriminator into misclassifying its outputs as real data. This setup provides a robust foundation for training a GAN to create convincing synthetic images. Next, we will implement the core training loop for our generative adversarial network, GAN, where both the generator and discriminator learn from each other. We begin by initializing our generator and discriminator models, along with defining the binary cross-entropy loss criterion essential for evaluating the performance of both models. Now let's see how we can set up the optimizers for each model, using the Atom optimizer with specified learning rates and beta values to control momentum. The training process involves iterating over a fixed number of epochs and processing a batch of images to ensure the generator and discriminator are trained alternately. In each iteration, we first zero the gradients for the discriminator, then load a batch of real images and create corresponding labels indicating they are real. The discriminator computes its output on these images, allowing us to calculate the loss based on the disparity between the predicted and actual labels. Next, we generate fake images from random noise, again evaluating the discriminator's output to compute the loss for these samples. After completing the discriminator's training step, we shift our focus to the generator. Here, we want to maximize the discriminator's error in classifying fake images as real, so we adjust the gradients accordingly. Finally, every 10 epochs, we print the losses of both models to monitor their training dynamics and ensure they are progressing in balance. Now let's implement the fashion generator, a crucial component for generating new clothing designs using deep learning. In this implementation, we define a class that inherits from NN module, which is standard practice in PyTorch for building neural network models. The init method initializes our generator, setting up a sequential model composed of transposed convolution layers. Each layer plays a significant role in upsampling the input latent vector, which represents a compressed form of the learned features. We begin with a randomly initialized latent vector of size 100, feeding it into the first transposed convolution layer that scales it up to 128 feature maps. The use of RayLU activation functions introduces nonlinearity, allowing the model to learn complex representations of fashion items. This process continues through additional layers, 64 and 32 feature maps, each progressively refining the generated output. Finally, we use another transposed convolution layer to transform the feature representation into a 3-channel RGB image format, suitable for visualizing clothing items. The tan activation function at the end ensures that the output pixel values range between -1 and 1, aligning with common normalization practices for image generation. This architecture provides a foundational element for creating novel fashion designs through generative modeling. Similar to our earlier examples, the discriminator would be set up to classify images as real or generated. Training this model would follow the same principles as the previous GANs we covered, adapting the dataset and parameters to focus on fashion-related images. This opens doors to innovations in fashion design, allowing for rapid prototyping and disruptive change. In conclusion, the advancements in generative models are paving the way for numerous innovative applications across diverse industries. From enhancing artistic expressions through style transfer to creating synthetic medical images for training and fashion design, the potential is vast. As we continue to investigate these technologies, it's crucial to consider ethical implications, dataset quality, and maintaining a balance in model training. Embracing these challenges not only enhances our skills but contributes to the future of generative modeling. Keep exploring, keep creating, and always challenge the boundaries of what's possible with AI. Generative models like generative adversarial networks, or GANs, have opened a new frontier in data generation and manipulation. As we explore their capabilities, one critical aspect that we must address is how we evaluate these models. Unlike traditional models that produce a single numerical output, generative models create complex data, images, music, text, where accuracy isn't as straightforward. So let's dive deep into the realm of generative models evaluation metrics, a significant area that will enhance our understanding and application of these powerful techniques. So far, we learned that generative models, particularly GANs, have transformed data creation and manipulation across various industries while facing challenges in training complexity and dataset requirements. We've explored how these models can be used for style transfer in creative industries and for generating synthetic medical images to aid in healthcare. We've also touched on the fundamentals of GAN architecture and training, emphasizing their applications in fashion design and the importance of ethical considerations. With that foundational knowledge in mind, we will now cover generative models evaluation metrics, unpacking their complexities and discussing approaches to ensure our model's efficacy. Let's begin by addressing why evaluating generative models differs significantly from conventional models. In traditional machine learning, model accuracy is often calculated using well-defined metrics like accuracy, precision, and recall based on predictions against true labels. However, when we're generating data, the situation becomes more nuanced. We aren't just predicting a single value, we're creating whole datasets or images, making it challenging to have a one-size-fits-all metric. The evaluation of generative models typically revolves around several strategies, including visual fidelity assessments, statistical tests, and downstream task performance. For instance, we might visually inspect generated images to see how closely they resemble real images. However, a visual inspection can be subjective, which is why we often turn to more quantitative metrics. Now let's implement the inception score calculation, which is crucial for evaluating the quality and diversity of generated images. The code begins by importing the necessary libraries, including NumPy for numerical operations and Keras utilities for handling the Inception v3 model, which will provide us with class predictions. Next, we define the function calculateInceptionScore, which takes a list of generated images as input. Inside the function, we load the pre-trained inception model. We then initialize an empty list to store the prediction scores for each image. For each generated image, we pre-process it to fit the inception model's requirements and convert the image to an array format suitable for prediction. Afterward, we expand the dimensions of the image array to meet the input shape expected by the model and call the model's prediction method to retrieve the class probabilities for that image. These probabilities are stored in the scores list. Once we've processed all images, we convert the scores list into a NumPy array for further analysis. Finally, we calculate the mean and variance of the predicted probabilities using those to compute the inception score. This score provides insights into how well our generative model is performing, with higher values indicating better diversity and quality in the generated images. Now let's implement the following code to calculate the Frechet inception distance, FID, between real and generated images, which provides a quantitative measure of their similarity. The function begins by loading a pre-trained inception v3 model, which is essential for extracting features from the images. We then predict the activations for both the real and generated sets of images, capturing the underlying features that define their distributions. Once we have the activations, we calculate the mean and covariance for both sets. These statistics are critical because the FID metric evaluates the similarity of the two distributions based on these measures. The squared difference in their means is computed to understand how far apart the centroids of both distributions are. Following this, we calculate the covariance matrix's square root using the Schur decomposition, which is integral to the final FID score. The FID score itself is obtained by combining the mean difference and the trace of the covariance matrices, offering a single value where lower scores indicate closer similarity. Ultimately, this function encapsulates the FID computation, enabling a robust evaluation of generative models' performance in generating realistic images. The displayed figure titled Evaluation Metrics for Generative Models is a vertical bar chart that directly compares four evaluation values: inception score IS at 8.5, Frechet inception distance FID at 20, user study rating at 4.5, and downstream task accuracy at 75. Each bar has its numeric value annotated above it. The x-axis lists the metric names, and the y-axis is labeled score/distance. Key patterns visible in the chart are: the downstream task accuracy bar is dramatically higher than the others, 75 versus single or low double-digit values, indicating that generated samples perform strongly when used in a downstream classification task. The inception score of 8.5 sits at a moderate to high level, implying reasonable sample quality and diversity according to a classifier-based metric. The FID value of 20, which is plotted as a higher bar but is a distance metric where lower is better, therefore indicates a moderate distributional gap between generated and real data, and the user study rating at 4.5, shown near the top of its scale, signals strong human-perceived quality. From these data, we can conclude that the model's outputs are highly effective for downstream tasks and are perceived positively by users, while there remains measurable statistical divergence from real data as captured by FID. The figure thus reinforces the lesson point that multiple complementary metrics, each with its own scale and optimization direction, are necessary to form a complete evaluation of generative performance. While both inception score and FID have their merits, they are not without their challenges. For instance, inception score may give high values for images that are far from the real distribution but have high confidence in classifications, potentially misleading evaluations. FID, while often more reliable, can also suffer from the choice of the pre-trained model and the nature of the data. In practice, it's essential to use a combination of metrics to gain a holistic view of model performance. For example, we might evaluate generated samples in terms of their effectiveness in specific downstream tasks, like image classification or style transfer applications. This evaluation can illuminate how well the model learns to generate meaningful content beyond visual fidelity. Now let's implement a simple convolutional neural network, CNN, using PyTorch to evaluate the effectiveness of our generated images through a classification task. First, we define the simple CNN class, which inherits from NN module. Inside its init method, we initialize a convolutional layer to extract features from our images, followed by a max pooling layer to reduce the spatial dimensions. This structure allows the model to capture essential patterns while minimizing overfitting. The fully connected layers follow, where the first layer maps the flattened output of the convolutional layer to a smaller size, and the final layer outputs predictions for 10 classes, reflecting a typical classification scenario. The forward method defines the forward pass through the network, applying the convolution, activation function, pooling, and the final linear transformations effectively. Next, we implement the train model function, which will handle the training process. This method iterates over a specified number of epochs, traversing through the training data. It computes the loss using cross-entropy, performs backpropagation, and updates the model's parameters using the defined optimizer. Overall, this implementation equips us with a foundational classification model to assess the quality of the images produced by our generative model. Another significant aspect of evaluating generative models lies in user studies and qualitative assessments. Especially in fields like art or design, subjective measures often play a vital role. User studies can provide insights into how real users perceive the generated content, assessing creativity or aesthetic quality. Including generators in a competition or gathering user feedback can help to supplement quantitative metrics with human perspectives. As we move forward in this exciting field, integrating qualitative and quantitative evaluations offers a comprehensive evaluation framework, essential for understanding the impact of generative models. As you embark on your own journey with generative models, remember to choose metrics that align with your goals, whether that's visual fidelity, diversity, or practical application success. In conclusion, the evaluation of generative models is a multifaceted issue that demands careful consideration. As we've covered, metrics like inception score and Frechet inception distance provide useful quantitative frameworks, while leveraging downstream task performance and user studies can enhance our evaluation approach. Each metric provides unique insights, and a combination thereof allows for a robust understanding of a model's generative capabilities. As you dive into working with your generative models, remember that the metrics you choose shape your understanding of model performance and will greatly influence your creative outcomes. The complexity of evaluating generative models reflects the intricate nature of creativity itself, threading science with art. Keep experimenting, keep iterating, and revel in the journey of generating remarkable data. Now let's take a look at the basic structure of our GAN model, which includes the generator and discriminator classes. We begin by defining the generator class, where we set up a neural network with two feed-forward layers. The first layer transforms the latent vector into a higher dimensional space, followed by a RayLU activation function, and then a second layer that produces output data formatted with a TAN activation function, which is suitable for generating images. This design allows the generator to create diverse outputs from random latent noise. Next, we define the discriminator class, mirroring the generator's architecture but with distinctions appropriate for its role. It utilizes similar layers but outputs a single value between 0 and 1 using a sigmoid activation, representing the likelihood that an input image is real. The discriminator's role is crucial, assessing the generator's outputs against real data. After establishing these components, we set hyperparameters, including the latent vector size and output dimensions for MNIST images. We also initialize our models and select the binary cross-entropy loss function with atom optimizers for both networks. This setup serves as the foundation for training our GAN and tackling the inherent challenges we discussed earlier. The figure titled Key Challenges in Generative Models is a bar chart that quantifies the relative impact levels of 5 common challenges. From left to right, the chart displays training instability at 25%, mode collapse at 40%, data relevance at 30%, overfitting at 35%, and computational resources at 20%. The numeric labels on top of each bar make the differences immediately apparent. Mode collapse is the most pronounced issue, 40%, followed by overfitting 35% and data relevance 30%, while training instability and computational resource demands register lower but still non-negligible impact levels, 25% and 20% respectively. The y-axis showing impact level percent, and the grid lines allow for easy visual comparison. Mode collapse exceeds computational constraints by 20 percentage points and exceeds training instability by 15 points. From this visualization, we can conclude that efforts to improve generative models should prioritize strategies that reduce mode collapse and overfitting and also address data relevance. Although training instability and computational costs are lower in relative impact here, they remain important and interact with the higher impact issues, indicating a need for a balanced mitigation plan across these areas. Now let's see how we can implement dynamic learning rate adjustment in our training loop. The function adjust learning rate is designed to modify the learning rate of the optimizer based on the current epoch. This technique helps in stabilizing training by reducing the learning rate at specified intervals, in this case, every 50 epochs. When such adjustments are made, it can help slow down the learning of the model that is performing well, encouraging a more balanced competition between the generator and discriminator. Next, we will look at label smoothing, a technique employed to enhance the stability of the discriminator during training. By setting the real labels to a value slightly less than 1, specifically 0.9, we introduce a level of uncertainty about the real data. Simultaneously, maintaining the fake labels at 0 allows the discriminator to avoid being overly confident in its predictions. This approach serves to prevent the discriminator from dominating the training process and maintains an effective adversarial training dynamic. By integrating these two techniques, we can significantly enhance the stability and effectiveness of our generative model training. Now let's take a look at the mini-batch discrimination class, which is pivotal in our efforts to counter mode collapse in generative models like GANs. This class extends the NN module provided by PyTorch, enabling us to incorporate a mini-batch discrimination layer into the discriminator. The constructor initializes the layer, where we define the number of classes for the mini-batch discrimination and create a parameter matrix, weights, that holds random values scaled to the input dimension and the number of classes. This matrix will be learned during the training process, adjusting to the diversity found within the generated outputs. In the forward method, we handle the model's core operations. Here, we calculate the differences between every pair of samples in the mini-batch by creating a two-dimensional tensor. This is followed by computing their squared differences and applying an exponential decay function, which effectively captures the differences in output quality between samples. Finally, we sum these distance values, yielding an output that assesses the diversity of the batch. By incorporating this layer, we facilitate the generator in exploring a wider range of samples, significantly reducing mode collapse and improving the variety of outputs. Now let's see how we can implement data augmentation using PyTorch's TorchVision library to enhance the quality of our training dataset. The code begins by importing the necessary transforms module from TorchVision, which provides a suite of image transformation functionalities. Next, we compose a series of transformations using the transforms compose method. Here we include 3 transformations: a random horizontal flip, which flips the images with a probability of 50%, a random rotation of up to 30 degrees, and finally, a conversion of the images to tensor format with transforms to tensor. This combination of transformations allows us to enrich the training data by introducing variability in the images, making our model more robust and better able to generalize. To apply these transformations, you would typically pass the transform parameter when creating your dataset class, as suggested in the commented line. By augmenting our images in this manner, we effectively increase the diversity of our training set, helping the generative model to learn from a broader range of scenarios, which can ultimately lead to better and more relevant outputs during the generation process. Now let's implement a generator class, a fundamental component of our GAN model, which will learn to generate data from random noise. This class inherits from the PyTorch NN module, allowing us to leverage its capabilities for building neural networks. In the constructor, we initialize the model as a sequential stack of layers. The first layer is a linear transformation that maps the input dimension, which corresponds to our latent vector size, to 128 features. This is followed by a RayLU activation function, which injects nonlinearity into the model, helping it to learn complex patterns in data. To combat overfitting, we incorporate a dropout layer configured with a probability of 0.3. This randomly disables 30% of neurons during training, forcing the model to learn more robust features that generalize better to new data. The final layer transforms the resulting 128 features to the output dimension, which corresponds to the size of the generated data, employing the TAN activation function to ensure that the output is scaled between -1 and 1. This structure not only facilitates the generation of data, but also introduces regularization, enhancing the model's ability to produce diverse and novel outputs. Now let's implement a simple data loader using PyTorch to manage our dataset efficiently. The first step in our code is to import the data loader class from the Torch utils data module. This utility allows us to easily load our dataset in manageable batches, which is particularly beneficial when working with large sets of data, such as in the case of training GANs. Assuming we have already defined our dataset, we create an instance of data loader, setting the batch size to 32 and enabling shuffling of the data. This means that during each training epoch, the order of the samples will change, which helps the model generalize better by not learning any specific ordering patterns from the dataset. In the next part of the code, we have a for loop that iterates over the data loader. Within this loop, we retrieve batches of images to feed into our model for training. By using this approach, we can leverage parallel computation, making the training process more efficient and allowing us to better manage our computational resources. This integration of batch processing is crucial for optimizing our model's performance, particularly when dealing with complex architectures and extensive datasets, as we discussed earlier. In summary, implementing generative models involves navigating a complex landscape of challenges, including training instability, mode collapse, data relevance, overfitting, and computational constraints. By employing strategies such as dynamic learning rates, minibatch discrimination, data augmentation, and regularization methods, we can tackle these challenges effectively. Now equipped with this knowledge, I encourage you to explore the nuances of generative modeling further. Take your time experimenting with these concepts, coding up solutions, and applying what you've learned in real-world scenarios. Remember, the world of generative models is vast and exciting. You have the tools to unlock its full potential. So, keep pushing your boundaries and generating incredible data. Happy coding! Generative models are revolutionizing the art world, allowing artists and technologists to explore creativity in unprecedented ways. One exciting application is the recovery of lost artworks using these models, which has the potential to reshape our understanding of art history. So far, we learned about the revolutionary impact of generative models, particularly GANs, in machine learning, along with related challenges like training instability and mode collapse. We've also discussed the significance of evaluation metrics for generative models and explored techniques to enhance stability and diversity in outputs, along with strategies to address issues related to data relevance and computational efficiency. Now we will dive deeper into advanced applications of generative models in art, showcasing how they can uncover hidden masterpieces and influence artistic expression. Now let's see how we can implement a simple convolutional neural network, CNN, using PyTorch for the analysis of painting layers. We start by creating a class called SimpleCNN, which inherits from NN module, allowing us to define our model structure effectively. Inside the constructor, we initialize two convolutional layers, conv1 and conv2, which will learn spatial hierarchies via filters. The conv1 layer takes in a single channel input, typical for grayscale images, while outputting 32 feature maps. We also introduce a pooling layer to downsample the feature maps, which helps in reducing the dimensionality and computational load. Following the convolutional layers, we have two fully connected layers, FC1 and FC2. The first fully connected layer transforms the output of the second convolutional layer into 128 dimensions, ultimately leading to the FC2 layer that classifies these features into 10 distinct categories, assuming we are working with a dataset of 10 classes. In the forward method, we define how input data flows through the network. The input is passed through the convolutional layers, followed by the defined activation functions and the pooling layers, ensuring we extract relevant features before classification occurs in the fully connected layers. This structured approach allows our model to learn and make predictions based on the complex features found within artworks. The figure titled Key Applications of Generative Models in Art is a vertical bar chart that quantifies the relative impact percent of 6 concepts: artwork recovery 30%, generative adversarial networks GANs 25%, variational autoencoders VAEs 20%, diffusion models 15%, conditional generation 10%, and image synthesis 5%. The x-axis lists these concepts and the y-axis measures impact percent with grid lines to aid comparison. Each bar has a numeric label at its top showing the exact percentage value, and the labels on the x-axis are rotated for readability. From the displayed data, we see a clear descending pattern. Artwork recovery is the single largest category at 30%, followed closely by GANs at 25% and VAEs at 20%. The top 3 categories together account for 75% of the plotted impact, and the top 4 reach 90%, indicating that recovery and core generative architectures dominate the represented applications. Diffusion models and conditional generation hold moderate shares, 15% and 10% respectively, while image synthesis is the smallest slice at 5%. These proportions support the lesson's emphasis that recovery tasks and well-established generative approaches, GANs, VAEs, are central to current art-focused work, that diffusion and conditional methods are meaningful but less dominant in this snapshot, and that pure image synthesis, while present, is a smaller component relative to recovery and model-driven analysis. Now let's see how we can implement data augmentation techniques to enhance our dataset for training the CNN. The code utilizes the TorchVision library, specifically the transforms module, which is pivotal in applying various image transformations. By composing a series of transformations using transforms, compose, we define a pipeline that processes our images. The first transformation, transforms random horizontal flip, randomly flips the images horizontally, which helps the model learn to recognize artworks regardless of their orientation. Next, transforms random rotation 10, introduces random rotations up to 10 degrees, allowing the model to become invariant to slight angle variations. The transforms color jitter is crucial for adjusting parameters like brightness, contrast, saturation, and hue. This alters the color properties of images slightly and further diversifies the dataset, enabling the CNN to learn robust visual features. Finally, transforms to tensor converts the images into PyTorch tensors, which is essential for inputting the data into the CNN. By integrating these transformations into our dataset preparation, we substantially improve the model's ability to generalize and accurately distinguish between artworks, particularly when dealing with subtle variations in paint layers. Now let's see how we can implement the generator and discriminator architectures for our GAN model. The generator is designed to take a random noise vector as input, which it transforms into an image of 28 x 28 pixels. This size matches the MNIST dataset. It consists of several fully connected layers with Ray-LU activations, ultimately outputting the generated image through a TAN activation function that normalizes the pixel values. In this architecture, the sequential nature of layers enables the generator to learn complex features progressively as it transforms the noise into recognizable images. Next, we will write the discriminator, which serves as the evaluator of the generated images. This network also employs fully connected layers with leaky Ray-LU activations, which help in mitigating the vanishing gradient problem often encountered in neural networks. The final output layer employs a sigmoid activation to produce a probability score, indicating whether the input image is real or generated. By training these two models in tandem, we optimize the generator to create improved images while simultaneously enhancing the discriminator's ability to differentiate between genuine and synthesized artworks, fostering a collaborative learning process that gradually improves results on both sides. Next, we will implement the training loop for our GAN, which is crucial for optimizing both the generator and discriminator in tandem. This function begins by setting up the loss function and the optimizers for each network using the Atom optimizer, which is well suited for training deep learning models. The loop runs for a specified number of epochs, iterating over the data provided by the data loader. During each epoch, we first retrieve a batch of real images. The labels for these real images are set to ones, while the labels for the generated fake images will be set to zeros. We then enter the process of training the discriminator. By calling optimizer D0grad, we clear any previous gradients. The discriminator processes the real images, and we calculate the loss based on its output compared to the real labels, followed by backpropagating this loss to adjust the discriminator's weights. Next, we generate fake images by feeding random noise to the generator and again compute the discriminator's loss using the fake images, this time ensuring we do not update its parameters during the generator's phase of training using detach. After training the discriminator, we proceed to update the generator. We clear the gradients for the generator and calculate its loss based on the discriminator's output on the fake images, aiming for a generator that can effectively fool the discriminator. This back-and-forth training is what ultimately leads both networks to improve and generate increasingly realistic art pieces. Logs of the losses are printed out periodically, which helps us track the training progress. Now let's take a look at how we can implement a conditional generative adversarial network, CGAN, to create art influenced by specific conditions or styles. We begin by defining the conditional generator class, which extends a neural network module. This generator combines the input noise vector with conditional label information, allowing it to produce images that align with the specified characteristics. It uses a series of fully connected layers, where the first layer accommodates both the noise and labels, followed by activation functions to introduce nonlinearity. Next, we define the conditional discriminator, which similarly incorporates the condition as part of its input. This model evaluates the authenticity of the generated images based on the combined features of the images and labels. Utilizing varying activation functions, such as LeakURLU and Sigmoid, these networks collectively enhance the model's ability to interpret artistic styles, enabling the generator to produce diverse outputs tailored to specific themes or moods. This dual model setup facilitates a more directed form of artistic creation, ensuring that the generative process aligns with defined creative goals. As we see the impact of generative models in art continues to expand, the potential for future development is truly exciting. From discovering lost masterpieces to collaborating with artists and creating innovative artwork, the intersection of technology and creativity opens doors to artistic avenues previously unimaginable. The canvas of generative models is vast, and every stroke, be it by a machine or a human, further enriches the narrative of art history. In our next discussion, we will venture beyond the aesthetic realm, exploring how generative models influence various domains such as music, literature, and design. The potential of these models continues to broaden our horizons and redefine creativity for generations to come. Generative models are transforming the landscape of natural language processing, enabling machines to create human-like text with remarkable fluency. However, despite their impressive capabilities, there are significant challenges that we must address when implementing these models effectively. So far, we learned about the transformative role of generative models in the art world, focusing on their ability to recover lost artworks and enhance artistic expression. We've also examined the technical aspects of using convolutional neural networks (CNNs) to analyze paintings and explored the implementation of generative adversarial networks (GANs) for both generating and evaluating art. Additionally, we've touched upon the innovative potential of conditional GANs, allowing for the creation of artwork based on specific styles or themes. Our journey into how these models redefine creativity will continue as we look into their implications in other creative fields. Now we will talk about the future challenges of generative models, specifically in the realm of natural language processing. Now let's dive into the code that implements an LSTM-based text generator. We begin by importing the required libraries, including PyTorch for building our neural network. The LSTM text generator class is defined to encapsulate the architecture of our model. In the constructor, we initialize an embedding layer to convert word indices into continuous vector representations, which is crucial for processing textual data. This is followed by the LSTM layer, which facilitates the modeling of sequential dependencies in the text by maintaining a hidden state over time. Next, we define the fully connected layer, which maps the hidden state output from the LSTM back to the vocabulary size, enabling us to predict the next word in the sequence. The forward method processes input sequences through these layers, producing output that can be interpreted as probabilities over our vocabulary. This LSTM architecture is fundamental for understanding how we can generate coherent text sequences. As we proceed, we will utilize techniques for bias mitigation and data augmentation, ensuring that our training dataset represents diverse perspectives. This foundational structure sets the stage for addressing the challenges inherent in natural language generation. Now let's implement the following code, which defines a *transformer block * class as a fundamental component in building transformer-based models. This class is designed to capture dependencies in input sequences through its multi-head attention mechanism, enabling the model to focus on different parts of the input simultaneously. In the constructor, we initialize the multi-head attention layer using the embedding size and number of heads specified. This allows the model to learn various relationships present in the data. We also incorporate layer normalization to stabilize the training process and improve convergence. The feed-forward network consists of two linear layers with a RayLU activation function in between, helping to transform the input further and enhance the model's capacity for complex representations. Additionally, dropout is applied to mitigate overfitting. Next, in the *forward * method, we pass the input through the attention layer and combine the output with the original input using residual connections. This approach helps the model retain important information from the input. Afterward, we process the result through the feed-forward network, again using a residual connection and applying normalization and dropout. This structure keeps the model efficient and interpretable, laying the groundwork for more advanced applications in natural language processing. Next, we will write the training loop for our adversarial setup, which involves both a generator and a discriminator. In the train adversarial function, we start by defining the loss criterion as binary cross-entropy, which is suitable for distinguishing between real and fake data. We then initialize the optimizers for both the generator and discriminator with a learning rate of 0.0002. As we enter the training process, we iterate over the specified number of epochs. For each epoch, we loop through the real data provided by our data loader. We establish real and fake labels, where real data is labeled as ones and fake data as zeros. The training begins with the discriminator. We first zero the gradients of the discriminator's optimizer to prevent accumulation from previous iterations. Then we compute the outputs from the discriminator for the real data and calculate the loss based on real labels, followed by backpropagation. After this, we generate fake data from the generator and similarly calculate the loss against the fake labels before performing an optimizer step for the discriminator. Following the discriminator's training, we switch focus to the generator. Again, we clear the gradients, compute the discriminator's outputs for the fake data, and determine the generator's loss aimed at maximizing the discriminator's identification of fake data as real. Finally, we perform a step for the generator. Each epoch ends with a print statement that summarizes the losses for both models, providing insight into their performance and training progress. The accompanying horizontal bar chart titled Future Challenges of Generative Models in Natural Language Processing quantifies perceived impact across 5 domains: computational demand 30%, bias in models 25%, interpretability 20%, generalization 15%, and ethical concerns 10%. From the data labels on each bar, we see that computational demand is the single largest challenge, exceeding the next highest concern, bias, by 5 percentage points and being 3 times greater than ethical concerns. This ordering highlights a clear prioritization. Resource requirements and infrastructure, compute, memory, training time are the dominant operational bottleneck, followed closely by the risk that models will reproduce or amplify biased content present in training corpora. Interpretability occupies a substantial middle position, indicating that understanding model decisions is a meaningful but secondary concern relative to compute and bias. Generalization is lower but still notable, suggesting that adapting models reliably to new domains is an ongoing technical issue. Ethical concerns, while shown at the lowest percentage, remain a distinct category that cannot be ignored. Taken together, the chart implies that practical engineering investments, e.g., model compression, distillation, and efficient architectures, and data-centered interventions, bias mitigation, and dataset diversification should be primary focuses, while interpretability, domain adaptation, and formal ethical safeguards should be pursued in parallel to create balanced, deployable systems. Now let's implement the knowledge distillation technique, which allows us to create a smaller, more efficient student model that mimics the behavior of a larger teacher model. We start by defining 2 classes, teacher model and student model. The teacher model is designed with a more complex architecture, consisting of 2 linear layers with array LU activation in between, enabling it to learn more intricate representations. In contrast, the student model has a simpler structure with fewer parameters, making it faster and less resource-intensive, while still retaining essential predictive capabilities. Next, we introduce the distillation loss function, which computes the callback labeler divergence between the outputs of the student and teacher models. This loss measures how effectively the student model is replicating the teacher's outputs, with a temperature parameter that helps smooth the probabilities, allowing the student to learn from the teacher's softer outputs. Finally, we move on to the train distillation function, where we set up the training process. Here, we use the Atom optimizer to update the student model's parameters based on the calculated distillation loss. Through iterative training across specified epochs, we update the model, ensuring it learns to approximate the teacher's performance effectively. This approach not only enhances computational efficiency, but also retains model quality for practical applications. Now let's implement a simple filtering mechanism to ensure that the text generated by our model adheres to ethical considerations. In this function, we define GenerateText, which takes in 3 parameters: the model used for generating text, the input sequence, and a list of filter words that we want to avoid in the output. First, the function utilizes the provided model to generate a sequence based on the input sequence. This generated sequence is then transformed into readable text using a decoding function, which converts the model's output from a tensor format. Next, we introduce a crucial safeguard, iterating through the list of unwanted words. The function checks if any of these words appear in the generated text. If a filtered word is found, the function raises a value error, effectively stopping the output due to the presence of potentially harmful content. This simple yet effective approach highlights the importance of implementing ethical guidelines in generative models, allowing for an initial layer of safety against the publication of inappropriate or misleading content. Thus, this function plays a vital role in promoting responsible use of AI text generation. In conclusion, despite the transformative potential of generative models in natural language processing, we face critical challenges that need to be addressed. From bias and interpretability to generalization, computational demands, and ethical considerations, there's much to navigate. Nevertheless, by employing innovative techniques such as adversarial training, knowledge distillation, and ethical safeguards, we can harness the power of these models while mitigating their risks. As we move forward in our exploration, we will continue to discover how these models can be applied responsibly and beneficially across various domains, setting the stage for a future where human creativity and machine learning coexist harmoniously. Thank you for joining me in this discussion on future challenges of generative models in natural language processing. In this final section, we will do a project challenge to apply what we have learned so far. The objective of this challenge is to encourage you to leverage your understanding of generative AI concepts by working in small groups to create innovative applications that showcase your skills. You can choose from a variety of exciting project options, such as generating AI artwork using diffusion models, synthesizing images from descriptive text with GANs, developing a responsive chatbot utilizing language models, exploring deepfake technology while discussing its ethical implications, or conducting a comparative study of generative models like GANs and VAEs. Each project requires a detailed written report and a 15-minute presentation, allowing you to thoroughly document your methodology and results while also reflecting on your learnings throughout the process. Remember, collaboration is key, so work effectively as a team to produce high-quality outputs. You can find the complete project guidelines and resources in the GitHub repository linked in the description. Let's get started and have fun creating something amazing.